Dear participants, I would like to invite the chair of our webinar, Professor Adnan Tercan, the editor-in-chief of Turkish Journal of Mathematics, to make his welcome talk.
First of all, I would like to express my thanks and welcome to each participant of our webinar. In particular, I want to mention my appreciation to our honored invited speakers being a part of this organization. As we pointed out in different announcements related to this activity, we hope that our webinar will create an extension which scientists from different fields can share their experiences. Moreover, we expect that our webinar will foster different organizations of our journal in future, like face-to-face international conferences, etc. in Turkey. Recall that Turkish Journal of Mathematics is a science citation index expanded journal, publishing high-quality research articles, and it is supported by the Scientific and Technological Research Council, namely TÜBİTAK of Turkey. Recent metrics of our journal are in positive direction, which encourage us to do our best. To this end, I would like to thank the president of TÜBİTAK, Professor Hasan Mandal, and the manager of Ulakbin, Mehmet Miras Satoğlu, for their support and help, as well as each person who became a member in a different part of our organization. I wish our webinar will be useful and successful for each participant. Thanks.
Dear participants, now I would like to invite the President of Turkish Scientific and Technological Council, TÜBİTAK, Professor Hasan Mandal, to make his opening speech.
So, good morning, or good afternoon, or good evening. So, dear distinguished mathematicians, dear editor-in-chief of our journal, Professor Adnan Tercan, and all colleagues joining from around the globe. So, as the president of the Scientific and Technological Research Council of Turkey, shortly TÜBİTAK, it's a great honor to open this webinar, which will take 3 days, of the Turkish Journal of the Mathematics, by welcoming all distinguished mathematicians in Turkey and around the world. With our vision of the mathematics by advancing mathematics sciences, we have been organized this webinar with a focus on scientific developments in geometry, algebra, and applied mathematics. In this webinar, we take our responsibility to advance the field one step further by bringing together the distinguished mathematicians and extending our outreach to new communities. With these opening remarks, now I would like to share my presentation, which is entitled as the Co-Creating and Succeeding Together for Advancing Mathematics and Beyond. First of all, I should say again, I am a president of TÜBİTAK, but my field of expertise I am working on material science. So I hope that I am doing the right type of opening remarks and the presentation. And also, when I am preparing this talk, I learned a lot. I hope that I'll make a small, very small contribution to the conference or to the webinar. So I am now sharing to my presentation. Now, I guess you can see my screen. Okay, so I name it as the Co-Creating and Succeeding Together for Advancing Mathematics and Beyond. Okay, so this is has been published end of the year of 2021. It's a yearly publishing. Chinese Academy of Science, but it's covering all the world on the different disciplines, and you can see in here the 11 disciplines in here, on the research areas, and it's showing that what is the more giving an impact. I mean, a different type of way of the calculation, but so this is showing that in the different disciplines, what type of topics is in the front in the specific year. So for the year 2021, so it has been named of the double phase anisotropic variational problems is the research hot topic in mathematics. And also when we see some other 10 topics in the same respect, so we can see the top research fronts in the mathematics, including the, new methods for solving the complex mathematical problems, as well as the applied mathematics, course-cutting, physics, medicine, and the data science. So I mean, yes. So you can see in here for the red ones, these complex mathematics problems, and also the orange ones is an applied mathematics problem. So it is giving the whole area which is covering. So it is not only on theory, and also putting a kind of an impact on the different type of applications has been mentioned in physics, medicine, and data science. And in here also, in the same respect, for this 10th research front, so what type of, in terms of the impact side, so you can see also the one on the last, the one on the third from the bottom, on Bayesian multi-level modeling and its application, mathematical psychology. So it is showing that the highest number of citations, not the impact only in terms of the citations, so you can see the highest one. So this is also showing the potential of the mathematics is in using, especially on the different type of scientific and technological areas, not limiting to the basic science only. And in here again, looking for the, again from the research front, and if I back again in here, so you can see again the number one, so the double phase anisotropic variational problems in here, and in looking for this, so how it is this research front changing from year 2018 to 2021. So, and I am very much interested, especially when we started in 2018 on the, the covering research fronts on including the nonlinear Schrödinger equation and application, and it's coming in 2021. So methods of solving high-dimensional nonlinear partial differential equations. So this is a kind of also giving a kind of an impact on you can see in the right-hand side, so solving method based on the machine learning and deep learning. And also you can see some other kind of an impact on the different type of topics in here on deep learning. So so this is also showing a kind of a high impact on the type of publications coming on mathematics. And another one on here showing in one side a deep learning on artificial intelligence, and in the other side on machine learning and multi-scale modeling of the cardiac system. So this is also showing a kind of the impact on the type of outcome of that research front on mathematics, how it could be changed to in machine learning, but in terms of the application on the health sciences. So this is also giving a kind of changing from outcome to the impact. Yes, I'll come to another research front, and in here, so starting again from the mathematical sciences and life sciences, engineering sciences, even on social sciences. solving the problems in these respective areas. And so therefore the research topics on mathematics is covering the different type of areas and also included multiple fields. So in this respect, so with the support of the graph theory and statistics, another research front on complex network theory contributes to characterizing evolutionary mechanisms and behavior of the complex systems. So yeah. And now taking this, research fronts from mathematics to another area on information science again for year 2021. And now you can see the top 10 research fronts on information science. And you can see many of the areas in here, they are closely relating to advances in mathematics to support deep learning, data science, and ICT technologies. So this is also giving a kind of a right link and also the impact on how the mathematics is create and impact on the different type of fields, such as in information science and in other sides on the biological sciences. Again, on the top research fronts, you can see in here, especially on pandemic tumors treatments and image-based deep learning for automatic disease diagnosis have relied on again, mathematics and data sciences. So everything starting from mathematics and moving to type of an application on deep learning, and this is the application on information science and the biological science. And in here, again on physics, so you can see the top research fronts on physics. And in here, the discoveries that based on the twisted bilayer graphene superconductor, superconductivity, and quantum dynamics continue to be again supported by the mathematical advances. So another kind of an outcome impact-oriented type of the mathematics. So now when we see again in here, all the research fronts for 11 areas. Although I have been started to give my remarks on mathematics, especially on the left-hand side, you can see double phase anisotropic variational problems is the #1 research front for 2021. But I also try to show that, information science, physics, biological science, and I am sure that advanced in mathematics provide a basis for enabling the research fronts across all research fields, not limiting to only biology, information science, and physics. From ecology and environmental sciences and to astronomy and astrophysics and also the social science and economics, they have already also been included. So this is a kind of showing the impact of mathematics. Yes, now, we are going to be hearing today and next 3 days on around the globe. We will discuss, how, mathematics, and also at the meantime that this is kind of an outreach of activity of our Turkish Journal of the Mathematics. So, during the last, maybe 10 years, so about nearly 2,350 authors from 93 different countries has been contributed to our journal. So, of course, the highest is coming from Turkey, then China, Iran, US, and India. And also you can see the other countries. So as I said, from the 93 countries, and all have been named in the world map. So I thank all of them, which they have made, they have been, choose our journal and made their contribution. And I am sure that end of this 3 days, and will give a right type of outreach and will make the further impact of our journal in the global arena on mathematics. And when I checked what are the, in a similar manner, what the Chinese Academy of Sciences is doing. And also I have been done the same thing for our journal, Turkish Journal of the Mathematics, on the base of the keywords, not on the hot topics, but on the keywords. And so you can see in the time span of the 2005 and 2020, so covering the 15 years of period, last 15 years of period. So what type of topics are, keywords are is in the top field. So this is, of course, again, covering to all areas. Geometry, algebra, and applied mathematics. So the top 3 topic, keywords with the highest frequency. So you can see from the from this current map on fixed points, analytic functions, and eigenvalues. So these are the top 3, and of course it's going to be some other keywords. The top other 17 keywords in the list as well. So, and in here, so I take the sum of the papers, from manuscripts from this top 3 keywords, and the first one, as I said, for the fixed point in here. And so this is a quite a recent one on the an example is given from researchers from Algeria and Slovakia come together on this 2021 issue on a new example of multi-terms fractional differential equations employing the Banach and Penrose fixed point theorems. So this is showing a kind of a an example, and another one on the second one on we are working on the analytical functions. So this is 2 examples in here given. From one of them is from a joint paper, joint authors from Turkey and Romania. Another one is Kyrgyz Republic and Turkey on new subclass analytical functions for fractional integrals and fractional derivatives. And also other one is on definition of the new subclass of analytical functions that are associated with the, if I am doing the right, Chebyshev polynomials. So this is giving us, with a vision of the advancing in the field of the mathematics, the Turkish Journal of Mathematics is providing contributions to multiple advances and fronts, including the new classes of formulations. And I especially thanked our good colleague, Professor Novi Keha-Yapavlou from the University of Athens. I thank her very, very much. I met with him in different occasions, and I thank her, especially in this conference and meeting and this opening remarks, her great contributions with her knowledge, but also his kind contribution to the kind of a cash contribution to improve the performance, especially for young mathematicians. So, so I thank the. She's also joining us in this morning together to do this webinar. I thank the Novi Hoca. So we are saying her to Novi Hoca. So thank her very much. And also she's our associate member of our one of the basic science institute of the TÜBİTAK. So so once more, thanks her very much. And also, showing her contribution on the proofs and the new theorems on ordered hyper semigroups beyond hyper semigroups. So, and with this vision and advancing the field of mathematics, again, the Turkish Journal of Mathematics is providing contributions to multiple advances, fronts, including order hyper semigroups. So this is also from the year 2021. So looking for again the new classes, on the top keywords on eigenvalues. So you can see the different type of contributions from the year again 2021. So it's coming from our researchers from Turkey and also from Azerbaijan, Iran, and Canada. So it is giving a kind of creating an ecosystem. Our journal creating an ecosystem. From different parts of the globe. In Azerbaijan, Turkey, Iran, and Canada, for example. Yes, so therefore, like in research forms, which I have been shared, so our journal also trying to be contribute and impact on not only limiting to the mathematics, it's covering the giving an impact on all the fields. I mean, all the research fields. So in this respect, I mean, we found, and I personally find that, I mean, always come together with our colleagues from not limiting, of course, mathematics, but physics, chemistry, and talking about that, how we can increase the impact on the basic science to solving our global challenges. Yes, so I mean, so from this part, so I'm moving that, I mean, how our journal will make an impact for the development of our ecosystem in Turkey. So the journal is publishing by TÜBİTAK, which I have been representing as the president. Is now we have been just celebrated our 58th anniversary. Now we are moving to the 59. So our, I mean, TÜBİTAK, I mean, different type of functions, especially our colleagues who are joining from around the globe, has a little information about TÜBİTAK, so I am just sharing in this transparency. So, I mean, we are the funding agency we are funding the universities, but not limiting. So we are also funding the industry for research, development, and innovation for the projects on R&D and innovation. And also we are giving the scholarships and fellowships for undergraduate students, for graduate students, and also the postdocs. And we are also responsible for the science and society activities. So increasing the science and technology awareness in the society. Of course, we are trying to be encouraging our collaboration with internationally around the globe. So the journal is one of the points in this remarks, in this respect. And also we are doing I mean, in one part, we are funding the research and the research ecosystem in Turkey. In the other side, we are also doing, research by means of our 23 research institutes. Yes, one of our great mathematicians, so Professor Dr. Cahit Arf, I mean, he has been, great mathematician, and who supported the foundation of TÜBİTAK. I mean, from the, history of TÜBİTAK, the Professor Cahit Arf is an important fact, and also we are always pleased to be honored with his name in our at TÜBİTAK, and serve as the founding director. Is followed by the new generation of mathematicians following his path, and you can see a different type of his contribution, not only in Turkey, in globally, and you can see also again in the same respect. I have been made an analysis, so how we are using his theories. Yes, you can see some graph theory, information theory, North and quantum theory, surgery, and artificial intelligence. So we are using his contributions now in different fields of the science and technology. And he's also one of the research science awardees. And he was get the TÜBİTAK Science Award in mathematics in 1974. So by using this opportunity, I am giving a great remarks to Professor Cahit Arf Hoca. Yes, this is he's, as I said, the Professor Cahit Arf Hoca is the one of the science awardees in the past of the TÜBİTAK, history of TÜBİTAK in 1974, and it's from a picture from this year. And in recent years, there are 6 science awards given on mathematics. And this is this is a award ceremony from this year. Of course, they are not all from the mathematics. This is the 3 science awards and 14 young incentive science awards is given by TÜBİTAK, and as I said, in referring 6 science awards, mathematics in the recent years. And also, I mean, we are trying to be encouraged of mathematics in Turkey in our research ecosystem, and this is one of the. I mean, there are different type of funding programs, and one of the programs is attracting the outstanding researchers come to Turkey, do their research, and there's an example in here. I mean, from this 127 outstanding researchers who come to Turkey and doing their research, and one of the examples is given in here, come to the Koç University and creating an imaging lab of mathematics. An example is given, so in here, so I mean, so including the mathematics area. And in the other side, as I said, one of the roles for TÜBİTAK is trying to create international collaborations and improving the collaboration to the co-creation to make the more impact. So you can see this map with the green areas we have been collaborating. So, I mean, more or less, I mean, we are collaborating. And so most of the colleagues who are joining this webinar, we have already been a kind of a collaboration with the respective funding agencies in the respective countries. So we are aiming for in the future that we will have more collaboration in the mathematics area as well. And so you can see in here, so Turkey is also one of the founding members, and at the moment for a governing board member of the ANSO is the Alliance of the International Science Organization. And there are different type of platforms of ANSO, and I am personally is the governing board member of ANSO. And the Silk Road Mathematics Center is one of the platforms. So, in this respect, so I am encouraging also our mathematicians around the globe, so can take a role on the Silk Road of Mathematics Center. And the Turkish Mathematical Society is also a member of this platform. So this is also giving a kind of an potential for our mathematicians, which they can work together. So this is also could be a potential in this respect I want to share. And another kind of potential maybe for mathematicians, young mathematicians around the globe, want to come to Turkey, and if they want to continue their research as a PhD student or young postdoctoral researchers, so there will be a new call will be announced in this year, 2022. So you can come for the young researchers, come around the globe and come in here and continue your research as a PhD student or postdoctoral research students. Postdoctoral research associate, and the funding for travel expense also as a scholarship will be provided by TÜBİTAK. And another kind of opportunity which we could supply on the fellowship program, for sabbatical fellowship program. So our researchers again around the globe, so they can come in here, Turkey, can they stay to 1 month till 12 months. So they can spend a certain part of sabbatical part of their research, or this could be extended to up to the 12 months. So you can see in here different type of opportunities which we are providing under this fellowship program. So if any type of request and need, just contact us with our journal or with our editor, and we can, editor can direct you to the right person to get a further information, and we are very happy to provide kind of the information and also assist you to find maybe the right institution in Turkey to spend your certain part of your sabbatical leave. And another opportunity as TÜBİTAK, which we are providing, I mean, in one side, fellowship or scholarship for PhD and postdocs, and also, I mean, for experienced researchers to spend their time as an sabbatical leave. And also we are giving a funding to organize I mean, joint and collaborative events in national-wide or international-wide. So this also been covering organizing the workshops, seminars, panels, and colloquia, different type of events. And so this also could be another opportunity to further extending your already existing collaboration to be a more outcome and impact type of activities, and by using it as our program. And as I already mentioned, that TÜBİTAK in one side is the funding agency, in the other side is doing the research, and doing the research on the critical areas. So you can see these 23 research institutes on different type of fields. I'm not going to be talk about the details, but I mean, it's covering to all extents on IT technologies, on biotechnology, food, energy, environment, material science, and also including the space, defense, the railway, metrology. But I think is also one of the important research institute, especially in the recent years. It's, I mean, giving the right type of role, I mean, giving the right type of impact into the Turkish ecosystem, but getting the help from around the globe, like what we are doing this webinar, by means of the Basic Science Research Institute. So, and in this institute, we are covering the mathematics as well. So our director is also one of the TÜBİTAK Science awardee, Professor Ali Kam Nurbaloğlu. So he's the director of this research institute, and also it is covering the research institute, Basic Science Research Institute, covering the, I mean, advanced topics of basic science, and encourages interdisciplinary studies and trains leading researchers who will make significant contributions. So you can see the type of areas we have been working on it, not limiting, but at this moment we are working on the science of the universe, quantum science, computational science, applied mathematics, mathematical physics, and particle physics. And what type of activities which we are having. So, I mean, and organizing different type of activities. I mean, so you can see, and they are all in international level, and especially during the pandemic period. So this institute have a great job and great activities, and I also thank very much all the contributors to our research institute, giving their strong contributions and giving kind of a right potentials for our young researchers, especially in Turkey, for their I mean, interest on basic science. And so you can see some of the activities and different type of webinars, conferences, public lectures. And I am also trying to be involved by personally and giving a full support on our research institute. And but also we are trying to discuss the issues. On one side is the deep in the science, but in the other side, how we can solve the problems for today and especially for the future. And also some of the examples are again like in given and given in here on with I mean another public lecture series on scientific Turkey, public lecture series. And so we are talking about on mathematics, physical, and applied mathematics seminar series. So you can see and you can give the some of the examples in here on this area. Yes, some more examples. So we all thank all our contributors who make, kind and strong, commitment, and definitely will be get, in Turkey and in general, and still available in YouTube. So we all get the benefit from their experiences and also from their lecture. Yes, and maybe I am just coming to the end. That yes, what we are doing in here, and mathematics is the right area. So because we have been many challenges, and we will have also not for today. I mean, we are facing for today is the pandemic. In the other side now, we are talking about the climate change and their impacts, and cyber security attacks. So different type of challenges which we will have today and also in the future. And the science is the only way to be solve these problems, not temporarily, permanently, but more, to get the more impact of the science. So it is a more need on the open science. And our journal also is contributing in this respective to, in the open science platforms. And as TÜBİTAK, we have been a policy on the TÜBİTAK open science policy. All our research journals are freely available and open access. And we are also encouraging, because we are the funding agency, and also with our outcomes of our funded projects, we are encouraging them to be published in the open science, to helping the open science policy. So this is also kind of the way, what we are having today, and tomorrow and after tomorrow also is helping to our open science policy. Yes, during this, first issue of our journal, for which we have been published, so there are 23 articles. So you can see what are the topics has been bring into the attention on these 23 articles. Again, it's covering the new functions and improved mathematical solutions that will definitely contribute to scientific advances. And also we have been, as the second issue for this year, we have been a special issue on this places emphasis on the differential and difference equations as tools for the adequate modeling of the dynamic processes, with contributions from the 47 eminent mathematicians. I thank all of them from the 9 countries, and some of them will be us today, tomorrow, and after tomorrow. So I'll also thank you very much for their contribution in the journal, and also for their attendance during this webinar. And I especially thank, all the contributors for the next 3 days, and especially our colleagues will have a great effort in this webinar, and focusing on the studies contributing to the scientific developments in geometry, algebra, and applied mathematics, with they accepted our invitation and attending this webinar and give their contributions. I especially and personally thank all of them very much, and this definitely will increase the impact of our journal in Turkey and also around the globe. Finally, I'll say, so we need a future of co-creation to achieve the advanced future with mathematics. So in this, with these remarks, I thank very much for your attention. I hope that I am a material scientist, so I am not coming directly from the field, but I have been learned while I am preparing my presentation. So I am willing very much and looking forward what will be the outcomes during this next 3 days webinar series. I know that it's a very tough program, starting very early morning till very late night, and I wish very much fruitful discussions and also contributions, and I'll try to give my all support also, not for today, also in future, for the development of our journal. So thank you very much, and enjoy the conference or the webinar.
I would like to take this opportunity to thank the President of TÜBİTAK, Professor Dr. Hasan Mandal, for his informative talk. Thank you very much, Hocam. We will continue our academic program in 5 minutes. Thank you for your attendance. Dear participants, I would like to invite Professor Dr. Veselin Drensky from Bulgarian Academy of Sciences in Bulgaria. It's a great pleasure for all of us to have here Professor Drensky for the valuable talk on non-finitely based and limit varieties of algebraic systems. Professor Drensky, you are welcome to do your presentation, please.
Thank you very much. Let me share the screen.
Yes, you may start, please.
It's okay now?
Yes, it's okay.
Okay. First of all, thank you very much for the invitation to give a talk.
Sorry, Professor, could you please share your screen, full screen?
Yeah, sure. Now it's okay?
No, we can hardly see your screen.
But this is full screen now.
Okay, please
You
go
can,
ahead.
sorry, you can try to click Control L.
Yeah, I already had Control L.
Yeah, okay, it's perfect.
Okay, thank you very much. First of all, since of course, I'm very grateful to present this talk. Although I have a long time cooperation with the young Turkish mathematician Sheikh Mus van Dijk from Adana. So he spent 2 years in Bulgaria, and we still work together. And since I give some references in the talk, the best way to see this is simply to ask me by mail. Here is my email to send the presentation, or if the organizers have the presentations posted, I'll send them to post the presentation. So if ask a person which are the main problems in the algebra, very naively you should answer, describe all groups, all semi-groups, all rings, all algebras over field, associative, non-associative. But of course, this is a hopeless problem. So we need something else. And there are two obvious approaches. One of them is the structure approach, and the other is the combinatorial approach. For example, the algebraists, even the master students, they know that the finite dimensional associative algebras, they have a good structure. They have the Jacobson radical, which is nilpotent. Modulo the radical, you have an algebra which is semi-simple. Every semi-simple is a direct sum of simple algebras. You know which are the finite dimensional simple algebras, etc., etc. So you have a good description of finite dimensional algebras. But what is the combinatorial approach? You divide the algebraic objects in classes. You call these classes varieties, depending on the defining relations which they satisfy. The good thing here is that you can do the same things for groups or semi-groups, for rings, for algebras, commutative algebras, associative algebras, Lie, Jordan, etc. This idea is very old. It comes from the work by Gareth Birkhoff, Universal Algebras, and Bernard Neumann on groups. This is from the 1930s. And I'll speak about groups, but the same is for semi-groups, for associative rings, etc., etc. If you have a set X, then there is an algebraic group, algebraic system, for example, a group in the class of groups, which is generated by this set, and this has the universal property that if you send the set X to some algebra or to some group from the same class, you extend this uniquely to a homomorphism from the free object to the object you have chosen. You call this the free algebraic system in the class of algebras freely generated by this set. So we assume that X is a countable and infinite set, XD is a finite subset, and for the corresponding algebras, you write F of V or FD of V when you speak for the corresponding object. So, how this object look like? For example, for the class of all semigroups, you have simply all the words in the axis, and you multiply two words, simply writing him one after another. When you speak about monoid, you add also one to this set. If you have commutative semigroups, you simply have all the monomials in commuting variables. Something similar, if you have groups, of course, you also allow the inverse of the elements. For the abelian groups, you simply have monomials with negative and positive degrees in the variables, etc. The same is for the free associative algebra. Here, over a field of for the free associative ring, you simply have linear combinations of such elements. And if you consider non-associative algebras or non-associative rings, you have a similar object, but you have also parentheses in the words. And what is a variety? So you take, for example, some group or semigroup, the class of groups or semigroups, and you take two words, and you say that U and V, you say that U equals V is an identity for an object. If you replace the variables by elements, you got an equality. And if you consider all the objects which satisfy a given system of identities, this is a variety defined by this system of identities. And of course, you speak about that one identity forward from other identities if it goes for all the cases when these identities hold. So there is a theorem by Birkhoff from the 30s, which states that a class is a variety if it is closed under three operations, taking homomorphic images, sub-objects, and Cartesian products. So if you have an algebra R or a group R, and you apply first Cartesian products, then you apply sub-object and homomorphic images, you get all the class of the varieties. So in this case, if you start from an algebra R, the variety generated by algebra R, these are all the elements, all the objects obtained in this way. Now, traditionally, here you have something which is different from linear algebra. You say that a set of identities is the basis of the variety of the identities if it is defined by this set of identities. And this is finitely based if you can define it by a finite number of identities. You don't ask about independence of the identities. You simply use this word basis for all the cases. And if you cannot define a variety with a finite number of identities, then you say that this is not finitely based or infinite based. And what is the finite basis problem? Is it possible to define any variety with a finite number of identities? Of course, you have a weaker version of this. If the variety satisfies some explicit given identity, can you be sure that this is defined by a finite number of identities? And of course, if not finitely based varieties exist, to give an explicit example. So in the sequel, we shall discuss only examples of infinite based varieties. There are also a lot of positive results, but we skip them. We speak only about infinite systems. So the first examples, they come in same groups from 1965, when Birukov proved that this system of identities here is not finitely based. And a little bit later, there is another example, also of semi-groups. But now, about 35 years ago, there was a survey article by Shevrin and Volkov, when they gave more than 40 examples of varieties of semi-groups which are not finitely based. And this number now increases. For the case of groups, the problem was asked by Bernard Neumann in 1937, and the first result was only in 1970 by Alexander Roshansky. He proved that there are continually many varieties of groups. And as a consequence, there are infinitely based varieties. And the first explicitly given examples were by Adyan. You know that Novikov and Adyan, they proved that the Berser, they gave a negative answer to the Bersen problem, that if you have a group which is finitely generated and a given exponent, is this finite or not? And using this technique, Adyan gave an example of variety which is not finitely based for the case of groups. So these are the defining relations. You take the commutator of x in power pn and y in power n, and you take everything in power n when p is prime. And in this case, you get a variety which is not finitely based. There is another example by Michael Vaughan Lee, which is also in 1970, which is much easier to understand because it doesn't use the complicated theory of Novikov and Adyan. And here are the identities which define this one. Here, when I speak about group commutators, they are left normed, so they are in this way. And the simplest examples, they are due to Yuri Kleiman in Russia and Roger Bryan in England. They prove that the so-called product of varieties before A2 is not finitely based. This variety consists of groups which have a normal subgroup, which is a billion of exponent 2, and the factor group is of exponent 4. So this is the base of the identity. You have a product of squares in power 4, and you cannot remove all identities but finite number to get everything which you need. And for infinite based varieties in non-associative objects, there are simple examples which work in the same way for non-associative rings, non-associative algebra over any field. For binary magmas, so magma, this is a set with one binary operation. So these are the identities. This is almost obvious that you cannot remove any of this identity. And if you remove, you get something bigger. And the first example for varieties of Lie algebras, it was given by Michael Vaughan Lee in 1970. It was over a field of characteristic 2. This was the central bimetabelian variety defined by this identity, and a series of identities of this form. And it's proved that this is not finitely based. And Vorichenko, 10 years later, here there's misprinted CH, Vorichenko, he added to this system one more identity and obtained a variety which is locally finite. Locally finite means that the finitely generated algebras are finite dimensional, or finite when you speak about groups, for example. And if the field is infinite and of characteristic 2, then you have a very nice example, 2 by 2 matrices considered as Lie algebras. They have no finite base of the polynomial identities. This is in the same paper by Vaughan Lee. Then the explicit form of all identities, it was in my PhD thesis in Moscow in 1979. Lopatin 4 years ago, he found another proof. And the identities, they are this one. You have central parameter big identities, the identity of only, and this identity here, a series of identities, where you have 1, 2, 3, 4, and you take cyclically 2, 3, and 4. 3, 4, 2, 4, 2, 3. These identities, they form a basis of the polynomial identities for 2 by 2 matrices over an infinite field of characteristic 2, considered as a Lie algebra. And also there is another example by Vaughan Lie, also for Lie algebra. This is a big and binary-potent varieties of Lie algebras, again in characteristic 2. A big and binary-potent of class 2, this means that if you have commutators of length 3, and you take 2 commutators, you get 0. And these are the identities which form a variety which is not variety-based. You see here you have 1, 2, 2, 3, n minus 1, n, and 1. So you take cyclically all the elements from 1 to n. And of course, there is a natural problem. There is a simple 3-dimensional Lie algebra with the vector product. So this is an analog of the 3-dimensional vector space with the vector product. In characteristic 2, when the field is infinite, is the basis of this polynomial identities not finite. The problem is that if you consider a field of characteristic different from 2, 2 by 2 matrices and this algebra, they have a finite basis of the identities. So this is something which is, I believe that this is the case, but I'm not sure how to prove. I don't know how to prove it. And when the characteristic is positive, but bigger than 2, then I have a paper which shows that there is an infinite-based variety. These Lie algebras, they are solvable of class 3. This is the solvability. They have some analog of the identities of only. And this result was obtained independently in the same time by Ulrich Kleiman, but it was not published. And also, if you add to this system this polynomial identity, if you multiply several times by x2, you get 0. Then you find a variety which is locally finite and still infinite based. And there is one more example. This is in the same paper, which I already had the first example. In characteristic P over infinite field, there exists a finite dimensional Lie algebra with infinite basis of its polynomial identities. And of course, there is a very difficult open problem. What happens in characteristic 0? Are all varieties of Lie algebras over a field characteristic 0 finitely based? For associative algebra, this is the answer is yes, but for Lie algebras, we don't know. And for associative algebras, this problem was asked in 1950 by Specht. Jürgen Specht, he is known in his results on representations of the symmetric group and also some other representation theory, but also he has one paper in ring theory. This paper, which is translated in English, this is walls in rings, the first part. He asked the problem about finite varieties for unitary associative algebra over a field characteristic 0. And this paper, all the branches of algebra that now you call Specht, the Specht problem, the problem about finitely based problems of any algebras, groups. And in the 1980s, Kemmer, he proved, he developed a structure theory of T ideals. This means ideals in polynomial algebras. And I'll mention only two consequences: that the polynomial identities of every finitely generated PI algebra means algebra with polynomial identity, are the same as the polynomial identities of some finite dimensional algebra. If the algebra is not finitely generated, then there is an analog, which is stated in finite the affirmative answer to the Specht problem, that over a filter characteristic 0, all polynomial identities of associative algebras follow from a finite number of identities. And in characteristic P, there are also a lot of examples. The first example was given by Belov in 1999, and almost in the same time there were two more examples by Grishin and Shigolev. It's amazing that these three persons, they participated in the same seminar, in the seminar of Latishev. In the most seminars, they presented three different answers to the Specht problem in characteristic P. And these are the papers where they are given. But there is a very simple example in characteristic 2. This is by Gupta and Krasilnikov, Kantor Gupta and Alexei Krasilnikov. This is in 2002. These are the identities which, without finding base of the identities. And there is one more example, again in characteristic 2, again by Kantor Gupta and Krasilnikov, with this identity. So you can explain the proof maybe to a graduate student in algebra. Even the person is not a ring theoretist, but any kind of algebraist. And there is a conjecture that over a filter characteristic 2, an infinite filter characteristic 2 by 2 matrices, they don't have a finite base of their polynomial identities. For algebra, this is the case, but we don't know what happens with associative algebras. But it would be nice to have such an example. And now there are also some positive results when we speak about finite objects. For example, if you finite Jordan algebra or finite rings of the same class, they have a finite base of their polynomial identities. For groups, it was Schultz and Powell in 1964. For associative rings, finite dimensional associative algebra or finite fields, it was Kruse and Wolf in the 70s. For Lie algebras, it was Bertoul and Olshansky. For Jordan algebras, it was Medvedev. So there was a lot of activity in the 1970s about this one. And they all used structure theory of groups and rings. But for Lie algebras, the proof involves also quasi-identities. Quasi-identities, if something happened, then something. Yeah. And also this is known that you have a finite critical object, so I don't want to describe what's a critical object. And the problem, this is the following. If you have a finite algebraic system with a finite system of operations, it is true that this is finitely based. It was asked by Birkhoff in 1948, and the first result needs directions for 2 elements. If the algebraic system consists of 2 elements, it was answered by Linden in 1951. And the comment of Linden was that it is perhaps surprising that this problem is not entirely trivial, even for algebras that contain only 2 elements. So, other examples, Linden, okay, he showed that if you have an algebraic system with 7 elements, and you have 0 and you have 1, and you have 0 and you have 1 binary operation, and you have tables that almost all elements are, all the products are zero except this one, then you have that some identities which cannot follow from each other, so that this system has not finite number of identities. Then, of course, you can go further and ask what happens, what is the minimal number of elements of a finite algebraic system without finite basis of the identities. For 3 and 4, when the object has 3 or 4 elements, there is an example by Vishin when you have an element operation, 4 elements in the set. Even there is some set of identities which is okay, relatively nice. And finally, Mursky, he proved that there is a 3-element binary magma which is not finitely based. It consists, this is the multiplication table. And if you go further, the idea of the proof that Mursky showed that you have a system of identities depending on n variables, which don't follow from any system of identities in less than n variables. So for any step, you have to add new variables to get what you need. So you know that all these problems about finitely based problem, they have some logical aspect and also they have philosophical objects. Because if you can define something with a finite number of identities, from the point of view of philosophy, this is nice. If you cannot do this with finite, this is something which is not good. And if you translate the problems in the language of logic, you can ask, is there an algorithm which allows from finite algebraic objects as an input to determine the Turing machine. You can construct an algebra which is finite and the finite type such that the Turing machine stops if and only if the algebra has a finite base of these identities. But there are also some other results in this direction in the 60s, but I think that this problem is still open for finite semigroups. And if you consider semigroups with finite
I think there is some connection problem. Let's wait a couple of minutes.
I'm sorry, but I should start the. Can you see now?
Yes, yes, please.
Okay. I'm sorry, but
Don't worry.
in my home, the connection sometimes is very bad. So there is an example of some finitely based. These matrices, they have only zeros and one. And if you consider semigroups of 5 elements or less, then Tarski asked the finitely based problem for such semigroups. And there were a lot of attempts for all these things. And it was shown that, for example, that every semigroup with less than 5 or less elements has a finite base of these identities. So if you have an infinite system of independent identities, so this means that you cannot remove any identities to have the same things, then you have a fine continuum of subvarieties for 6 element same groups. Something strange happens here. So there are semi-groups which have an infinite base of identities, or they have a finite number of identities. So they are, when we speak about 6 element semigroups. So this is something which is Trachtman here has a result that if you have 6 element semigroups, it generates a varieties with continuum subvarieties. The same was, another example was by Edmonds, Lee, and Lee, much later. And if you consider semigroups with 5 elements, and all they generate varieties with finite number of subvarieties or count many subvarieties. There is only one exception. We don't know what happens with this semigroup with 5 elements. How many subvarieties it has. And I already mentioned that there was a paper by Chevron and Volkov in the 1980s, and now there is also a more newer papers when they study such questions for varieties. So I showed 2 exotic examples. One of them, you have varieties of same groups. So based, but if you consider involution of semi, is not finite based. And now, when you speak about finite rings and finite dimensional algebras, the first counterexample of a finite non-associative algebra without finite base of identities, it was given by Pauling in 1970s. To multiply from the left, you get 0. And there was an improvement of this example. This is by Wolf, who started with a 2-dimensional vector space and added 2 by 2 matrices, such that the multiplication is that all the products are 0 except when you multiply a vector and act on the vector with a matrix. Then again, this algebra satisfies a left nilpotency, and it has no finite base of its identity. This idea was further developed of this kind. For example, Maltsev and Parfenov, Yuri Maltsev and Parfenov, they did this in characteristic 0. The algebra was 5-dimensional again, but the vector space it had an action with 2 by 2 upper triangular matrices. This algebra has a base of polynomial identities, which are this one. Here again, the products, they are left normed. And when you consider a positive characteristic of a finite field over an arbitrary finite field, you have papers by Isaev and Keskitsin. You have also a 4-dimensional algebra with infinite base of the identities, over any field. This is a little bit similar. You have a two-dimensional vector space acting with two matrices. So it was done 5 years ago in 1950. But all these experiments use the notion of weak polynomial identities. So you have an associative algebra or non-associative. F is a weak polynomial identity for the pair RV if it vanishes in R when you replace the variables with elements from B. Of course, you can consider the same for free associative algebras when this algebra R is associative. And further, we shall discuss what happens only in the case of associative algebras. So the weak polynomial identities, they were introduced by Razmissov to solve two important problems. The first one was to give the polynomial identities for 2 by 2 matrices, both associative and leading characteristic 0. And also to construct central polynomials for matrices of any size. The central polynomials, it was the existence of central polynomials, it was one of the central polynomials in ring theory, and it was solved independently by Razmissov and Formanek, by Formanek in 1972, in Razmissov 1973. And depending whether you start an arbitrary subspace V, or this which generates R, or V is a Lie algebra, or it's a Jordan algebra, then you can consider different consequences for the identities, depending on the structure of algebra. And there are many applications of weak polynomial identities. For example, Vonley constructing infinite-based varieties of Lie algebras in characteristic 2. In practice, he showed, although he didn't state it explicitly, that if you take commutator of length 3 and this system of identities, weak identities, this has not finite base of identities. Something similar happened with Bolichenko in characteristic 0. He showed that this variety is finitely based, but the key moment was again that if you consider weak polynomial identities satisfying this identity, commutator of length 3, this has no finite base of the identities. And of course, you have a problem. What happens in the case of positive characteristic bigger than 2? If you give an example, then you have an infinite based varieties, which is a variety of nilpotent, a big and binilpotent class 2 algebras. And also there are some other examples, so I don't want to discuss. So probably when you consider varieties weak polynomial identities, this is natural to consider also varieties of group representations. So you start with a free group, and you consider the group algebra over a field. So if you have a group G and you have a G module, then you say that you have an identity in the pair GM, where G is the group, M is the module. If you take this polynomial and you replace the elements by elements from the group, acting on M, this goes 0. So there was a lot of activity in the school of Plotkin, in Boris Plotkin in Riga. Also, there are books, one book in Russian, one book in English about this. And if you start again about the non-spectrum varieties of group representations, there are examples by Gupta and Krasilnikovs. So in characteristic 2, you have two varieties one satisfying this identity, one satisfying this identity. Here in the square brackets, this is the Lie commutator with usual parentheses. This is the group commutator. And of course, you can speak also about varieties of representations of the algebras. The same statement, but instead of group elements, you take elements from the algebra. And again, in characteristic 2, there is a counterexample. This counterexample is due of Krasilnikov-Shmelkin. If you have an infinite field of characteristic 2, you have this algebra. So you have here upper triangular matrices, zeros in 2 of the places, equal elements here on the diagonal. Here you also have, so this is something 3-dimensional. And this algebra, it has a representation which is 4-dimensional, and it has no finite base of this identity. So this is nice to have examples similar to examples of Krasilnikov and Gupta for group representations for any field of odd characteristic, or of the theorem of Krasilnikov and Shmelkin for infinite fields of odd characteristic. But now I say a couple of words about limit variety. The variety is limit or just non-finitely based if this is not finitely based, and all of its proper subvarieties are finitely based. Of course, by the Thorne lemma, if you have an infinite base variety, it has a limit subvariety. But now I shall discuss some results on explicit examples of limit varieties, which don't depend on the Thorne lemma. For groups, we know that we have limit varieties because Newman, he showed that for any prime p bigger than 2, there is an infinite based variety of p groups. So as a consequence, for each variety you have an infinite, you have a limit subvariety. So the limit varieties are infinitely many. So, but further, it turns out that there are uncountably many limit subvarieties of groups. So this is Kozhevnikov. This is his thesis in Moscow State. And also, there are no explicitly known examples of varieties, limit varieties of groups. There are examples of varieties which are very close to limit, but they are, up to now, there are no examples. There are examples so-called bigroups. Bigroups are generalization of integral representations of groups. There are many such results. There are examples for semigroups. They come from the early 80s. And there are more examples by Pollack, by Mark Sapir, by Leon Volkov. And also, it is known that it was by Kleiman that there is a 6-element semigroup which generates a limit varieties of inverse semigroups. And this is the only limit example which is not a limit varieties of groups. So this is something which is, you have 2x2 matrices, which example we already had in some a little bit before. And now the hunting for limit varieties continue also nowadays. You see that there are papers which are even in which are published in 2021 and which are in a peer or which are posted in a peer in archive. So there's a lot of activity still on this problem. For Lie algebras, there is only one example which is known for Lie algebras in characteristic 2. This was done by Volichenko to this central Hamiltonian identity. You added several more identities to get something which is not finitely based. This was in preprint. It was never published in a journal. And if you consider algebra's characteristic 0, it's easy to construct such limit varieties. So they are anti-commutative. The product, they are metabelian in the product of two products of 2 days 0. They satisfy also some other identities. And one can show that this variety is generated by a 6-dimensional algebra with such basis A1, A2, A3, B, C, G, and such non-zero multiplication. And the proof, as in the original proof of the previous one, it used representation theory of the general linear group. And also, you can change a little bit this variety to make it commutative. And again, you have a 6-dimensional algebra we generated. So, if you consider varieties of pairs again, you have a lot of examples due to Isaac-Slitin. So I don't want to discuss the proof, but there is a problem which seems to be realistic to find a limit subvariety of the variety which was generated by this algebra here, and to show that to find a limit subvariety. Also, the examples I already gave with finite dimensional algebras which generate limit varieties, they are either commutative or anti-commutative, but it was nice to have such example which is of this kind. And also, it's natural to ask to find limit varieties of algebras in positive characteristic and over finite fields. Of course, you can do the same for associative algebras, for the algebras. And now there is a lot of activity about books which you can read about this. They are by Barturin. Barturin has a new edition of his book, which appeared in a year ago. There are also some survey articles. My book on pure algebras, it has something. There's a paper by Kanel, Bloff, and Trouwen. Also, there is here Vishne. This is an exposition paper with free access. There is one more paper. So this is, thank you.
I would like to thank you, Professor Dranski, for his valuable talk. Thank you for your attendance. We have 5 minutes break for the next session. Professor Dranski, could you shut your screen?
Sure.
Thank you. Please.
Oh, it's okay.
Hello everyone, welcome to our webinar again. I am Hande Uslu. This is our first session for our first day. And I would like to introduce our first presenter. He is the Ismail Aslan from the Ankara, Turkey. His presentation title is Phi Variational Approximation by Mellon-type Nonlinear Integral Operators. Ismail Hocam is here. Welcome. Yes, we can.
Hello.
Yes, we can see your screen. If you are ready, we are ready also listen to you.
Okay, I am ready. Hello, everyone. My name is Ismail Aslan from Hacettepe University, and my title is Phi Variational Approximation by Mellon-type Nonlinear Integral Operators. It is known that Mellon-type integral operators have a great application area. They could be useful in physics, engineering, statistics, economics, signal processing, and etc. In this presentation, we will talk about approximation properties of Mellon-type nonlinear integral operators. And nonlinear forms of these operators are investigated under Phi variation together with the Lebesgue measure in the literature. However, due to the homothetic structure of these operators, it seems that Haar measure is more suitable for this type of operators. So, in this presentation, we will consider the Haar measure under convergence in Phi variation in the definition of the operator. We also improve our operator by a regular summability methods given by Bell, which contains many well-known methods such as Cesaro and almost convergence methods. We also study the order of convergence with the help of suitable Lipschitz class of Phi absolutely continuous functions. And the inverse of our mean approximation theorem is also considered, which allows us to obtain a general characterization theorem for Phi absolutely continuous functions. And at the end, constructing some suitable kernels, we illustrate our approximations. Let me first give the definition of this Bell summability. Here is given which is a family of infinite matrix of real numbers and X be a sequence. Then the double sequence given here, the double sequence is called A transform of X if it is convergent for all n and mu. And we say that X is A-summable to L if this A transform converges to a number L uniformly in mu. This is the definition. Some basic properties, as I said in the beginning, if we choose A is the identity matrix, then we get the classical convergence. And if we choose Cesaro matrix instead of A mu, so we get this Cesaro summability method, which is also called arithmetic mean convergence. And if we choose almost convergence matrix, our summability reduces to almost convergence method, which is given by Lorentz. Throughout the paper, we assume A is regular. Regularity is, as you know, if xk tends to L, then A transform of X goes to L again, then we call that A is regular. Now, before our mean approximation theorem, I will talk about some basic definitions and notations. Here is the definition of Phi function. Phi is from positive real numbers to itself, which is continuous, non-decreasing. At 0, it is 0, and positive when S is positive, and it tends to infinity when S tends to infinity. From now, we always assume that Phi is a convex Phi function with this limit. This limit is needed for the modulus of continuity. So another space is that L mu1, which is the space of integrable functions with respect to R measure. So, as we said, we consider the Musialak-Orlick's phi variation in this presentation. The definition is that for a given measurable function f, this supremum phi f pi minus 1, so the summation, supremum of this summation, where p is equal to this increasing sequence, it is called that phi variation of f. So this is the definition of phi variation of f. And the space of functions of bounded phi variation will be denoted by this one. The definition is here. It is given by that f is R measurable and there exists a lambda positive such that this variation is finite. This is the definition. Another definition is locally phi absolutely continuous functions, which we need in the approximation theorem. The definition is that for all I, which is equal to AB, and for every sufficiently small epsilon, if we can find a delta positive satisfying that this is less than epsilon, whenever this is less than delta. So if you find a such delta, then we say that f is locally phi absolutely continuous function. And the space of this type of functions are will be denoted by this symbol. Okay, now a history of our problem is that Mellin type integral operators are introduced by Bardaro and Vinti, which is given here, the definition of the operator. They prove the convergence of this operator under phi variation. But here, as you see, this is a linear operator, and they use Lebesgue measure. And then they also construct a nonlinear form of this operator again in 10, but they again use the Lebesgue measure. So different from the literature, we use R measure here. Again, it is nonlinear, but we also improve our operator by a regular summability method. This is the definition of our operator. Lk is given here, R measurable on R positive, and it is integrable. On the other hand, Hk given here from real numbers to itself, it is 0 at 0, and Hk is a psi-Lipschitz function, different from the Lipschitz function. It is a more general form, which means Hk satisfies this inequality. And here, psi is a Phi function. Okay, another condition is that, which is common in the nonlinear setting, phi, eta, and psi will be properly directed throughout the approximation theorem. The definition is that if for all rho in 0, 1, one can find a zero in 0, 1 again, satisfying this inequality, we will say that phi, eta, and psi is properly directed. Now, these are our assumptions, which are a generalization of approximate identities. This supremum will be finite for every fixed delta in this interval. A transform of this limit will be 0, and A transform of this limit will be 1. These three are the conditions on the LK kernel, and the fourth one, given here, GK is HKU minus U, so this limit goes to 0 with uniformly in every proper bounded interval. This is the condition of nonlinear kernel HK, which we utilize in the approximation theorem. We realized that if psi compose F is in this space and condition I holds, then our operator is finite. And furthermore, if I is satisfied with this condition, then our operator is also in this space, L mu 1. Another lemma is that If f is in this space here, dv eta, and condition I holds, then we get this inequality. This inequality means that our operator maps from dv eta to dv phi. Okay, so under these assumptions, I4, and if f is in this space, then we can find a lambda positive satisfying this main approximation theorem. So, which is improved and which is under hard measure. Okay, for the order of approximation, we use these three conditions on LK. This assumption, remember, it must be 0. So we say that this statement goes to 0 in this rate. This statement, this expression goes to 0 in this rate, and this one also goes to 0 in this rate. These are three assumptions on LK. And the fourth assumption is that this one goes to 0 in this rate. So these are four conditions, and now in order to investigate the is this common in the rate of approximation, we utilize from the Lipschitz class of phi absolutely continuous functions, different from the classical one. Here there is log p, logarithm function, so it is more suitable in this setting. So under these assumptions, we prove that this operator goes to 0 in the rate of n to the power minus alpha for every f in this space. Now we will investigate the inverse of our approximation theorem. I will skip this definition. Okay. In order to investigate characterization theorem, we need this condition. As you see, this is a more general form of being a locally phi absolutely continuous functions, because there is an A transform here. But to make it more suitable for our for the proofs, as an equivalent condition, we need this one. The inequality can easily be seen by this paper 6. So we have two equivalent conditions. Now, if LK satisfies this one of these conditions and I holds, and if this composition is in this one with this condition, then we see that our operator is also phi absolutely continuous functions. Be careful, f is not phi absolutely continuous functions, but operator is phi absolutely continuous functions. So this lemma is very important for the proof of theorem 5. Theorem 5 is our characterization theorem. F is phi absolutely continuous functions if and only there exists a lambda positive satisfying that this approximation goes to 0 under these assumptions. Okay, we give a general condition, but in order to show that the existence of this type of kernel, we construct one of them. This is LK given by here, and we assume for simplicity for now psi is this one. So LK satisfied all the conditions of theorem 5, and this is the graph of LK. Now in example 2, we construct another kernel for our approximation theorem. LK is this one, but this time it is not a continuous function. And HK we use from the paper 3, HK is this one. Now using this, we will show an illustration. It is not hard to show that our operator satisfies the conditions I4 and capital I4. So these are just proofs. I will skip them. And this is the graph of LK. So they are not continuous. And for an example, we assume that f of x is R tangent x, but it is the domain is R positive. It is not hard to see that f is in this space. So taking this taking phi equals eta and lambda equals 1, we can easily prove that our operator approaches to 0, where the operator is given here. For simplicity, we just assume that A is identity matrix, but it is not hard to find another forms for this type of operators. But just for simplicity, I assume A is equal to identity matrix. And as you see, the continuous line is R tangent X, and the dotted dash dot are our approximations, our operators. Finally, if we take A is C1 Cesaro matrix, our approximation turns into this one. And if we assume almost convergence matrix, our approximation turns into this one. And as you see in the example, if we assume A is identity matrix, then we get the classical convergence. I should note that this study is supported by TÜBİTAK, and here are my references. Thank you for listening.
Thank you very much, Ismail Aslan Hocam. I would like to say it's a very interesting presentation, and we were glad to arrange your schedule to attend this webinar program. I would like to ask, is there any question or any valuable comment for Ismail Hocam from the panelists or attendees? If you have any question or comment, you can use the Q&A window. It means question and answer part from the last button in the screen, and you can write your question. Let me check. Okay, I think there is no question. I would like to say again, thank you for this nice presentation. And also we are very glad to your contribution to our webinar. Then let me introduce our next speaker, Sabah Beyicbey from the CİTİK'te Algeria, with the presentation entitled by Stability Result for a Weakly Non-Linearly Damped Porous System with Distributed Delay. If she's here, she can share her screen. I couldn't see her attending. Okay, let us wait a couple of minutes if she can attend. Okay, by the way, let me remind one more time, if you have any question, you can use the question and answer window, and you can check the schedule from our web page to attend other presentation. Hello again. The time for waiting our speaker is over. So we will continue our program as scheduled. Because of that, now we are making a little break until the 11:40 with our next speaker. So see you soon.
Hi, get to yes, please. Please. Let's see.
Hello again. Thank you for your patience for this little break. Now we are ready to listen our next speaker, Professor Osman Alagöz from Algebraic, Turkey, with the presentation entitled by Approximation by Sampling through Meyer Operators in Weighted Space of Functions. If you are ready, we are ready to listen you.
Thank you so much. Do you hear my sound?
Yes, we can hear you and we can see your screen, but please make your presentation full screen with Ctrl L.
Sorry, I couldn't get.
Can you press Ctrl L?
Control
L.
L. Okay. For what?
For making full screen.
Full screen.
Görünüm. Thank you very much. Now we are listening to you.
Okay, thank you so much. Hi there, participants. My name is Osman. I am an assistant professor doctor in Bilecik University. We are working on a scientific research project supported by TÜBİTAK, and this presentation was made by the authors you see on the page. These are my collaborators. In this work, we study approximation properties of sampling Meyer operators for functions belonging to weighted spaces of continuous functions. We get pointwise and uniform convergence results of the family of operators and determine the rate of convergence via weighted modulus of continuity. We also studied a quantitative Voronozh-Kaya theorem to obtain rate of pointwise convergence. In the last part, we give an example by using some specific kernels which satisfy the theorems obtained. Generalized sampling series was first constructed by Butzer and his school in the late 1970s in order to reconstruct a function f with its sample values at some discrete points. It is defined by the equation labeled 1, as you see. Here f is a function from R to R for which the series is convergent for every x, and chi is called kernel, satisfying some suitable conditions. After that, Bardaro et al. Introduced the L1 version of generalized sampling operators in cited 5. They also define Meyer modification to approximate functions belonging to LP spaces by replacing the integral means by a general convolution as in the form you see in the middle of the page. In Meyer modifications, the kernels don't need to be same. In the previous page, you see the same kernels called Varphi in the series and in the integral. But as I said to you before, the kernels don't need to be the same. In the recent paper, which is cited in 16, Costarelli et al. Have constructed a generalized sampling Meyer operators in this frame. As here, the kernel functions Varphi and PC satisfy some suitable conditions. So let me talk about some preliminaries. In generalized sampling series for functions having continuity property, sorry, I skipped a page. Yes, this page. There are some things that I want to talk about this page. In generalized sampling series for functions having continuity property, generally the space C to 0 R has been considered. To eliminate the boundedness of the corresponding function, in a recent research paper, the authors considered weighted spaces of functions, although the family of generalized sampling Meyer operators is defined for functions LP space. It is also meaningful for functions, for continuous functions as well. So this time we can talk about the preliminaries. Let me give you some basic notion and definitions about the study. Let's denote L21 the space of all Lebesgue integrable functions, and by C0 the space of all uniformly continuous functions. Let's consider two functions which is called kernels, Varphi and PC, such that satisfying the conditions which is labeled 1, and then we give the definition sorry, we give the definition, the algebraic moments and the absolute moments of these kernel functions, as you see on the page. And we have a remark. As a result of the assumptions of the sampling Meyer operators, we obtain the first result. The operator take 1 to 1, where here 1 denotes the identity function. In the second item, we obtain a result of absolute moment of Varphi kernel and also PC kernel. Now, it's time to talk about the weight function. A function rho is called a weight function if it is positive continuous on the entire real axis R. In this study, we consider the weight function as rho x equals to 1 to 1 plus x squared. Here we give some specific notation about function spaces. As you see, B rho R, the space of all real functions whose product with the weight functions rho on R is bounded, denoted by B rho, and some other subspaces of it. We can easily see that B rho R and the subspaces of it are norm space with the norm of F according to rho. Here we also give the definition of the weighted modulus of continuity for functions F, which are element of C rho. The subspace of B rho is denoted by omega, big omega, and given in the equation labeled 3. In this lemma, we recall some properties of weighted modulus of continuity. Let delta is bigger than 0 and x is element of R. Then we get these 3 results. In the first item, omega is a monotonically increasing function. In the second one, omega goes to 0 as delta goes to 0 for functions f, which is an element of C rho. And in the last item, for each lambda is bigger than 0 and f, we have this inequality. On the other hand, quantity of absolute value of y minus x with respect to delta directs us to a piecewise function, piecewise inequality, sorry. So we get the main results. Here is a proposition which helps us to obtain the next main theorem, where Varphi and PC, the kernels with alpha equals to beta and equals to 2, and rho is the weight function here. It is a spatial inequality, but it's very useful for us. It is a nice proof process by using the definition of sampling Durkheim operator and the definition of algebraic moment and absolute moment of the kernels and some other basic algebraic operations. We can get the result. In this theorem, we show that our operator is a linear operator from B row to B row. We omit the proof details here. And this is the theorem about the pointwise and uniform convergence of the operator, which is one of the main theorems of the paper, of the study. And the proof pages, because I don't have enough time, I am skipping these pages. Here another theorem, and this theorem gives us an upper bound between the difference of operator and the function of f, and we again the details of the proof. We get a remark. By using Taylor expansion of a function f, such as in the equation 8, and the error term function, together with modulus continuity, we can obtain a new inequality form given in labeled 9, as you see in the bottom of the page. Now we can state the Voronovskaya theorem. Let Varpy and PC be the kernels with alpha and beta equals to 3, and then we have this result. We omit the details of the proof. In the last part, we get here, I give you an example which satisfy the results given in the theorems. Firstly, let's give the definition of the central B spline. It's a spatial kernel function of order 3. Here you see the definition, which is labeled 10. If we write more explicitly of the form of this kernel, we can get this piecewise form, which is on the top of the page, as you see, and you also the graphic of this kernel. We can easily understand it satisfies the assumptions which is given in the theorems. For example, the sum of the series equals to 0. We can calculate this calculation using MATLAB software. So let's go on. Here we take another kernel function by taking characteristic function, which is defined on the closed interval 0, 1, and as a result of choosing these spatial kernels, we get Durkheim sampling type series becomes like this. So now this is time to choose a function. We choose a weight function. Here we define fx equals to 1 to 1 plus x minus 2 square. Then in the operator, as you see, we have some constant, as you see, omega. We take these omega values 5, 15, and 45, and see the results according to these omega values. What will be the graphical approximation results? In the next page, you will see the results. between the operator and the function we choose. If we take omega equals to 5, the result is here. If we take omega equals to 15, the result is here. And if we take omega is 45, the result is like this. So these are my references which we used. Thanks for watching.
Thank you very much, Professor Osman Alagöz. I would like to give my thanks for your valuable talk. Now let me ask the panelists and attendees about the questions and any comments. And now I'm seeing a question. We have a question. It says that, why do you have -2 in the denominator of the weighted function?
Why do we have -2 in denominator of the weighted function? It satisfies the condition. There is no any reason not to choose this function. I don't get exactly the question. Why?
If the attendee wants explain one more time his or her question, we can wait a little bit. And also, let me ask my question one more time. Is there any comment or question, another question for Professor Osman Alagöz? Or this anonymous attendee, is this anonymous attendee satisfied from this answer? We have one more explanation from the same attendee. Can you see the question? Let me read. Usually we have 1 plus x squared. In this case, you have -2. How do you choose your weighted function?
Yeah, we don't have to choose every time 1 plus x squared. We can take any row function instead of x. So here we take x minus 2 instead of x to make a different result. And also we are working on some other different weighted function graphical results, but it didn't finish yet, so I couldn't add the presentation. So we are still working on it, and when we finish it, we are planning to submit this paper, and maybe if we have a chance to publish it, we can prove the details more and more.
Okay, thank you. Also, the anonymous attendee says thank you. We are also recommended to follow your researchers and academic publishing after today. So I think there is no any question. I would to say thank you one more time to you for this nice presentation, Professor Osman Alagöz. Also, we want to give our thanks on behalf of our organizing committee for this nice contribution. Now we can continue with our next speaker as scheduled in our program. I can stop this screen. So now let me announce our new speaker. It is Anıl Çolpan Zenginoğlu from the Maryland, United States of America. Now we can ready to listen his presentation entitled by Hyperboloidal Compactification for Wave Propagation. Before giving the microphone to the Professor Anil, I want to give my all thanks to him because we are very glad to listen him here. And he was able to arrange his schedule because there is some difficulties in the American local time. Again, I want to say thank you him. So, can you hear me?
Yes, I can. Can you hear me?
Yes, we can also hear you.
All
So
right.
if you are ready, we are ready also listening you.
Okay, thank you. Yes, it's 4 a.m. here. I just woke up. Thank you very much for having me. Actually, this is the first time. I'm from Turkey. I grew up in Istanbul. I'm a research scientist at the University of Maryland. This is the first time I'm giving a scientific talk in Turkey. Thanks, COVID, I guess.
Thank you so much. Sorry for interruption. Can you make a full screen your presentation?
I think it should be full screen. No?
No. Can you try Control L or try the tools?
So now it's not full screen?
No, we can see the Adobe
Yes,
export.
now, and then now it should be.
Yes, yes.
You see it full screen?
No, unfortunately.
Interesting.
Maybe
Then
you are sharing your screen only PDF because of this.
let me see why that happens. Let me then use a different program instead of this one.
Okay, you can try.
Work. So not allow me to share at this point. Let's try it again. So, do you see full screen now?
Yes, now we are perfect for the syncing.
Great. I'm just going to try to use the spotlight. I hope the spotlight is working.
Yes, it's working.
Okay, great.
Yes, please.
Okay, so the talk is titled Hyperboloidal Compactification for Wave Propagation. As this is a meeting about the studies on scientific developments in geometry, algebra, and applied mathematics, I thought I structure the talk based on these topics. So here's the talk outline. I will first describe the problem. The specific problem I'm solving is related to the wave propagation. It comes from applied mathematics, but the solution comes from geometry. So it's a geometric construction that comes from relativity. My background is numerical relativity. And then that geometric construction applied to the wave propagation problem solves what we call the outer boundary problem. And this is the structure of the talk. So the problem is numerically computing waves. My background is relativity. Again, we calculate gravitational waves from black holes, but waves are everywhere. Sight is essentially waves. Hearing is acoustic waves. In this case, I'm giving two examples. One of them is the Maxwell Equations, where you solve for electromagnetic waves scattered from the surface of an airplane to see the radar cross-section, how the airplane is visible in the radar. Another example is earthquakes, the waves that propagate on the Earth. This is from a 94 earthquake near Los Angeles, Northridge earthquake. And here actually you can see really what you do when you calculate these things numerically. You put them into a box. So these are the box boundaries. And the challenge then is, what do you do at the box boundaries? Because these waves propagate, and wave equation problems usually are posed on unbounded domains, on an infinite domain. But then when you numerically calculate them, you put them in a box, and at the box boundary, you have to make sure that the propagating waves are not hindered by these artificial boundaries, because they are not part of the physical problem. This brings us to the outer boundary problem. We want that the truncated solution approximates the original solution without the artificial boundary. Now, this implies that your boundary conditions must be well posed so that you have a well posed initial boundary value problem. the data that you provide must be transparent to the interior solution. So when the wave is propagating and hitting the boundary, the data must be such that it makes the boundary invisible or transparent. And then the numerical implementation has to be stable, accurate, and efficient. Each of them is actually a difficult and challenging problem, and there has been multiple papers written on this. And they all arise from the fact that you somehow truncate the original solution domain by some artificial outer boundary. This is particularly challenging for wave equations, meaning hyperbolic partial differential equations, because the solutions are oscillating. So if you wanted to calculate the solution on the infinite domain, well, there are infinitely many oscillations on that infinite domain. So that's very challenging. The other problem is they decay very slowly. So the propagation of radiation towards infinity in 3 dimensions is 1/r. The famous fall off of radiative fields is 1/r, and that's very slow. You cannot just truncate the domain, say it vanishes here, and then you'll be fine. That's not the case. So you really have to be careful what you do at those boundaries. This has been an important problem for many decades. There are some famous works by Enquist and Majda in 1977. It's very old. One of the most popular ones is Berenger's perfectly matched layers. But anyway, any of these solutions are sort of, they work quite well, but it's still an open problem because none of the solutions are local and exact. All of them are either approximate or they are global, but not exact. And here comes the solution. And the solution comes from geometry, and in particular, the geometry of space-time. You see, what you do when you compactify, you only compactify in the spatial directions. So when you map infinity to a finite domain, compactification, typically in applied mathematics, people just do it along space. But that's actually inappropriate. It's better, and I will argue in this talk that it's better, to do it along the null direction or along the hyperboloidal direction. So what do I mean by hyperboloidal? So I'm going to just take a hyperboloid. So this is the equation that defines an hyperboloid. You can see it as x squared minus y squared, some constant value. Here I'm using T and R for the TR plane, the space and time. So T is the time direction, R is the space direction, and this is a hyperbola. And as you can see, this is the unit hyperbola, and it acts as a pseudosphere of the Minkowski metric. This is the set of the points that have unit distance to the origin in terms of the Minkowski distance. So unit space-time distance to the origin. In that sense, the hyperboloid is actually a very fundamental object, and it's been known to Minkowski, in his 1908 talk. He has the hyperbola as the kinematic space of special relativity. It's a very fundamental object, similar to a sphere, which is at unit distance, unit Euclidean distance from an origin. Here we have a unit Minkowski distance from an origin. So it's a pseudosphere of the Minkowski metric. And it asymptotes to the null cone. So this T minus R equals 0, that's these blue dashed lines represent the surface, the light cone surface, the outgoing propagating light cone surface. When you send a wave from the origin, pulse, let's say an earthquake, and that's the epicenter of the earthquake, the propagation goes along the characteristics. In this case, the characteristics describe the null cone, and that's T equals R. And this hyperboloid asymptotically approaches those propagating waves. Whereas when you do T equals constant foliations, they actually move away from the propagating wave. They go to the wrong direction. And that's the problem. So when you have the hyperboloid, you can write the spatial metric on the hyperboloids. Here, this is a 2-dimensional plot. Of course, you have to imagine it as a 3-dimensional space. And the spatial metric of this is the unit hyperbolic metric. And the difference, again, the similarity to the sphere and the naturalness of the construction is very visible here. With the sphere, you have a sine function, trigonometric functions. With the hyperboloid, you have a hyperbolic sine function. So that's the main difference. But it has a big impact on the geometry and a big impact on your numerical code when you do this along the hyperboloids. So what you then do is you take one of these hyperboloids, this one, and then you shift it in T. So you shift it along the time direction by some value. So let's say it's tau. These are the shifted hyperboloids, and these provide a foliation of space-time. Just like before, we were using t. Instead of t, now we're using tau. So instead of the standard, what we call them Cauchy surfaces that go to infinity only in the space-like direction, this is going infinity towards the null direction, and that's called null infinity. So you shift them by tau, you define the tau as your new coordinate, and then you write your metric, the Minkowski metric, in terms of this new coordinate, which makes your spatial slices exactly the slices of the hyperboloid. So it's hyperbolic geometry on your spatial slices. And now once you have hyperbolic geometry, you can compactify. So now we map the infinite domain in Xi or the infinite domain in R, where R goes from 0 to infinity, to a rho where rho goes from 0 to 1. And then you get the Poincaré disk. Some of you will recognize this woodcut by Escher. This is the circle limit for heaven and hell. It's a finite disk, but it represents an infinite space, and infinity is at the boundary rho equals 1. And as you can see, the metric here at rho equals 1 blows up. That means the distances become infinitely large at the outer boundary. This goes back to actually Penrose's construction. The Penrose diagrams, they represent the infinity of space-time. You see, we recognize that with the null cone, it's not just infinity in spatial directions or infinity in time-like directions. We have also infinity in null directions. And the topology of that infinity is like a cylinder. You see the disks are like Poincaré cuts, hyperbolic metrics along the cuts. And then in the time direction, you have the regular time direction. But the cylinder is a special kind of cylinder that in applied mathematics is usually unknown. Applied mathematics treats t time still in Newtonian fashion. But what I'm arguing here is that it should be treated in a Minkowskian fashion, in a space-time. So I'm just going to go through. So this was the geometry part. The applied math part is just applying this idea to a wave propagation problem. And for simplicity, I'm taking here the Helmholtz equation. Here you see the unknown, the second radial derivative of the unknown plus some wave number equals 0. It's the standard Helmholtz equation on a domain, again, on an unbounded domain that goes to infinity. The Helmholtz equation doesn't have unique solutions. You have to impose the Sommerfeld radiation condition to ensure uniqueness. And then when you here do this compactification, just map R to some rho, which is finite, you see that the equation is singular. In particular, the wave number becomes infinite towards the boundary. That means you get infinitely many oscillations. So that's the original compactification problem. And then you cannot compactify. You just relabeled your points. You cannot add the point of infinity because it's singular. But if you do the hyperboloidal compactification, I'm not going to go through the derivation of this, but it just becomes a rescaling with a singular factor that comes from this lifting up of the time slices. And the farther you go, the more you lift them up. Essentially at infinity, you lift them up at an infinite value. So a singular transformation leads to a regular equation. It's just degenerate at the principal part. And then when you evaluate it at infinity, you see something like a Sommerfeld radiation condition pop up. So that's an important difference. You do not impose the condition, it just comes out. You know, that has to do with the arrow of time, actually. It's a very interesting aspect of this, but I'm not going to go through that now. I just wanted to demonstrate, because, you know, I'm sure nobody's following the derivation here, just demonstrate this on a simple example, and that's the example of a plane wave in frequency domain. So what you see here is a plane wave, many oscillations on a domain from 0 to 5. Imagine on an infinite domain, of course, you have infinitely many oscillations. And if you map them now from R to rho to a finite domain, you still have infinitely many oscillations. So you haven't solved the problem. You just translated an infinite domain problem to an infinite resolution problem near the boundary, because you cannot even resolve these infinitely many oscillations to plot, let alone to calculate numerically. So what you get is some sort of a singular function as a solution at the outer boundary. But the hyperboloidal rescaling, the compactification with the hyperboloidal time transformation, leads to this rescaling, which removes the singular part And then you have a smooth function. A smooth function that doesn't oscillate much, that you can resolve easily with your numerical methods. And you don't have an outer boundary anymore, because the outer boundary actually is at infinity. And you don't have to, if you look at the equation, because the principal part is degenerate, there are no boundary conditions to be applied, and you have your whole domain solution on your numerical grid. So just to conclude, this leads to a local and exact method. Local because it's local in rho, even though it's infinite in R. And it's exact because there are no reflections from the outer boundary, because actually the outer boundary is at infinity. The method is geometric method. Again, this comes back to the geometry idea. So it's not dependent on any discretization. In your code becomes simpler because you don't have boundary conditions, you don't have boundary data. And all of these advantages, in addition to that, you get the unbounded domain solution. So if you're interested in echo area, in acoustics, radar cross-section, in electromagnetism, or gravitational waveforms, gravitational flux, in general relativity, all of those things are defined mathematically at infinity, and you get that directly. You can also adapt this to high-frequency wave propagation. You see here, this transformation can be modified such that there are less waves on the domain, which means your numerical code will be more efficient, because typically your efficiency is measured by, you need a certain number of points to resolve each wave. So if you have fewer waves, it's much easier to have a numerically accurate computation. And it also handles non-compact sources. Actually next week we'll have a paper about this, nonlinear forcing, variable coefficients. So it's very general. The two disadvantages you could say is not as simple as the Helmholtz equation. I don't consider this as much of a disadvantage. If you have seen any of the boundary treatments, they are fairly complicated. So you get rid of the boundary treatment, but your equation looks a little bit longer. I think that's okay. The main restriction is that it only works with smooth boundaries so far. There might be a way to do it with Cartesian coordinates, but currently we cannot handle corners with this method. That goes back to the fact that the topology of null infinity, again, is a cylinder as shown in that Penrose diagram from 1965. Anyway, so that's it. Thank you very much. And that's the end of my talk.
Thank you very much, Professor Anil. We are very glad to see your presentation now. Let me ask, is there any question or comments for our presenter? You can ask your question from the Q&A window by writing your question.
My dream is that this method is applied to some real-world problems. It's applied in gravitational waves and black hole calculations. But if any of you has some wave equation problems with boundaries, I will be interested to look into it.
I think there is no question. Let me say something. Actually, I'm working about the just a little bit partial differential equation and the applied mathematics area. I'm very happy to take a chance to see your presentation. It was very interesting and well-designed presentation. I would like to thank you again. And also, I want to thank you one more time for your participation because of the some time difference conditions. I think now you are 4 a.m. According to your local time.
Right.
So we are very happy to see you here. I kindly recommend all the participants who are listening now or listening asynchronously after this webinar, please contact with the Anıl Hocam for your questions, and you can reach his studies from the internet. So thank you
for
again.
having me. I appreciate it. Thanks.
Thank you very much. Okay.
Bye-bye.
And now let us turn to our program and continue as scheduled. Now we have the next speaker, Neslihan Nesliye Pelen from the Samsun, Turkey, with the presentation entitled by Vector-Borne Disinformation During Disasters and Emergencies.
Thank you.
Hello.
Hello. Can you see the page?
Yes, now we can see your presentation. Can you make a full screen your?
I try now.
From görünüm. Yes.
Now it's okay.
Yes. Yes. Now we are ready to listen you.
Thank you very much. In this talk, I will give you some information about the vector-borne disinformation during disasters and emergencies. First of all, I will make a small introduction about that topic, and we will try to design a system to explain this explain the vector-borne disinformation. Then we will try to make the mathematical analysis of that system, and at the end I try to share my numerical results with you. First of all, the vector-borne disinformation model is a type of rumor model. Therefore, I very briefly want to talk about SIR models, because SIR models are the initial point of these kind of systems. SIR models is the first epidemiological model that describes the relation between the compartments, susceptibles, infected, and removes. These models was first mentioned by Kermack and McKendrick in 1927, and now many epidemiological models are studied today. These studies mainly inspired from that model. After a while, Daly and Kendi realized there is a similar transmission between rumor and transmission of rumor and transmission of the illnesses. Therefore, they design another model which is very similar with the SIR models, and their model's name is the ISS model, which is also a compartmental model, and the compartments in that model are the ignorance spreader and stiflers. After their research, again, many researchers start to make studies on rumor models. In the literature, you can find many examples of that models. And in that study, what we are doing is mainly settle the relation between vector-borne diseases and the vector-borne disinformation. Here in our study, the social media behaves like a vector while rumor is spreading in our system. And therefore, we adopted our rumor model on vector-borne diseases. Very briefly, what are vector-borne diseases? Vector-borne diseases are the diseases that are caused by parasites, viruses, or bacteria that are transmitted by a vector, such as mosquitoes, ticks, flies, tritium bugs, so on and so forth. Also, researchers indicate that the vector-borne diseases spread to non-endemic regions because of the globalization and climate change. And this phenomenon is not very different for the vector-borne disinformation models because of the social networking elements. And also, while designing our model, we assume that each short message or video distributed by social media users are denoted as a bite of a mosquito. And therefore, an infectious vector causes consciously disinformation or unconsciously misinformation, and this causes an outbreak of info pollution locally or globally. Now, we come to the mathematical modeling of vector-borne disinformation model. For that reason, firstly, we assume that there is a wrong information about the COVID-19 pandemics that is available on these social media elements. And this wrong information is transmitted by the vectors. In other words, here the vectors are the messages. They are transmitted with the social media elements. These messages are transmitted with the social media elements. And here we define two types of populations. First one is the human population, and second one is the vector population. Human population is divided into 4 compartments, and vector population is divided into 3 compartments. The compartments in human population are the compartment of S. This contains the people, this is the susceptible population, and this contains the people who are not aware of the wrong information. The other compartment is the E compartment. It is the exposed population, and it includes the people that are received message, wrong message, but they still doesn't transmit it yet. The compartment I, it is included the infectious population, and the individuals in that compartment spreads the wrong information directly or via social media. And the last compartment in the human population is the compartment of R. This contains the people recovered. This is a recovered population, and this contains the people who forgot the wrong information and they are available to be infected again. When we come to the vector population, this is denoted with NV, and it is includes 3 compartments: SV, EV, and IV. The SV compartment is the susceptible vector population, and it denotes all the information sources in the social media at time t. The second compartment, EV compartment, is the exposed vector population, and it includes all the loaded wrong informations in the social media elements, but these messages does not transmit it yet. And the last compartment is the IV compartment. It includes the infectious vector population, and these messages spreaded wrong information in these social media networks. And while settle the system, we ignore the direct transmission between humans for that system. And now, after talking about the compartments, it's important to understand the relation between the compartments to obtain the system. Very briefly, I want to talk about these relations. First of all, a social media user in the compartment S attacked by an infectious vector IV. What does it mean? It means that any people in the compartment of S, any person in the compartment of S receives the wrong information, and then he or she take this wrong information, but there is but he or she doesn't decide to transmit it yet. Therefore, he or she is in the compartment of E, and a similar mechanism is also true for the vector population part. Therefore, a person or a device in the non-infectious phase has the information, but still it is not shared yet. And also, some conscious individuals do not prefer to share an unconfirmed information who are directly transferred to the compartment of R. And also, we assume constant recruitment and death rates for the human population and vector elements. Also, because of the high number of people and high number of vectors, we use saturation elements, saturation points, and we also include these terms into our system. Let's talk about the follow chart of that system. Here you can see the attraction between the IV compartment and SV compartment. After that initiation, you can see here the follow up to the compartment of R. And also, we have said that some conscious people who are not decide not to share the unconfirmed informations, they go to immediately from the compartment of E to R with a rate of theta. Also, we have said that some people starts to forget what they have taken before, and therefore there you can see a follow from the compartment of R to S because of that reason with the rate of gamma. Also, there is another interaction between the compartment of I and S. After that initiation, you can see also the follow from EV and IV, and also we have said that that rate of humans, which is denoted with mu v for each compartment in the human population, and you can see here the deceleration rate of the vectors with the rate of mu v for each vector compartments, vector population compartments. Here, according to that follow chart, we obtain system 1. Here, system 1 is the model that explains the vector-borne least information, and we combine this system with the initial conditions that you see in 2. First of all, we try to explain the existence, show the existence and uniqueness of system 1, and to show that one, we define the following iterative sequence in 3, and this first lemma says us the solution of system 3 with the corresponding initial conditions in 2. Each term of the sequence is bounded from above and below with non-negative constants. It has a very simple proof. This proof is mainly based on mathematical induction, and since we take our initial conditions non-negative, automatically when we take m is equal to 0, all the conditions or the necessary how can I say that what we want is obtained when m is equal to 0. When we take m is equal to 1, or we come to the initial step by using these conditions on the initial conditions and the other parameters, we obtain for the last subinequality of system 3, this last subinequality of system 3, we obtain this result. Making the necessary calculations, we immediately see that IV1 is less than or equal to that term, but bigger than or equal to 0. Very similarly, when we do the similar things for the other sub-equations, we obtain that when m is equal to 1, the compartments are bounded from above and below with non-negative constants. And when we come to the induction step, we assume that these compartments, when we take m is equal to m, they are bounded from above and below with non-negative constants. And applying these similar calculations to that induction step, we obtain that all the compartments of system 3 is bounded from above and below with non-negative constants when m is equal to m plus 1, and this gives us the desired result. I will use one fixed point theorem to show the existence and uniqueness of the system 1. Therefore, I want to very briefly remind you that theorem. And theorem 2 says us the solution of system 1 with given initial conditions in 2 is exist and unique. How we prove this existence and uniqueness? To prove the existence of uniqueness for system 1, we should have to show that system 3 is a Cauchy sequence. For this reason, we should have to use maximum norm, and we take the difference of m plus 1 and m terms, and after using the Gromov inequality and lemma 1 I have just mentioned above, by using these tools, we get the desired results. very briefly, I want to explain this one. We take this difference using Gromov inequality, obtain, after using maximum norm, we obtain inequality 4. Very similarly, we obtain 5, 6, 7, 8, 9, 10. We add up all of these and take that inequality. In that inequality, the D1, D2, D3, D4, 5, 6, and 7 are defined as like that. By choosing T small enough and AI less than 1/3, we and using Banach fixed point theorem, we can obtain that system tree is a Cauchy sequence. And since the convergence of the sequence of system 1 is obtained as a result that system tree is a Cauchy sequence, we get a
I think there is some connection problems with Neslihan Hoca. Let me wait a little bit for connecting again.
can you hear me?
Yes, we can hear you.
I'm very sorry. My charge is off. I'm very sorry. I didn't realize that.
Okay.
I can continue if
yes,
it's okay.
If you are ready, you can continue, but you have only 4 minutes to finish your presentation.
Okay, I will finish. I will finish.
Okay.
Just a minute. And in that theorem, we obtain the non-negativity of the solutions. It's not full screen.
No. You are not sharing your screen now.
Oh, I'm sorry. Just a minute. I think now it's full screen. Sorry, not full screen. It's okay now?
Yes, now it's okay. You can please.
Yeah. In that theorem, we can show the boundedness of the parameters here. I very briefly want to talk about the disinformation-free equilibrium point. Disinformation-free equilibrium point is that point here. By using the Van den Driesch method, the next generation matrix method, we obtain the basic reproduction number R0. For that reason, we define such a vector and curly f and curly v vectors. Here f represents the inflow of the new infections and we denote the outflow from the infectious compartments. You see here the Jacobian matrices of curly f and curly v. By after obtaining its Jacobian matrices, we obtain the next generation matrix, which is f v minus 1. And since the basic reproduction number is the spectral radius of the next generation matrix, we obtain R0 as that one. Here, theorem 5 says us if these two conditions are satisfied, then the equilibrium x star, or disinformation-free equilibrium point, is globally asymptotically stable. To obtain this result, we use the Lyapunov stability theorem and LaSalle invariance principle. After using these ones, we obtain the global stability of this free equilibrium point. And when we come to this information equilibrium point, after the necessary calculations, we obtain x star star as this way. Here we define PC and RV as that way, and PC is bigger than 0 because of that reason. With a small calculations, you can obtain these results immediately. And also for the sensitivity analysis, we calculate the sensitivity index of R0 according to the parameters in the R0, and therefore, according to these, we obtain these index formulas here. Before the numerical simulations, I just very briefly show you the parameters and their estimated values. These are obtained from several articles, several studies. And here you can see our numerical simulations. These numerical simulations are done according to the change in theta and beta. What is beta? Beta is the transmission rate, and theta is the rate of choosing not to spread an untrusted information. Here you see, although R0 is less than 1, there is not gone to this is free equilibrium point for the number of whisperers or eyes, because this one does not satisfy the conditions of theorem 5 I just talk about now. But when you take beta as 10 over minus 7, you see gone to the equilibrium free, this information free equilibrium point, because it satisfies the conditions of system 5. And very similarly, when theta is changed, you obtain these results. And here the sign of indices, and these are my references. Thank you to listen to me, and sorry for the how can I say, sorry for my
technical problems. Yeah. Okay, no problem. Thank you very much for your valuable contribution to our webinar. It was a very nice presentation.
Thank you.
Sometimes there will be some technical problems like that.
But disconnection.
Yes.
For disconnection, I'm very sorry.
It is the normal for the webinar sessions. So I cannot see any question for you. So let me, yes, okay. I would like to thank you again. So close your screen. Now we are finishing our first session. I would like to thank all of participants for this session. Now we will continue our invited speaker talk with Tahir Coşkun as a moderator. So now we have a 5 minutes break. After this break, we can continue from here. See you soon.
Hello, everyone. Good morning and good afternoon. Ladies and gentlemen, now we are waiting for the talk of Professor Dr. Volkan Rehman. As I see, he is not in the event yet. Let me check once more. Although we have contacted him a couple of hours ago, and we checked the time of his call. I couldn't see his name in the list of attendees at the moment. Let's wait a couple of minutes. We can wait 5 minutes. Murat Bey, please, you can start the timer.
So, hi, just a quick question.
Yes, Professor.
Yeah, so if the professor doesn't appear, is it possible to move on to the next presenter, or we should wait?
Actually, no, Professor, because the local organizing committee is keen to preserve the scheduled times in the program.
Okay, that makes sense. Sorry for that.
Yeah, thank you. Thank you,
Okay,
Professor.
thanks.
Then let's give a 5 minutes break.
Of course.
Murat Bey.
Thanks for the information.
Thank you, Doctor. Hello everyone. Volker Möhman, the professor, seems not to be here at the current time. We are so sorry for this unwanted, unsuitable situation for all of you. Now we will give a break and we will continue with Manoj Kumar Patel's talk at the next session, and the talk will begin at the scheduled time. Therefore, we will give approximately 1 hour break. Thank you a lot.
Good afternoon, everyone. Welcome to this session. I am Figen Takıl Mutlu. I will moderate this session. Now, I kindly invite Professor Manoj Kumar Patel from India to the presentation. Professor Manoj Kumar Patel, you are welcome to do your presentation, please.
Yeah, thank you very much. Am I audible?
Yes.
Yeah, okay. Now let us start to share my screen here. Yeah, is it visualized?
Yes. Could you please share your screen in full screen?
Yeah, this is full.
Okay.
Okay. So first of all, I would like to thank to the organizer for providing me the opportunity to talk about the characterization of Phi semi-injective module in the webinar studied on scientific development in geometry, algebra, and applied mathematics. So motivation of this work comes from 1995 when Nicholson and Yusuf studied the structure of principally injective ring as if every homomorphism from a principal right ideal to R is a left multiplication by an element of R. After that, in 1999, San and his collaborator extend this notion to module and generalize the idea of principal injectivity to M principal injectivity of a given right R modulium, any modulium. So here, before come to the these are outlines. Here we have to consider definition and examples of the Phi semi-injective modules. And next section is characterization and properties. And after that is references. So here before going to define the Phi semi-injective module, it needs some basic notion like M cyclic submodule. Here injectivity is defined is map is extended from the submodules of M. Now in that case, in Phi semi-injective module, our map is extended, means any map from M cyclic submodule extended from M to M. So for defining what is the M cyclic submodule, a submodule N of M is called M cyclic if it is homomorphic image of some endomorphism of M. Or we can say equivalently, it is isomorphic to M modulo L for some submodule L of M. For example, we can consider every submodule of Z is the Z cyclic submodule. And also we can consider every direct summand of a module M is M cyclic submodule. Also, we can use the terms fully invariant. So a submodule K of M is called fully invariant if it is invariant under all the endomorphism of M. So for example, 0 and M is the trivial example of the fully invariant submodules of any module M. And some distinguished example of the fully invariant submodule is like Sokal. Sokal of M is defined like sum of all the simple submodule of M. And next one is the radical is defined like intersection of all the maximal submodule of M. And next one is the torsion submodule is defined as collection of all the element of M which is annihilated by some positive integer M. And next one is considered the singular submodule is the collection of all those elements of M whose annihilator is a essential ideal of R, or we can consider is an essential submodule of R over itself. So here we look in the diagram here. First, we have to define the M principally injective. So here SEM is considered as a fully M cyclic submodule of M only. So if any homomorphism from this SEM to N can be extended from M to N, then N is called M principally injective. So here if n is replaced by m itself, then any homomorphism from m cyclic submodule to m can be extended from m to m such that this diagram is commutes. We get G composition I is same as F. Then we have to say M is semi-injective module. So the module where we are interested is needs only fully invariant M cyclic submodule, which extends the notion of M principally injective and F semi-injective module to the Fi M principally injective and Fi semi-injective module. So here, now in this definition, we have to consider SM as a fully invariant M cyclic submodule of this module M. And here I is the inclusion map. So if every homomorphism F from this fully invariant M cyclic submodule SM to N can be extended to homomorphism G from M to N such that this diagram is commutative, G composition I is F, then we have to say N is Fi M principally injective. And if N can be replaced by M, then we call M as a Fi semi-injective module. And any ring R is called Fi self-principally injective if R over R is Fi R principally injective. So there are many examples. Every simple module, semi-simple module, quasi-injective module, semi-injective modules, and Fi semi-principally injective rings, and they are direct summand. All are Fi semi-injective modules. And next example here, we have to consider Z be the ring of integer, and N is Z4, which is denoted Z modulo 4Z, and M is considered Z6, is denoted Z by 6Z. Easily we verify N and M are the Z module, and we can say, we can check easily here, N is Fi M principally injective and M is Fi N principally injective, but Z is not Z principally injective modules over Z. Now, next example, here we have to consider, let R be the ring of upper triangular matrix like this here over the field F, and sorry, and M module is considered as the first row is non-zero and other row is 0 with the element of F field, and NR is here right corner down element only. So easily verify NR is Fi M principally injective, but not M injective module, because here M cyclic submodule is 0 and M itself. But in case of submodule, there are one F is also a submodule, forms a submodule, but map from here to N cannot be extended to M to F. Okay, so now we come to the first result, which contains our basic results of the Fi semi-injective module. If M cyclic submodule N of a module M is Fi M principally injective, then N is a direct summand of M. That is, we can say here every short exact sequence from 0 to N to M to M1 is splits. And next result, we can say next part is every direct summand of Fi semi-injective module is Fi semi-injective. That is, we can say here Fi semi-injective module is closed under the direct summand. And this is also, this structure is closed under the finite direct sum and finite direct summand. And next part here, if finite direct sum of Mi modules is Fi semi-injective, then Mi is Fi Mj relatively principally injective. And next part, we can say every injective endomorphism of uniserial Fi semi-injective module is an automorphism. We can say uniserial Fi semi-injective module is co-Hopfian, where co-Hopfian is defined like every injective endomorphism is an isomorphism, just like, for example, Artinian rings. Artinian rings are module. These are forms of co-Hopfian modules. And next property is considered as a definition. If N is Fi M principally injective, if and only if the composition of homomorphism Mn to G, where G is the endomorphism of M, is exactly same as collection of all the homomorphism from Mn such that kernel of G is contained inside the kernel of F. So this is the definition of the EFIM principally injective. This can be extended on EFI semi-injective module as a definition. So we construct a corollary here. Let M be a EFI semi-injective module and FG are the endomorphism, some endomorphism of M. Then F in belongs to SG, means belongs to the SG if and only if kernel G contained inside the kernel F. Now next result is consider M and N is a right arm module where M is the duo, then M is N projective and every submodule of N is FIM principally injective. If and only if N is FIM principally injective and every fully invariant M cyclic submodule of M is N projective. So now for next we have to define the PP ring, where it is defined like if each principal right ideal is projective, then we call ring R is PP ring. So our next result characterize the projective modules in terms of the EFI semi-injective, EFIM principally injective. So the following statements are equivalent for a projective module M. Every homomorphic image of any FIM principally injective module is FIM principally injective. If and only if every homomorphic image of any M injective module is FIM principally injective. If and only if every homomorphic image of any injective R module is FIM principally injective. And if and only if every fully invariant M cyclic submodule of M is projective. So this is the things, and the next result is obtained by the remarks here. We have just stated above, if every fully invariant M cyclic submodule of a module M is, if every fully invariant M cyclic submodule of M is a direct summand of M, then M is FI semi-injective. So hence we make a remark, if the endomorphism ring S of any module M is one Newman regular, then M would be FI semi-injective module. So with the help of these remarks, we construct a statement here. If S is the one Newman regular ring, then every fully invariant M cyclic submodule of M is FIM principally injective. This is the first part, but converse of first part is not necessarily true. So this is holds for the direct projective module. So direct projective module can be defined any epimorphism from M to the direct summand of M is splits. That is kernel of F is a direct summand of M. So we can state the converse part of first result is here is hidden. So I am speaking here. So if M is direct projective and every fully invariant M cyclic submodule of M is FIM principally injective, then S is one Newman regular. That's all. So now we have to state here, characterize the commutative semi-simple ring. The commutativity used in only proof in the proof of 2 implies 3. So the following statements are equivalent for a commutative ring R. The direct sum of any two EFI semi-injective module is EFI semi-injective. If and only if every EFI semi-injective module is injective, if and only if R is semi-simple Artinian. So commutativity used in only proving in the second implies third, not in all. So now next result is the equivalent statement. The following statements are equivalent for a quasi-projective EFI semi-injective module. Here S is the endomorphism of M. So image of S is EFIM principally injective. If and only if image of S is a direct summand of M. If and only if image of S is M projective. So 1 implies 2 is obtained from our first result. And here these are the have some little work of proving. So next result is the statement is true. In this statement is holds for means these are equivalent for a duo module M, where S is the endomorphism of M. So first is M is Phi semi-injective module if and only if left annihilator of kernel of F is same as ideal generated by F, left ideal generated by F, for all the endomorphism F. If and only if kernel of G is contained inside kernel F, then ideal generated by F is contained inside ideal generated by G, for all the endomorphism Fg. And if and only left annihilator of image of G intersection kernel of F is same as left annihilator image G plus left ideal generated by F. So
Have 4 minutes.
okay. So corollary based on this result is having here. This is characterizes Phi self-principally injective ring. So this result is true equivalent for the commutative ring R. We can state R is right Phi self-principally injective ring if and only if annihilator of X is same as ideal generated by X. Here no concept of left and right concept is one side, because here we are considering the commutative ring R. So annihilator of Y is contained inside annihilator of X. Then this implies ideal generated by X is contained inside the ideal generated by Y. And if the annihilator of ideal generated by Y intersection annihilator of X is same as annihilator of ideal generated by Y plus the ideal generated by X. And next result is we have to characterize Phi semi-injective module in terms of the endomorphism rings and their images. Here, let M be the duo Phi semi-injective module and Fg is the sum endomorphism of M. So here, if Fm is embedded into Gm, then Sf, ideal generated by F, is homomorphic image of Sg, ideal generated by S. And here, next part is Fm means Gm is an image of Fm, then Sg can be embedded into Sg. So next part, we can also conclude here, if Fm is isomorphic to Gm, then we can say Sg is isomorphic to Sf. Okay. So corollary based on this one, let R be a commutative Phi self-principally injective ring. So for any element xy of R, YR means ideal generated by Y is embedded into ideal generated by X. Then ideal generated by Y is an image of ideal generated by X. And if ideal generated by X is an image of ideal generated by Y, then ideal generated by X can be embedded into ideal generated by Y. So we can consider same, just like parallel to previous, XR is isomorphic to YR, then RX is also isomorphic to RY. So this is the last slide. So here, these are our references which are used to work here. And thank you. Any question or comment?
I would like to thank Professor Patel for his early talk. Is there any questions or comments? If you have a question, you can write your question through the question and answer section.
Sure.
Seems that there is no questions. Thank you again, Professor Patel, for your.
Yeah, thank you. Thank you very much. Thank you.
Now we will continue with the next speaker. Please turn off your screen sharing, Professor Patel.
Yeah, I have stopped the sharing.
Okay.
Yeah.
Now I would like to invite Professor Karima Chatu from Algeria to the presentation. The title of Professor Chatu's talk is Linear Codes over R and Their Applications in Secret Shading Shapes. Professor Chatu, you are welcome to your presentation, please.
Okay. فيديو على لا كان ما بغاتش تدير.
Could you please share your screen, full screen?
Share.
You can make full screen with Control L.
Control
L.
L. Okay. Okay. درتها.
Thank you.
Hello, ladies and gentlemen. I'm Shtoh Karima. I'm from the University of Patna, Algeria. And today I will speak about linear code over R and their applications in script sharing schemes. First, let's see my work plan. We have the first part, which is introduction and properties of the ring R. We have the definition of simplex and McDonald linear codes over R. After that, we have the construction of linear torsion codes over FP, and the minimal linear codes over FP. Finally, we have applications of secret sharing schemes. After all of that, we have a small conclusion. The main objective is to provide an important overview of information security. The survey argues that cryptographic techniques are the most effective technique for protecting high-value data. Secret sharing schemes is a significant concept in cryptography. For this, several authors have examined certain linear codes and have classified the access structure of secret sharing schemes from their GL codes. However, it is a complicated problem to determine the access structure of the secret sharing schemes based on linear code over finite ranks. Thereby, the first part of this work will focus on the one hand on the construction of linear code over finite ring R. Also, we determine secret sharing schemes based on linear codes over finite ring R and their access structure. The second part will concern the applications of the linear code over finite ring R in the secret sharing scheme. We will describe the most important aspects related to the innovative procedures of the secret sharing schemes. Let's move on to the second part, which is the properties of the ring R. The first commutative ring that we consider is R1 equal Fp plus rho Fp plus rho power 2 Fp, where rho power 3 equal rho. We also define the second and the third commutative ring by equation 1. Moreover, the ring R as the product of R1 and R2 and R3. Define R ring element by C is a concatenation of the element R1, R2, and R3. We say that the linear code C is a R additive code if it is a subgroup of R. A code C is called separable if C is the direct product of C row, C var row, and C sigma. It is easy to to observe that linear code 0, C0, C sigma is defined by equations 3, 4, and 5. According to the definition of the orthogonal non-zero idempotents of a commutative ring R, we have the equations 6 and 7 are satisfied. Now we have a new presentation of the code C is given by the formula 8, where lambda E mi G mi K for E G K between 1 and 3 are orthogonal non-zero idempotent verifying the Pierre's condition over R. It is made using the concepts in reference 1, torsion codes of the code C over R was defined by equations 9, 10, and 11. In comprehension, we have the following tower of codes. In order to characterize the secret sharing schemes of linear code, we want to offer the covering problem of linear codes. Now we define the separ of code word C in FP power N is defined by equation 13. If C and C prime be two code words of C, we say that C covers C prime if only if the weight of C product C prime equal the weight of C prime. Then non-zero code word of C is said to be minimal if the only code words that cover it are scalar multiples of C. Question now is how to construct linear code whose non-zero code words are all are minimal. The following lemma provides the guideline in this direction. That's to say this lemma gives the sufficient condition on weights for a linear code to be minimal. In this part, we have small remark. The problem of linear codes is to determine all the minimal code words of C. This is a very hard problem in general, but can be solved for linear simplex and McDonald codes. Then any minimal linear codes over FP can be used to construct secret sharing scheme. Let a dealer P0 and B be a set of n- participants. Also, let AP be the set of all access elements on P in the secret sharing scheme based on C. To compute shares for all the participants, we have the following steps. First, the dealer chooses randomly a vector U in FP power K such that S equal UG0. Therefore, the dealer treats U as an information vector and calculates the corresponding code word V, where in this case G is a generator matrix of the code C. Consequently, then give VE to party PE as their share for each E between 1 and n-1. If S equal V0 equal UG0, then the set of shares VE1, VE2 from VEM determines the secret S if only if the column G0 verifying equation 15. Then the secret S is recovered by computing 16. To determine the number of minimal access sets in the secret sharing schemes, we have the following theorem. In the secret sharing schemes, we have, based on the code C orthogonal, there are p power k minus 1 minimal access sets. For the third part, we have the definition of simplex and McDonald linear codes over R of type alpha and beta. We define the generator matrix of simplex code of type alpha and beta by the concatenation of simplex code of type alpha and beta over R1, R2, R3. The generator matrices of these codes are given by equations 17 and 18. In this remark, we have some properties of these codes. The same way of the code of the McDonald code, we have the generator matrices of the code of the McDonald code of type alpha is defined by 19, and the McDonald code of type beta is defined by 20. From the construction of linear torsion codes, we can give the linear torsion codes ST alpha, ST beta, MT alpha, and MT beta over F, over FP. The parameters and the generators, the generator matrix of this code is given by equation 21. And the parameter of the code ST beta and generator matrix of this code as is given by equation 22. According to the formula of the generator matrices of linear codes ST alpha and ST beta, we have the following results that given the Hamming-Wide distribution given by this table. In the same way, the generator matrices of linear codes MT alpha and MT beta are given by the formulas 23 and 24. So we have the Hamming-Wide distribution of these codes is given by these tables. We have result on non-zero code words of ST alpha, ST beta, MT alpha, and MT beta over FP are minimal. For the proof, by table 1, we have the weight minimal of ST beta equal the weight max of ST beta. Then from lemma 3-2, all non-zero code words of ST beta are minimal. For the codes MT alpha and MT beta over FP, according to the table 2 and lemma 3-2, we have the following equations are satisfied. We specify and analyze the secret sharing schemes from some of the code introduced in this work by the following results. For the first results, we have ST beta be a torsion code over FP, then is secret sharing schemes based on ST beta orthogonal. There are N1 participants. Moreover, each participant PE is involved in P minus 1, P power K minus 2 out of P power K minus 1 minimal access sets. For the code MT alpha, this code is the torsion codes over FP, then in secret sharing schemes based on MT alpha orthogonal, there are N2 participants. Moreover, each participant participant PE is involved in P minus 1, P power K minus 2 out of P power K minus 1 minimal access sets. For the code empty beta, we have, there are N3 participants. Moreover, each participant PE is involved in P minus 1, P power K minus 2 out of P power K minus 1 minimal access sets. Finally, we have conclusion. In this study, we derive structural properties of linear simplex and McDonald codes over R. We obtain some new features about the ring R. We are in the process of observing and studying more deeply on these rings. Specifically, we mention the torsion codes. We are also interested in studying minimal linear code over FP and applications of these codes in secret chain schemes. We have some references that help to realize of this work. And thank you for your attention.
Thank you for your valuable presentation, Professor Çatı. Is there any questions or comments? You can write your questions in the question and answer section. It seems there is no questions. Thank you again, Professor Çatı.
Thank you. Welcome.
We have about 3 minutes for the next talk. Thank you for your contribution. Professor Çatı, please, you can turn off. Thank you. Hello again, dear participants. Now I kindly invite Professor Özcan Yazıcı from Turkey to the presentation. The title of his talk is The Transfinite Diameter of Bernstein Sets. Professor Yazıcı, you are welcome to present your study, please.
All right, thank you very much. I would like to thank you for thank the organizers for this nice meeting and giving me chance to talk at the webinar. Let me share this. All right, so this talk will be in several complex variables, and I will talk about transfinite diameter of Bernstein sets. I will explain all this, what's the transfinite diameter and what's the Bernstein sets. All right. Well, let me start with some basic definitions. We define pluripolar sets. These are the sets which are contained in the minus infinity locus of a plurisubharmonic function. Here, plurisubharmonic function, you can think of like these are the functions with positive Laplacian. Okay. Here is an example of a polar set in one dimension. C, we say polar instead of pluripolar. Any point, any singleton is a pluripolar because you can write the singleton by this set with this function logarithm z minus z naught in modulus. Well, now we will define transfinite diameter. So we take a multi-index alpha j and we define this, we give this monomials with multi-index z to the alpha j. Here z is the coordinate, the usual coordinate in Cn. And you can count the number of monomials of degree s. This is a simple computation. It's a good exercise for any undergraduate. And this is the number of monomials of degree at most s. Here, we will denote this by ms, okay? We will use this later, these numbers. Now we define transfinite diameter. We take arbitrary points, k points, w1 up to wk, and define this one-dimensional determinant. This determinant is basically determinant of the matrix given by these monomials and the points ei, wj. And you can easily see that this is a polynomial of degree here given by LMS. You can easily count this number. Then we define Fekete points. So these are the extremal points for this polynomial. Basically, these are the points where our function, our one-dimensional determinant here, takes its maximum, okay, or supremum here. And we call this Fekete points. And using Fekete points, we define here first this ds. ds is basically this determinant to the power 1 over s. And remember, ls here, it was the degree of the polynomial v, okay? And as s goes to infinity, we take the limit, and this limit is called the transfinite diameter. Well, this limit exists always, okay? And this was shown by Zaharyuta in general, and in one dimension, it was shown by Fekete. These are some old results. Well, as you realize here, the computation of transfinite diameter is not easy. I mean, explicit formulas are not given in most cases. For unit pole or intervals, you can compute this, but for a little bit more complicated spaces, this is very hard to compute. Instead, we approximate this transfinite diameter we give some upper, lower bounds, and so on. An important result here, which says a compact set is polar or pluripolar if and only if its transfinite diameter is 0. What it says basically, the set is very small if its transfinite diameter is 0. Okay. All right. Well, now we define the sets, Bernstein and Markov sets, and later we will connect these two notions, Bernstein sets and Markov sets, and their transfinite diameter. We will talk about this. Well, what's the Bernstein-Markov inequality? This is a well-known inequality, which says basically the subnorm of the derivative of any polynomial here is smaller than degree of the polynomial times the subnorm of the polynomial. This was proved in 1889. And we generalize this inequality and define Markov set. And we say a compact set, here this inequality, Bernstein-Markov inequality, it holds on a unit disk. And we generalize this inequality and define Markov sets here. We say a compact set is Markov set if it satisfies the following generalization of this inequality. Here, in this inequality on the left-hand side, we have d alpha p. This is basically the partial derivative of the polynomial p. Alpha is a multi-index here. And on the right-hand side, we have a similar thing. Here for Bernstein-Markov inequality, we have degree p. We have degree p here as well. Now we take the supremum over a compact set. And there is an extra r here. We will also talk about this. Okay. So if this inequality holds for any polynomial and for some r and for any multi-index alpha, we say our compact set K is a Markov set. Okay. And you can guess easily here, unit disk or ellipsoids. These are all Markov sets. Okay. These are nice sets, but well, when r is equal to 1, we say our Markov set, we call it Bernstein set, okay? So basically, when r is equal to here 1, we say that our compact set is Bernstein. Well, basically, here, any Bernstein set is a Markov set, right? Set of Markov sets is larger. And we have an open problem here. We don't know whether Markov sets are pluripolar or not. We guess that they're not pluripolar. The reason is in one dimension, it was shown that Markov sets are not polar. This is in one dimension in the plane, okay? But in higher dimension, this is open. In 1997, Sichak proved that Bernstein sets are not pluripolar, and this is in any dimension, even in higher dimensions. Bernstein sets are not pluripolar. That means they are not small, okay? So they are not contained in the minus infinity locus of a plurisubharmonic function. Remember the definition of pluripolar. Pluripolar sets are small sets, you can think of like that. This is hard to pronounce. They here, L and M, I will say, in 2002, they give this lower bound for the transfinite diameter. They show that transfinite diameter of any Bernstein set is bigger than or equal 1 over m times 2 to the n minus 1. N is the dimension of Cn here. And here m, remember this m. Okay, it comes from the inequality here, this M, okay? So Bernstein set satisfies in this inequality with M, and in that case, we have this lower bound for the transfinite diameter. Well, why this is important? Well, in particular, this shows that transfinite diameter is not zero. And if this is non-zero, we know that Bernstein set K is not pluripolar, okay? Well, that was known by Syczek, but this gives another proof of that fact. And this may give some hope to show that Markov sets are not pluripolar by finding a lower bound, like in the case of Bernstein sets, but we haven't succeeded this yet. Well, before going to our result, let me mention this briefly, the proof of this result. In this result, L and M, they used a deep result of Zaharyuta, which says that basically you can compute transfinite diameter using a directional Chebyshev constant, and this is a tedious. It has some tedious computations, and it's not easy to employ, but somehow they use that and show this lower bound. And recently, we proved this a similar, a little bit better lower bound using a very simple technique. Okay, and we show that transfinite diameter is bigger than 1 over E and M. And in the proof, we use some extremal points other than Fekete points. Remember, in the definition of transfinite diameter, we first find some extremal points, and using these extremal points, we define a limit, and that limit was the transfinite diameter. But now we will introduce other extremal points, and using these extremal points, we will show this result. Let me go over the proof, just a sketch. Before the proof, let me first give this extremal set, how we construct these points for the transfinite diameter. We take an arbitrary point, A1, in the compact set, and let's say W1 is 1. We construct these extremal points inductively. Let's say we're given this K minus 1 points in the compact set K. Then we define a polynomial PKZ by this kind of Wanderman determinant. All right, so this is a polynomial in Z, and you can easily see that. Or maybe before we talk about this. All right, so this is a polynomial in Z, and it has supremum at some point, let's say AK. Okay, so we choose AK as the extremal point for this polynomial. All right. Then we construct the sequence of extremal points, and here Jedrzejowski, he showed that using this extremal point, one can compute transfinite diameter, okay, dk. All right. So this is how we construct the extremal point for transfinite diameter. Now we prove our results. Remember, that was the theorem here. Transfinite diameter is bigger than or equal 1 over E and M. N is the dimension, and M is the constant in the Bernstein inequality. All right. So we take some extremal point like in the previous slide, okay? A J minus 1 extremal point for the transfinite diameter. And then we define this polynomial PZ. Here we is the Wanderman determinant. Let me remind this here. The Wanderman determinant is this, okay? All right. And define this polynomial. Here the bottom is a constant, and the top is a polynomial in one variable Z, okay? So this is a polynomial in Z in one variable. All right. Sorry, Z is in K as well. It's not one variable, but it's an n variable. Okay, it's an n variable polynomial. And you can easily see the order of this polynomial is alpha j. This follows from the determinant. Remember, the determinant here is given by this matrix. And this shows that basically it has order alpha j. All right. Well, the derivative of P of order alpha j is alpha j factorial, because the order of P is alpha j, right? And what we do is next, recall here Bernstein inequality, which says the alpha order derivative of P is smaller than, the subnorm of this is smaller than right-hand side here. But left-hand side here, we just see that it was alpha j factorial, and this is less than or equal right-hand side. Here, wj is the supremum of the Wanderman, the determinant. Remember, that's why we get this. I mean, this inequality follows directly from the top one here. Then we apply this inequality several times, and we obtain that wj is bigger than or equal E and M to the 1 minus Lj. Here, Lj is the sum of all orders up to j. And we take the power of both sides, 1 over Lj. Then we take the limit. After we take the limit, we get on the right-hand side 1 over E and M, and we prove our result, right? So in particular, this shows that Bernstein sets are not polypolar, but that was known earlier. It's nothing new, I would say. But this here lower bound is new. It's an improvement of the previous bound given by L and M. All right, that's it. Thank you very much.
I would like to thank Professor Yazıcı for his valuable presentation. Is there any questions or comments? Okay. It seems there is no question. Thank you again, Professor Yazıcı, for your contribution.
Thank you very much.
Dear participants, unfortunately, the planned speaker, Professor Nusret Karaaslan from Turkey, will not be able to attend our webinar, so we will take about 15 minutes break for the last talk. Hello again. Dear participants, now I kindly invite Professor Burak Ekici from Turkey to do presentation. The title of his talk is Formal Categorical Reasoning. Professor Ekici, you are welcome to present your study, please.
All right, thanks a lot. So let me just go ahead and share my screen. Can you monitor my slides in the full screen mode?
Yes, please.
Great. I also want to start with sending my big thanks to organizers for arranging such an interesting event and also providing me with this first opportunity. My name is Burak Ekici. I'm currently working as an assistant professor at the Computer Engineering Department of TED University here in Ankara. And today I want to quickly exhibit the category theory library that I've been implementing within the proof assistant COC for some time now. Let's take a look into the agenda of the talk point blank. So to start with, I want to spend a few words on the COC proof assistant for those who are just encountering that kind of formal proof environments for the first time. And then I'm planning to carry on with a few discussion on the design principles of the category theory library that I've been developing therein. And at the end of the day, if the time permits, I'm planning to conclude with a case study for exemplification and demonstration purposes. Okay, so what is indeed COC? It is in fact a formal proof management system which embodies a functional programming language alongside a specification language. Of course, in the functional programming language, you can go ahead and implement your terminating recursive functions, and in the specification language, you could state properties of these functions and give them proofs. So it's a two-in-one proof environment system in which you can implement your functions and try also to prove properties of them. So I think the proof assistant COC first appeared as an outcome of the PhD thesis of Professor Thierry Coquin. It was written in 1985 at the École Supérieure de Ulm in Paris. So the mathematical and let's say the philosophical foundations on which the proof assistant COC is based is in fact the Curie-Howard isomorphism, which directly highlights a strict relation, or let's say isomorphism or equivalence in between constructive logic and type theory. So here you can basically take type theory as an alternative to set theory in the sense that it provides some sort of constructive foundations to do mathematics. So according to Curie-Howard isomorphism, any proposition by the constructive logic side can be taken and viewed as a type within the scope of type theory. I mean, a type is just a collection of things that you can inhabit anyways. And in the same lines, of course, any valid proof that makes the proposition hold can be seen as a program of the corresponding type. So this means that indeed the slogan is very obvious here. Slogan becomes really obvious. So you can program proofs just as you program functions. So I think it's a very nice ability to be able to program proofs. Instead of going ahead and writing your proofs on a piece of paper, you could go ahead and implement them within proof assistants like COC, for instance. Of course, this ability to program proofs comes with side benefits. So this way you can certify your proofs, because I mean, getting your proofs checked by a mechanical process would be much less error prone in comparison with having a person just checking it out, right? So checking your proofs would be really crucial, just as checking your programs. So the type theory or the logic that backs the COC proof assistant is indeed called the calculus of inductive. This is in fact to simply type lambda calculus with a bunch of constructions, bunch of things like type operators, dependent types, polymorphic types, inductive data types, some restricted form of general recursion, so on and so forth. So it is in fact a constructive logic or constructive type theory, which means that to start with, it doesn't really assume any sort of classical axioms like law of excluded middle or any kind of equivalent. But of course, if you want to do classical mathematics in such kind of proof assistance, you could go ahead and import classical axioms with a piece in mind, because it's provably safe to have calculus of inductive constructions plus law of excluded middle, for instance. I mean, you won't be able to prove false. It's probably safe. So I think another kind of important feature to discuss here is, in fact, the organization of the universes. So in such kind of proof assistance, you have, you just need to organize universes one way or the other, and the way Koch takes it is as follows. So you have three different sorts of universes, namely prop, set, and type. Prop is in fact the universe of propositions. It's impredicative, in which computational abilities are kind of restricted, because in an impredicative universe, if you allow computational abilities together with the assumption of law of excluded middle, then you can easily prove false, and this will basically make your proof system inconsistent, and this is something you want to avoid, right? So luckily enough, we have an alternative called set, in which, I mean, you can basically do computations and assume any form of law of excluded middle, but it is a predicative universe. And the third sort of universe is called type, which is the universe of both sorts, namely prop and set, and it's basically presented in a cumulative and hierarchical manner. Namely, it's basically given within a stratification. So, of course, to avoid Russell-like or Burali-Forti-like paradoxes. So more or less, I mean, the technical introduction to Koch is kind of something like this. Once again, it's basically an environment which allows you to program proofs just as you program your functions. So, well, I think it would be pretty inappropriate if I make an attempt to explain category theory in front of mathematicians. It would be a bit of a shame, but anyways, but nevertheless, I would suffice to say that, category theory is in fact providing some sort of structural foundations to do mathematics, alternating especially axiomatic set theories. Well, in that sense, a category is just nothing but a structure or just collection of objects and arrows, such that for every single object you have the identity arrow, and you have composition operation defined over arrows, which must be associative, and the identities disappear within the composition. So the structural nature of category theory makes it very suitable to be implemented in proof assistants like Koch. And of course, there are a bunch of existing libraries out there implementing categorical objects within Koch. So I just wanted to list 5 of them here, including that of mine. Some of them are standing with papers, some of them do not. So for the equal and the homogeneous treatment, I just wanted to provide the GitHub links to the source codes if you are interested in any sort of development and implementation or kind of like objects. Of course, you can navigate through the links and play with them. So a few words indeed on the design principles. So in general, if you want to computerize any sort of mathematical framework, maybe the first thing that you need to do is go ahead and formalize mathematical objects within the provided programming language, and that's what we do here indeed. So when it comes to formalizing categorical objects, we are basically employing Koch type classes together with the use of dependent or indexed data types. So I think more or less, I think all of the other existing libraries are basically embarking on the same approach in that sense, modulo tiny little changes. So here, what you monitor is in fact an example. It is in fact categorical functors implemented as a Koch type class. Well, as a side information, a functor is in fact an arrow in between categories, mapping arrows and objects, preserving the identities and composition. So here in this implementation, the field called F object is basically responsible for mapping objects, and F map is basically mapping arrows. And these two fields are indeed that they are called proof obligations, and they are there to make sure that the identities and the composition is kind of preserved. So as for the use of dependent types here, well, if it applies, I think it becomes much more apparent within the implementation of the field fmap here. So let me go through an example. So suppose we are given a pair of, we have an arbitrarily given category C and D, and the functor, let's say G, defined from the category C to D. And of course, this functor is going to map every single arrow from A to B in the category C into an arrow from F object of G of A to F object of G of B. Well, of course, the type of F object is completely depending on the functor instance itself. It's an indexed data type. So it's something not surprising. It's indeed, it's a prize. That's something what we want to obtain at the end of the day. But we have to admit that, I mean, on one side, employing, dependent types when it comes to implementing or let's say defining mathematical objects, of course, it brings in some sort of high level of expressiveness. But on the other hand, it's a little bit too cumbersome when it comes to proving properties of dependently typed instances. So what I mean, maybe, so I can basically clarify the point further with this example here. Suppose we are given a pair of functors, f and g, defined from some category C to D, and the goal is to prove that f is g. And the sameness measure here is, in fact, the constructive or the Leibniz equality of type theory, which is constructed through the reflexivity construction. So to prove that two functors are in fact the same, all you need to do is to demonstrate the sub-goals that they basically map objects and arrows in the same fashion. Yeah? So here's the first sub-goal to the main lemma. F and G are basically mapping objects in the same fashion. So of course you can go ahead and state this proposition and try to make an attempt. Make an attempt to prove it, because the type checks. I mean, the type of f object of f is indeed the type of f object of G. So of course, depending on the definitions of f and G, you can immediately make an attempt to prove this proposition. But the same thing is not valid, unfortunately, for the case of fmap. I mean, when it comes to map arrows, because fmap f, the equality in between fmap f and fmap G cannot be directly stated because it doesn't type check. These two guys are of different types. So the type of fmap f is basically represented by the expression down here, and the type of fmap G is the one below. So of course they are different. So what we are trying to do is indeed to compare objects of different types. That is indeed purely illogical. So so the first thing to do is in fact to go ahead and prove that these two guys are of the same type. Maybe their types unify, and only then we can make an attempt to prove whether f and G are mapping arrows in the same fashion. So so this problem is in fact not easy to solve because it boils down to, or let's say reduces to the problem of dependent pattern matching, or let's say higher order unification, which is in general undecidable. So we have no solution. But fortunately, of course, for some particular cases, of course, depending on the definitions of f and G, we could make an attempt to prove this. You know. And so why do we have such a problem? I mean, of course, the problem originates from the fact that, the contextual equality of category theory is not 100% reflected is not 100% represented by the constructive equality of type theory. So there is a mismatch and there's a gap, and it's impossible to close this gap in general. But of course, as I said, what we could do is we take particular cases and try to solve this problem for that specific case. Suppose one way or the other we manage to indeed prove that f and G are basically mapping arrows and objects in the same fashion. Are we done? Not yet. We still need to prove that indeed their proof obligations are the same. So it's a bit strange. So we are trying to make an attempt to prove that different propositions, different proofs of the same proposition are the same. Of course, again, this originates from the mismatch in between the contextual equality of category theory and structural equality of type theory. And of course, we just need to employ a proof irrelevance axiom to get this solved. Okay, so the coverage of the library, I mean, I think I've been implementing lots of things ranging from categories to monad algebras, Eilenberg-Moore structures and all that constructions and lots of theorems. But so as I've been mentioning earlier, so all the other existing libraries are more or less embarking on the same sort of design principles. So the novelties are in fact due to non-existent and different implementations. So in that sense, I think I managed to implement lots of novel things, especially in terms of adjunctions. So I have two different definitions of adjunctions with an equivalence proof of them. One definition is suitable for some proofs, the other for some other proofs, well, within a proof, you may want to switch between definitions, and of course, this will allow you to do so. And the universal property of adjunctions is something that I also managed to prove, different than the other existing libraries out there. This one is interesting. So the fact that the internal language of the category induced by any Cartesian closed preorder is in fact the language of intuitionistic propositional logic. Maybe it's too easy to be proven, so none of the other libraries are just including this. Comparison theorem for the class deconstruction that even gave me a paper a couple of years ago. Now I'm struggling with the same sort of theorem, but this time for the Eilenberg-Moore structures, which requires lots of functional equalities indeed. So let me just spend a couple of minutes also on the case study, in which I'm planning to demonstrate you the fact that the soundness, I mean the intuitionistic propositional logic is sound with respect to categories induced by any Cartesian closed preorder. So, well, a preorder is nothing, but a set enriched with a binary relation which must be reflexive and transitive, and every preorder induces a category with the following fact. So the objects of the category are indeed the members of the preorder itself, and as for the arrows, we define them as follows. So if for every pair of members in the preorder, if they are related by the underlying relation, then this relation is reflected as an arrow in the corresponding induced category. Of course, you have enriched preorders. A preorder is called Cartesian closed if it has the greatest element, binary meets, and the Heyting implications. Well, these structures are correspondences of some other structures by the category theory side. The greatest element is in fact the terminal object. The binary meets are indeed products, and the Heyting implications are just exponentials. So this is one leg of the interpretation. In the other leg, of course, we have intuitionistic propositional logic, which is presented in this very tiny little and easy syntax. So you have propositional identifiers, the ground propositions, the truth value. You don't have falsity because it's a constructive logic in which you are not allowed to prove false. So as for the logical operators, you have conjunction and implication, and every single proposition is indeed either valid or invalid under some context, which are represented by list of propositions, if you want. So implementation in Coq is not really a big deal, just one-to-one correspondence. We benefit inductive types of Coq, and for every single constructor here, we have a unique constructor. There's nothing to discuss here, and the contexts are represented by list of propositions indeed. So, of course, this syntax is being governed by a set of rules. Well, we have 9 rules for this fragment of the logic, each of which are really simple, but maybe focus on this one. It's familiar to everybody, I think. It's called modus ponens. If you have phi implies psi, and phi at the same time under the same context, of course, you can go ahead and deduce psi. Yeah. So we also need to implement these rules within the proof assistant for the sake of completeness and implementation. So, well, again, we are benefiting from the Coq inductive types. So the implementation given here on the slides and this one in Coq's syntax, they are in one-to-one match with a single different set, of course. So this one is named axiom 1. This rule is named axiom 1. This is axiom 2, axiom 3, 4, and so on and so forth. So because you have some naming restrictions within such kind of environments. So here is the maybe the most important point, the interpretation function that's defined from the intuitionistic proposition logic into categories induced by any Cartesian closed preorder. So the function is basically, so every single proposition is represented by a distinguished object in the category. The truth is represented or interpreted by the terminal object, the propositional end by categorical products, implication by categorical exponentials. These two lines are in fact referring to the interpretation of the context. So empty context is by the terminal object, and the non-empty context is basically categorical products of the interpretations of every single individual proposition. So implementing this in Coq is, of course, is a bit too cumbersome, is a bit hard to parse for human eyes, but I think it's not really a big deal. It's just the same thing. So the interpretation function is called M here, defined from IPL to the underlying category. Every single proposition has a corresponding object, distinguished object. Here you see the interpretation of the truth value as the terminal object, the conjunction as product object, implication as exponential object, and these two lines are referring to the interpretations of the contexts. Then you can go ahead and state the main statement, the soundness proof. So if under the context gamma, some proposition phi is provable within the scope of IPL, intuitionistic propositional logic, then there is a map in the, in any sort of category induced by Cartesian closed preorder from the interpretation of gamma, the context to the interpretation of phi. Okay, here is the soundness statement implemented, well, just in Coq. So this is a link. If you're interested, you can just click on and navigate through the corresponding proof. So of course, I'm not going to dig into the proof details, but it's the proof proceeds by a structural induction on the structure of rules. So we have 9 cases because we have 9 rules, and it's just a structural proof, and it's implemented and checked by the proof assistant Coq. If you're interested, once again, of course, we can refer to the library. So maybe a few words on what's next. I think I'm a bit above the time here. I'm basically trying to center my category theory library around the functor equalities, this problem, which is undecidable to start with, but of course, for particular cases, why not to make an attempt to solve this problem. So in terms of the functor equalities, I think these three theorems are really relevant. So comparison theorem for the Eilenberg-Moore construction requires at least couple of functor equalities. Next monadicity theorem is also another interesting one, maybe a case study for a graduate student would be, to prove that category of categories is Cartesian closed. And again, it requires some sort of, a basic form of this problem. And on the other side, I'm also interested in interpreting programming language constructs in the category theory in terms of categorical structures. So one of the interesting points is indeed to interpret dependent products in terms of adjunctions and try to prove some properties benefiting from the universal property of adjunctions. And of course, sky is the limit, and there are lots of things remaining out there to be implemented in such kind of proof assistance. Okay, that concludes what I wanted to say. Thanks a lot for your time, and if you have questions, of course, I will happily get them.
I would like to thank you, Professor Ekici, for his valuable presentation. Is there any question or comment to Professor Ekici? It seems there is no question. Thank you again for your presentation. The next session will start in about 5 minutes later. Thank you for your attendance.
Hello, good morning and good afternoon, everyone. Welcome to the session. First of this session is Gülnur Tuğkan, and I kindly invite Professor Gülnur Tuğkan from University of Turkey to present his talk on the computation method of minimum dwell time for the true stability of discrete time linear systems. Professor Gülnur, can you make full screen, please? Thank you. And now the microphone is yours, Professor Kızıltan. You can continue your talk. Sorry, Gülnur Hocam, sorry, we cannot hear you. Your microphone is closed at the moment. You can open your microphone.
Sorry, is it okay?
Yes, yes. Thank you. Thank you.
Hello, everyone. I would like to first introduce myself first and my work. I'm Gülnur Çelik Kızılkan, working for Department of Mathematics Computer Science in Necmettin Erbakan University. Our topic today is new competition method of minimum dwell time for the sure stability of discrete time linear systems. In this work, first at all, I would like to do a short introduction, and I would also like to mention about discrete time switch system. I would also like to give details of sure stability and sure stability parameter. Then I'm going to give dwell time and average dwell time methods for sure stability. Switch systems are continuous or discrete dynamic systems consisting of a finite family of systems and a rule that provides the transitions between these subsystems. Here, a sigma of t's denotes the subsystems, and sigma is the switching signal function. Sigma is a partial function. Switch systems are encountered in mathematical physics, such as mechanical systems, automotive industry, communication network, aircraft and air traffic control, and many other fields. For this reason, it has been one of the research topics that has attracted attention recently. Naturally, as all in dynamic systems, it is important to examine the stability of the switch systems. In a switch system, even if all subsystems are stable, the system may be unstable for some switching signals. There are roughly two different ways of studies on the stability of the switch systems in the literature. The first of these studies is to examine the stability of the system under the given switching signals, and the other is to determine the switching signal that will ensure the stability of the systems. In this study, we have focused on the second method for discrete time linear switch systems, and we have aimed to give a method that determines that the dwell and average dwell time for the system to be sure stable. There are many studies on the dwell and average dwell time for the sure stability of the switch systems, and these studies are generally use the eigenvalues of the coefficient matrix of the given system. It's well known that the eigenvalue problem is an ill-posed problem for the non-symmetric matrices. Moreover, if a matrix has multiple eigenvalues or is close to matrix with multiple eigenvalues, then its Jordan normal form is very sensitive to perturbations. This ill conditioning makes it difficult to develop a robust numerical algorithm for the Jordan normal form. So the Jordan normal form is usually avoided in numerical competitions. A discrete time switch system is defined as follows. The solution of system 1 is as on the screen for initial condition x of 0. System 1 is sure stable for a given switching signal if 1 is Lyapunov stable and x of t goes to 0 as t goes to infinity. The amount of time passed between the consecutive switching events is called dwell time of 1. If a subsystem is sure stable, then there exists a minimum dwell time that guarantees sure stability of 1. For the system 1, these sets are the switching signals. Here, TKs are successive switching time instant, and n sigma of t is the number of switching before time t. Consider the following difference equation system. If all the eigenvalues, if the absolute value of all the eigenvalues of matrix A is smaller than 1, then the matrix A and also system 2 are called to be sure stable. This criterion is known as the spectral criterion or first Lyapunov theorem in the literature. Lyapunov theorem or second Lyapunov theorem is another criterion for sure stability of system 2. Lyapunov theorem is expressed as like this. The matrix A is sure stable if and only if there is a solution H of the Lyapunov difference matrix equation. Here, H must be positive definite symmetric matrix. Although the spectral criterion is very useful for examining the stability of system 2, it is an ill-posed problem for non-symmetric matrices. Therefore, the concept of sure stability parameter was introduced in literature. Stability parameter reveals the quality of sure stability without calculating eigenvalues. Sure stability parameter of the system 2 is represented by omega A and defined as on the screen. This parameter was first introduced by Bulgakov in 1980. If omega A is finite, then the linear difference system 2 is sure stable. Otherwise, we set omega A is equal to infinity. Now, let us consider the matrices A1 and A2. The eigenvalues of these matrices are same. They are minus 0.1 and 0.7. We can see that they are sure stable matrices because their sure stability parameters smaller than infinity. They are finite, and we can see omega A1 is smaller than omega A2. So it means the quality of the sure stability of A1 is better than the quality of the sure stability of A2. This means that the shear stability of the matrix A2 deteriorates than the shear stability of matrix A1 with less perturbation. For example, if A1 and A2 are perturbed with matrix A like this, then matrix A1 plus B is shear stable, but A2 plus B is not shear stable. As can be seen, while eigenvalues don't give an idea about the quality of shear stability of a matrix, the parameter omega A calculates the quality of shear stability. Then this theorem gives the dwell time for shear stability of a switch system 1. Let us denote by F the set of all transitions between subsystems, and AP be shear stable matrices. Then the switch system 1 is shear stable for dwell time like this. If tau is bigger than maximum alpha n over beta n for n is in F, then switch system 1 will be shear stable. And this theorem for average dwell time, again, F is the set of all transitions between subsystems, and we assume that AP are shear stable matrices. Then switch system 1 is shear stable for this average dwell time. Let us consider these switched systems with initial condition x of 0 is like this. This switch system is given with 3 subsystems with A1, A2, and A3. These matrices are shear stable because their stability parameters are finite. Let the transitions between A1, A2, and A3 is given in this figure. It is seen that switching from system 1 to system 3, from system 3 to system 2, and from system 2 to system 1 be admissible. According to these transitions, maximum alpha n over beta n is equal to 2.8101, and we can calculate that tau is equal to 3. The solution given in this graph are obtained for dwell time. Tau is equal to 3. We can see from this graph the solution is shear stable for tau is equal to 3 minimum dwell time. For minimum dwell time, solution x of t goes to 0 as t goes to infinity. And now let us consider this switch system with 4 subsystems, and subsystems are given with A1, A2, and A3, and A4 matrices. Again, these matrices are shear stable let's consider the transitions between subsystems given in figure 3, in A, in B, and in C. We have calculated the dwell time and average dwell time from Theorem 1 and Theorem 3. You can see them on this table. It is seen that Theorem 1 and Theorem 3 yield good results in this table. I would like briefly summarize the main issue of our study. Although eigenvalue based methods are generally practical, they don't work well for non-symmetric matrices because the eigenvalue problem is an ill-posed problem for non-symmetric matrices. And as far as we know, dwell and average dwell time have not been studied depending on the omega A parameter in the literature. Therefore, the results obtained in this work are new and original. And here is the references. Thanks for listening.
Thank you very much for your good and informative talk, dear Professor Kızılkan. Is there any comment, remark, or question regarding the presentation of the professor?
Sir, actually, I have a question for Dr. Kızılkan. May I ask my question?
Yes, go on, yes.
My name is John, and actually, I am studying similar topics. I am also interested in difference equations. First of all, I kindly ask, could you please illustrate the definition of omega one more time?
Okay. Stability parameter.
Yeah, exactly.
Here.
Just it reminds me, you know, it's kind of matrix measure maybe. So the first question, can it be related with the matrix measure? Second of all, it's going to be very expected question. You dealt with autonomous systems because you choose your matrix is constant. Is it possible to construct a similar study by using matrix functions? Actually, I am much more interested in the answer of second question.
I'm sorry, could you repeat your questions, please?
Okay, let me ask the main question. You used constant matrix, your system was autonomous.
Yes.
Is it possible to construct a similar study by using non-autonomous system? I mean, what happens if A is function, not constant?
I understand.
Thank you.
I don't know because I don't study on non-autonomous system, but I think it is possible. But I will try to find out for you on this subject. Thank you for your question.
Thank you, Professor. Because you know most of the real life models are non-autonomous. I mean, it's challenging. Yeah, that's true.
Yes.
It is difficult to study non-autonomous systems, but if you focus on such a similar study on non-autonomous systems, it will be a great job. That is what I believe. Thank you.
Yes, thank you for your question. But first step of study is for autonomous system.
Thank you. Thank you a lot. Thank you a lot. Thank you for your nice and good presentation, Professor Kızılkan. I think we can continue with the next presentation. Please, can you close your screen share, Professor Kızılkan?
Okay. Sorry.
And also you can close your microphone, please. I kindly invite Professor Kaushik Das from Turkish Government College of India to present his valuable contribution on set-valued minimal fractional programming problems by second-order contingent F derivatives. Professor Das, can you hear me? Could you hear me?
Thank you, sir.
Yes, Professor. You can continue your presentation.
Good afternoon, all. Myself, Kaushik Das from Turkey Government College, West Bengal, India. And topic of my presentation is set-valued minimax fractional programming problem.
Sorry interrupting you, Professor. Sorry interrupting. Can you share full screen, Professor?
Yes. Yes, I am audible. Hello.
Yes. You can you, yes. You are well done. Thank you very much, Professor.
Okay. Title of my presentation is set-valued minimax fractional programming problem by a second-order continuous derivative. So these are the outline of my presentation. So in vector optimization problem, the main objective is to find out the optimal elements of a non-empty subset of a partially ordered vector space. And this type of problem arises in function analysis, operation research, statistics, approximation theory. The main work was done by Edward in 1881 and Pareto in 1896. And this branch started with the work of Kuhn and Tucker in the year of 1951. In the last decade, there has been an increasing interest in the extension of vector optimization problem to set-valued optimization problem, where the objective functions and constraints attached to the problem are of set-valued functions. And this type of problems arise in mathematical economics, management science, and engineering. And it has applications in gap functions for various vector variation inequalities and duality principles in vector optimization experiment. So this is the concept of notion of cone. Here K be a non-empty subset of a n-dimensional equidistant space, and K is said to be solid if interior of K is non-empty. Similarly, K is said to be pointed if K intersection minus K is nothing but zero element of Rm, and K is said to be convex is lambda K plus 1 minus lambda K subset of K for all lambda belongs to closure interval 0, 1. And K is said to be cone if lambda K subset of K for all lambda greater than equals to 0. And this is some examples of solid pointed on closed convex cone of Rm. And now there are mainly two types of cone ordering in Rm with respect to a solid pointed convex cone Rm plus. And for two elements y1 y2 belongs to Rm, y1 less than equals to y2 if y2 minus y1 is an element of Rm plus, and y1 less than y2 if y2 minus y1 belongs to interior of Rm plus. Let B be a non-empty subset of Rm, then the minimal and weakly minimal points of B can be defined like this. Y dash is said to be a minimal point of B if there is no y belongs to B set minus and y not equals to y dash such that y less than equals to y dash. And similarly, y dash is said to be weakly minimal point of B if there is no y belongs to B such that y less than y dash. And this is the notion of contingent cone. Here y is a real norm space and B is a non-empty subset of y. And in the contingent cone 2B at y dash, it is denoted by TBY dash. It is defined like this: an element y belongs to TBY dash if there exists a sequence, there is sequences lambda n in R with lambda n tends to 0 plus and yn in y with yn tends to y such that 1.3 holds. And these are some examples of contingent cone. This portion, this is the contingent cone to y at the point y0, and this portion will be the contingent cone to y at the point x. And similarly, in 1981, Obin and 1999, Cambini et al. Introduced the notion of second-order contingent set. This is nothing but the extension of contingent cone to the second-order case. And these are some elementary notation of set-valued maps. Here, x and y are two real number spaces, and k be a point, a solid pointed convex cone in y. Then f is a set-valued map from x to y, that is f of x subset of y, for all x belongs to x. The effective domain image and graph, epigraph of f can be defined like this. This is the examples of set-valued map, the inverse image of a non-bijective function, the subdifferentiable map of a convex function. And in 1997, John and Rao introduced the notion of contingent epiderivative of set-valued map. This is nothing but a single-valued map whose epigraph coincides with the contingent cone to the epigraph of f at the point x dash y dash. And when the set-valued map reduces to a single-valued map, and this contingent epiderivative reduces to the directional derivative of the function f at the point x0 in the direction q. And this in this diagram we can easily see that in the first diagram it illustrates the Frechet derivative of a single valued map at the point x dash fx dash. And in the second diagram, this portion is the epigraph of f at the point x dash y dash, and this is the contingent epiderivative of the set valued map. So we can easily see from these two diagrams, and that is Frechet derivative for a single valued map and the contingent epiderivative for a set valued map. And for when the set valued map reduces to the single valued map, then the contingent epiderivative reduces to the Frechet derivative. And in 2005, John et al. Introduced the notion of second-order contingent epiderivative of set valued map, and this is also a single valued map whose epigraph coincides with the second-order contingent set to the epigraph of f at the point x dash y dash. Next, we will discuss about the cone convexity of the set-valued map introduced by Borwin in the year of 1977. Yeah, A is a convex cone of a real number space X. Then the set-valued map f from X to Y is said to be K convex if this holds 1.10. And it is clear that when the set-valued map is K convex, then epigraph of f is a convex subset of X cross Y. Similarly, the second-order cone convex set-valued map can be defined like this, and it was introduced by Zhu et al. In the year of 2004. And next we discuss about the cone semi-compact valued and upper semi-continuous set-valued map. A set-valued map is said to be upper continuous if f plus v is open for any open set v in R. Similarly, a set-valued map is said to be Rn plus semi-compact valued if fx is Rn plus semi-compact for all x belongs to domain of the set-valued map f. And this is the theorem developed by Corley in 1987. X and y are real topological vector space, and A is a non-empty complex set of x, and K be an acute convex cone, that is closure of K is a pointed cone. Then and f is a set-valued map from x to y, which is K semi-compact valued and upper semi-continuous set-valued map. Then there exist maximal points of this optimization problem. So this is basically the existence theorem for the existence of maximal points of the optimization problems. So these are some literature survey I am discussing in brief. In 1985 and 1999, Vector and Bhatia and Wire established the optimality condition and developed the duality results of differentiable fractional Minimax problem. In 1987, Jalma established the necessary and sufficient optimality condition and proved the duality results for differentiable fractional Minimax problem. In 2006, Ahmed and Hussein studied the sufficient optimality condition and developed the duality results of non-differentiable minimax fractional problem. And in 2008, Lee et al. Established the necessary and sufficient optimality condition where higher order contingent derivative. So this is our motivation. Over here, we consider a set-valued minimax function problem. The objective function and constants are set-valued map. Then we establish the second-order KKT sufficient optimality condition under say the second-order continuous derivative. And lastly, we formulate the duality results of non-dual group and mixed types, and we prove the desired duality theorems between the primal and dual forms. In 2014 and 15, Das and have introduced the notion of row cone convexity of set-valued maps. So this is the definition of row cone convexity set-valued maps. And in the theorem, they characterize the row cone convexity set-valued maps in terms of continuous derivative of set-valued maps. In 2015, Das and Nahak introduced the concept of second-order row cone convexity of set-valued maps under the assumption of second-order continuous derivative. So in this case, when rho equals to 0, that is in the equation 4.4, we have the first order row cone convexity, and when rho greater than 0, then it is called strongly second order row cone convex, and when rho less than 0, it is said to be weakly second order row cone convex. And it is clear that strongly second order row cone convexity implies row cone convexity, and row cone convexity implies weakly second order row cone convexity. And Das and Nahak in 2015 formulated a set-valued map F from R to R2, which is second order row cone convex, but not second order cone convex. So in this example, we prove that F is second order row on second order here rho equals to -1. That is, F is second order -1 cone convex, but F is not second order cone convex. So these concepts are more general than the second order cone convexity. So this is our main problem, and the problem is set-valued minimax functional programming problem. Here F, H, and G are set-valued maps, and so we have to minimize this, maximize of this subject to this constant. And we assume that the set-valued map phi defined by this, it is cone R plus semi-compact valued and upper semi-continuous. So we will study this set-valued minimax fraction problem in this paper. Okay. So the feasible set of the problem is defined like this: is prime, that is those x belongs to A such that gx intersection minus rp plus is known. So these are some notation we have used in these papers from 4.10 to 4.16. Now the minimizer of the problem is defined like this: let x dash belongs to s dash be a feasible point of the problem M if P, and z dash is maximize of phi x dash y over y belongs to B. Then x dash z dash is said to be a minimizer of the problem if there exists no x belongs to s prime and z with x not equals to x dash such that z is that z dash. Now we establish the second order sufficient KKT condition of the set-valued minimax fractional programming problem under second order row cone convexity assumptions. Now we first prove the following lemma, which will be required to prove our main result. This is our lemma. Next we go to our main result, that is sufficient KKT condition of set-valued minimax fractional programming problem under second order row cone convexity assumptions. So these are the assumptions of the theorem. Here A is a non-empty convex subset, x dash is a feasible point, and z dash is this, and it satisfied 4.19, and we also assume the conditions, these conditions. Here we also assume that the set-valued maps F minus H and G are of the type second order row cone convex type. And these are KKT conditions 4.20, and these are the conditions 4.20 to 4.25. And when these conditions are satisfied, then we can apply the theorem and we can conclude that x dash z dash will be a minimizer of the problem MFP. Next, we construct second order Monda type dual corresponding to the primal problem. Here we also assume that the set value maps f minus h and g are of second order contingent epidemial set value maps. So these are our second order Monda type dual. The maximizer of the Monda type dual can be defined like this: a feasible point x dash z dash w dash J star and Y star and W star of the dual problem is called the maximizer of the dual problem if there is no feasible point x, j, w, z1 star and w1 star of the problem such that this holds. And this is our second order weak duality. Here, these are our assumptions of the theorem. Here, A is a non-empty convex subset of Rm, X0 is a feasible point of the dual problem, and X dash Z dash W dash J star and W star is a feasible point of the dual problem. Here, we assume that the set valued maps F minus H and G are of row cone convex types, and it satisfying 4.27. Then, by applying the theorem, we can conclude that maximum of this not less than Z dash. This is our second order weak duality theorem. Next, we state the second order strong duality theorem. Here, our assumption is that x dash z dash is a minimizer of the primal problem, and w j star belongs to this, and here we assume that for some positive integer k, and for the equation 4.202 4.24 are satisfied at the point x dash z dash w dash j star w star, then this point will be the feasible solution of the dual problem. And further, if the second order weak duality theorem between the primal problem and dual problem is satisfied, then this point will be the maximizer of the dual problem. Next, we develop second order converse duality.
For interrupting, Professor Das, could you accelerate a little bit further, please?
Yes.
Thank you.
So I am going to the conclusion part. Hello.
Yes, please, Professor.
Okay, thank you. So in this work, we introduce the notion of second order row cone convexity in the theorem of set value optimization problems. We establish the second order PKT condition of the set value minimax fractional programming problem under second order row cone convexity assumptions. We also prove second order weak, strong, and converse duality theorem of various types for the problem under second order row cone convexity assumptions. So this is our future work. Our future plan is to study the following problems: symmetric goals of the set value minimax fractional programming problem under second order row cone convexity assumption, an equilibrium problem and variational inequality problem related to the set value minimax fractional programming problem under second order row convexity assumptions. So we can work on this in future. These are some references. So thank you for your kind attention.
Thank you very much for your exceptionally good talk, Professor. Is there any question or comment regarding the presentation of Professor? If any, please prefer the question answer button below of your screen. Since no question, since no any question comment, I think we can continue with the next contributor. Dear Professor Das, thank you a lot for your contribution. You can close your screen and also your voice, please. And the next presenter is Professor Melis Görgülü from Eskişehir Osman Gazi University of Turkey, and he will talk. He will present a good talk on high-degree B-spline algorithms for the numerical solution of the Kadri-Gibbon equation. Professor Görgülü, please share your screen.
Hi.
Hi, welcome, Professor. And now the microphone is yours, Professor. You can continue, please.
Thank you. My name is Melis Dorşahin Görgülü. I'm working at Eskişehir Osman Gazi University, and the title of our presentation is High-Degree B-Spline Algorithms for Numerical Solution of the Coder-Gibbon Equation. The co-author of this study is the Dursun Örük, and my contents are like these. In this study, two different collocation methods based on the octic and the nonic B-spline functions are used to get the numerical solution of the Coder-Gibbon equation. The single soliton solution of this equation is examined by both of the B-spline algorithms, and the comparison of the numerical results with the exact solution of this equation are given by tables and the figures. The Coder-Gibbon equation has the form as in the equation 1 with the initial and boundary conditions like these. And this equation is a class of fifth order Korteweg-de Vries equation. And this is used to model the well-known wave phenomena in the quantum mechanics and the nonlinear optics. And the numerical solution of the Coder-Gibbon equation are studied before by some researchers by the a-domain decomposition method and the higher wavelet method, Pedro-Galerkin method, collocation method, and the variational iteration techniques. In this paper, two simple numerical B-spline algorithms are proposed, taking into account the difficulties of the getting this equation's exact solution due to its nonlinearity and having a fifth order derivative. In numerical methods, we consider a uniform mesh with the nodes x sub r, and the space type denotes by h, and the exact solution of the unknown functions are denoted by u, and the numerical solutions of it is denoted by the capital U, and the delta t denotes the time step. And for time discretization of this equation, we use the Crank-Nicolson method. And together with these approximations, then we obtained this equation for, this is the time discrete form of the Coder-Gibbon equation. And using the following recursive formula, which is mentioned by De Boer, we obtained the B-spline functions with the various degrees, and the octic and the nonic B-spline functions are again obtained by this recursive formula. And if you want some details, you can see the details in the Beyza Koyulmuş master thesis. The octic B-spline functions at the nodes can be obtained by the following formula. These are like these. And the numerical method, octic B-spline collocation method, for the space discretization of the time discrete form of the Coder-Gibbon equation will be obtained. First, we take the approximate solution capital U. Here, B8 is the octic B-splines, and deltas are the time-dependent unknowns, which will be calculated later. And the approximation and its first seventh order derivatives over the elements like these can obtained as follows by using the octic B-spline functions in the approximations equation. And finally, the fully discursive form of the Coder-given equation is obtained by using the octic B-spline coequation method like this. And here the parameters are chosen as. Thus, the system consists of n+1 equations and n+8 unknowns is formed. By using the boundary conditions, some parameters are eliminated from the system. Then the obtained n+1 times n+1 metric system is solved easily using the MATLAB packet program. To start the iteration of this system, the term delta 0 is achieved by the help of the initial and the boundary conditions of this equation. Then the other deltas at the next times can be obtained. Since we get an implicit system according to the term delta, we use an inner iteration in which, before using the calculations of next time step approximation for the time parameter. Then the other B-spline we use is nonic B-spline. Again, it's obtained by the recurrence relations as in 11. And the parameters are like these volumes. And the other numerical methods we suggest is the nonic B-spline collocation method. Again, for space discretization of the time discursive form of the Coder-given equation is used. And let me take the approximation capital U as in 12. Here B9 is the nonic B-spline and deltas are the time-dependent unknowns again. And the approximation solution and its first X orders derivatives over the elements like this can be written as follows. And finally, the fully discursive form of the Coder-given equation is obtained as follows again, where the parameters are like this. This time, the system is obtained which has n+1 equation and n+9 unknowns. Again, using the boundary conditions, some parameters, first 4 n+4 parameters are eliminated from the system. Thus, the solvable metric system is obtained and then solved by the MATLAB packet program. And similar with the previous method, the other steps are repeated. For the test problem, we take the propagation of a single soliton wave. Here, the accuracy of the methods is calculated by the following L-infinity error norm, and the time and space discretizations order of convergence are computed by the following formula. This is two different formula for delta t and the h we use. And the single soliton wave solution of this equation is can given like this. The computation domain is fixed in these intervals, and the initial condition can be obtained from this exact solution like this. And the boundary conditions are taken as 0 for this equation. The simulation of the wave during the time interval 0 and 0 or 4 is shown in these figures for both of our proposed methods. And the error norms are given next table. And from this figure, it's seen that the obtained wave remain in the initial remains its initial shape during the running time for both of the methods. You can see. And this the table 1. If we looking at the change in the error norms over time, it can be said that it supports the previous situation, and the method success will simulate this way because of the error norms is so little for these methods. And the comparison of the obtained error norms for each of our proposed methods and the quintic B-spline collocation method in the Kara Ağaç study are given in this table. According to this table, while space steps is decreased, all of the error norms decrease. And it's seen clearly that the our methods have lesser error norm values than the other method. And the nonic B-spline collocation method has the less errors for the various values of the age. Table 3 and 4 are given to see the conservation invariance for the proposed methods. From table 3, when the time step is fixed as 0 or 1, the space discretization of the convergence for the optic B-spline collocation method is around 5. For the other method, the nonic B-spline collocation method is around 6. From table 4, when the space step is fixed as 0 to 5, the time discretization of the convergence of the both of the methods is around 2. And the distribution of the absolute error at time 0 or 4 is demonstrated in these figures. As carefully inspected from the figures, the error is observed at the middle of the space interval, both of them. And this result is also compatible with the results we obtained in table 1. In conclusion, the numerical solution of the Coder-Gibbon equation is present by two finite elements method, which are the collocation methods based on optic and the nonic B-spline functions. And for space discretization of the methods, the optic and the nonic B-spline functions are used as trivial functions, and for time discretization, the Crank-Nicolson method is used. What is considerable in this study is that the use of the high degree B-spline functions that have not been used before to solve numerically high order partial differential equations. The soliton wave solution of Kortebek-Devar's Coder-Gibbon, is simulated successfully to see the efficiency and the accuracy of the methods, and the error is considerably small for both of the proposed methods. And finally, we have seen from this examination that the high degree B-spline functions may be used to get the numerical solutions of a high order nonlinear partial differential equations, which has the similar properties with our equation. Thank you very much for listening to me.
Dear Professor Görgülü, thank you very much for your excellent talk regarding the subject. Is there any question or comment regarding the presentation of Professor? Seems no. Thank you again, Professor Görgülü. You can close your screen share and your microphone also. Thank you a lot.
Thank you.
And according to my code, we should have a 7 minutes break. Up to the next contributor time.
Namaste. Greetings to all.
Sorry, Professor Agarwal. We will wait the exact time for your talk.
It's not my turn. This.
Yes.
Excuse.
The next contributor is you.
Next.
Yes. After
next.
5
Okay.
minutes.
Okay.
After 5
Okay.
minutes.
Okay.
Thank you.
Okay.
Hello, everyone. The next contributor, Vandana Agarwal, I kindly invite him to present her talk. She is coming from Preliminaries College of India, and he will give a talk on heat transfer in magnetic hydrodynamics, macropolar Jeffrey fluid flow through porous medium over an exponential stretching sheet with thermal radiation.
Namaste.
Yes, you can continue, Professor, please.
Just greetings to all respected panelists.
Can you share no, it's your turn. Can you share your screen, please, Professor Agarwal?
Sure.
Yes, please.
Is it visible? Right?
Yes, visible. And
okay.
Put your make it full screen, please. Control L, I think.
Control
L.
F.
L.
N.
L. L.
L. Is it okay?
Maybe you can arrange it from the view section.
Just.
No, not this way. Control Los Angeles. Control and L.
Control
yes.
F.
L. Los Angeles. L. Control L. It's okay. Thank you, Professor.
So, before I begin with my presentation, I would like to say thank you to the organizers for giving me this platform to present my work. So, we must and before I go further, I would also like to say thank you to my supervisor, Dr. Bhupender Singh, my guide, that without his support or guidance, I won't be able to present this work. So the title is like that. Actually, I keep it here somewhere. The heat transfer in magnetic hydrodynamic micropolar Jeffrey fluid flow through porous medium over an exponentially stretching sheet with thermal radiation. Now, in this paper, numerical investigation of the problem, the said problem is being examined. And here I have used this using similarity solutions based on the boundary layer assumptions. And through this suitable similarity transformations, the governing partial differential equations are transformed into the non-linear ordinary differential equations. And MATLAB software has been used to solve this, and inbuilt solver is there, BVP4C. So a parametric study for the for such a different parameters like magnetic field, porosity, Jeffrey fluid, etc. The radiation parameter on the flow and heat transfer is conducted, and the effects were discussed. So a physical interpretation set of numerical results on are obtained, like we have used velocity profile, micro rotation, and the temperature profile, and the graphs are plotted, and the characteristics has been shown by using whatever graphs are plotted. Based on that, certain conclusions has been made. So the study of boundary layer flow over a stretching sheet has gained much interest in past few years because of its now I'll be more comfortable. I hope you won't mind if I'm switching off my camera, because some network issues I'm getting here. Now the slide is more visible to me. and various applications like polymer extrusion, annealing, and thinning of copper wires. So this has many applications, basically in fibers and polymer plastic sheets. So flow in the boundary layer on a moving continuous solid surface was first investigated by Sekida. Since then, now various aspects of the problem have been investigated. So just in references, I have mentioned few the name of the researchers and the papers from where I have taken help. Now, as a result of our research work, the current study aims to investigate the flow and heat transfer of a Jeffrey fluid over an exponentially stretching sheet. And similarity transformations, basically similarity transformations, I'm not going into detail just because of some other engagements and short of timings. So Jeffrey fluid is in general a less complex direct model utilizing time derivative instead of convective derivative and utilizing by most fluid models. Now this liquid model is equipped for depicting the qualities of retardation and relaxation time. Coming to the mathematical formulation of the problem, a steady, this two-dimensional flow of an incompressible Jeffrey fluid over an exponentially stretching surface is considered with a uniform magnetic field. X-axis has been taken along the stretching surface with y-axis normal to it. And the sheet stretched vertically with the velocity W is equals to X to the power L, where this L is the reference length. The flow and heat transfer characteristics under the boundary layer and Voisley approximations. Now with the radiation effects are governed by these equations, like equation of continuity momentum and this micro rotation and one temperature. I hope you're visible to see here. Now this where the symbols have their usual meaning, like U and V are the velocity components in the X and Y directions. Lambda 1 is the ratio of the relaxation and retardation time. Lambda 2 is the relaxation and T is the fluid temperature. Then this mu is the kinematic viscosity and mu is taken as a coefficient of fluid viscosity. Likewise, this standard symbols has been taken, and like for thermal conductivity and all. Then the corresponding boundary conditions, these are taken as this, like UWX, like first it is the velocity of the sheet, and where this goes infinity is this BEX is the external velocity. Then hereby we introduce some similarity variable like eta. Now this F and theta are the dimensionless stream functions, and stream function is and this theta is the for temperature. And these introducing these similarity variables, now the equations has been transformed. These equations has been transformed or reduced to the nonlinear ordinary differential equation. So with the help of this this BVP package or the inbuilt solver, this equations has been reduced, and here graphically we have applied these equations for this simulated velocity, micro rotation, and the temperature. And these parameters, the effect of these parameters is been studied based on the graphical results. These are the transformed boundary conditions. So actually, I'm not going into the detail just because of short of timing. I'm sorry for that. But quickly, just I am presenting an overview of the my work, just a research paper, like effect of various parameters on velocity, micro rotation, and temperature. Like all the three graphs, like what the nature, by the nature of the graph, we can have a few conclusions at the end of my slide, that how come it is like near the, you can say near the sheet, like where this Jeffrey fluid is in the solid form, and when we move away from the this boundary, then it's come to be in a fluid state. So here the graphs for the Jeffrey fluid parameters, that how it is showing effect on this velocity profile, micro rotation profile, and here theta is the temperature profile. Here, like it is showing that with the increase in the value of this lambda 2, the temperatures is also increasing. It's the effect of de Boer number. So likewise, all the graphs has been drawn. Basically, graphical discussion has been there in my paper. So like likewise, this 1 minute. Like one I can here this, like the porous medium, like does not or resist the flow. Flow has been asserted. Now, larger the denseness of the porous medium, the larger the temperature. The micropolar particles of the fluid oscillates irregularly about the point. And eta, the value is being shown, and accordingly porosity, based on this porosity or other parameters, likewise for de Boer number and Prandtl number, mixed convention. I'm just sorry again, I have few engagements and not able to give you explain them properly because of the short of timing. Just I'm coming to the conclusion part. Like it is found that temperature profile of the fluid increases with the decrease in the value of de Boer number, and also the radiation parameter controls the thickness of the thermal boundary layer. And it has also been concluded that the increase in the micropolar parameter leads to the cooling of the sheet and the mixed convection. These are the few conclusions which have been drawn. And it is also concluded from the plotted graph that Jeffrey fluid parameter and magnetic field parameter has an inverse effect on micro rotation profile of the fluid, and that is increasing the value of this parameters leads to the decrease in micro rotation, right? Near the sheet, the fluid show the oscillating behavior. So some references and few reference I mentioned in the end. One paper I have mentioned here. This has been accepted, but yet to be published. So thank you once again for the patient listening. I'm really sorry again that I have to go somewhere, so I won't be able to attend more. I'm hope for looking forward, and hopefully I'll be there for tomorrow's session. Thank you so much once again. I'm stop sharing my screen.
Yes, Professor, please. Thank you very much for your excellent talk, Professor Agarwal. Any question or comment regarding the presentation of the professor? Please prefer question and answer button below for any questions or comments. Seems no any question or comment. Then we can continue after 5 minutes break again with the talk of Semih Sakarya. At the moment, we will give a 5 minutes break. Hello again, everyone. I kindly invite Professor Semih Sakarya to present his
Hello,
talk
I'm here.
on stability analysis of a modified Holding Tenor model with delay. He is coming from Untitled University of Turkey. Dear Professor, the microphone is yours. Please continue your talk.
Okay, I will share my screen now.
Yes, please.
I think everything is ready, so I can start.
Yes, everything seems okay.
Okay. First of all, thank you all for coming to listen to us today. Firstly, I want to introduce my fellow colleagues, Ali Demirci and Cihangir Özdemir. They are with us today. And today we are going to talk about our newly established pre-predator model, which we named Modified Holding Tenor Type 2 model. And we will talk about the stability analysis of this model, as well as the delayed version of the model. Okay, we will continue with some introduction parts. After that, I will introduce our new model, the Modified Holding Tenor model. And we will see the stability analysis of this model and the delayed version's stability analysis. And we will continue with some numerical simulations. And we will conclude our work and we will finalize this today. So there are many pre-predator models in the literature, and they are used to explain the true interactions and dynamics between prey and predator species, as well as the changes of the populations of the species through time. Holding Tenor model is one of these models actually, and its origins is based on the generalized Gauss model. In the late 50s, Holding suggests this model, and after some modifications of the tenor, this model finally is referred to as Holding Tenor model in the literature. You can see now two-dimensional dynamical system, which we can say it is the classical Holding Tenor model. In here, X represents the prey populations prey population, and Y is the predator population here. Of course, I should mention the Allais effect here. The term X minus N in the first equation is represented to the Allais effects. And it is basically used for the explain some biological phenomena, which are ability of surviving or ability of finding mates. This kind of similar biological phenomena are tried to explain with Allais effects. In this work, we aim to establish a new prey-predator model inspired by classical Holding Tenor model, and we aim to analyze and obtain the stability conditions of this model and the delayed version of the model, as well as to obtain the conditions of the whole bifurcation. And now I can introduce our newly established model. We established three-dimensional dynamical system here. X and Y are the prey species. Meantime, Z are the only predator species in our ecological system. Predator Z can eat both prey. Meantime, there's no interaction between prey species. And as you can see, we only use Allais effect for the only first species, which is X. And now you can see the delayed version of our model. As you can see, we use the delay parameter 2 for only the predator species Z, in order to realize the situation that predator population needs some time to birth to predation. And this means that a newborn predator species needs some time to grow old enough to predate on its own and to be represented mathematically in the predation function. So we can continue with the stability analysis of the model. And in this dynamical system, we have three different equilibrium points. And in the E1 and E2, there is no predator species. Meantime, in the E3, we can observe some coexistent state of all three species here. Of course, in order to realize a realistic biological model, we only consider the non-negative values of E3, and we analyze this. In order to analyze the stability of these equilibrium points, firstly, we start with finding the Jacobian matrix of the dynamical system. We can write the J matrix dependent on alphas, as you can see here. And by using that, we can establish our characteristic equation on the followings, depending on betas here. To decide the stability of these equilibrium points, we will use this characteristic equation, and we will start with substituting E1 and E3 separately into the characteristic equation. These are similar equilibrium points because there's no predator species, and both prey populations are at the limit of the carrying capacity of the habitat. Obviously, we can use the Returris criterion here to decide the stability of these equilibrium points. And we can say that if these three conditions are satisfied, our equilibrium points E1 and E2 are stable under these conditions. And you can see the conditions here. And we can say that our dynamical system is stable at these equilibrium points under these conditions. Similarly, we can substitute the E3 into the characteristic equation, and we can find the followings. And also, we can say that Returris criterions hold here as these three conditions are satisfied. Our equilibrium point E3 is stable under these conditions. Now we can look at the delayed model stability analysis. To be a reminder, I want to say that we only use the delay parameter tau here for the predator species Z, and which means there is no delay condition at E1 and E2, pardon. And so the investigation of E3 with delay conditions are performed only. In order to decide the stability of the dynamical system around the equilibrium point E3, we use this following equation to obtain the characteristic equation, actually. Here, J0 is the Jacobian of the dynamical system with respect to the non-delay variables, whereas the J2 is the Jacobian with respect to the variables with delay. And later, we can write our J0 dependent on alphas, as you can see here. And similarly, we can write J2 dependent on thetas like this. By using these two, we can obtain our characteristic equation of the delayed system, as you can see here. So, in order to investigate E3, we should consider two different cases here. In the first case, we will look at the tau values where tau equals to 0. And we will substitute tau equals 0 into the characteristic equation here. And similarly, we can use the Returris criterion, and we can say that these three conditions are satisfied. The dynamical system is stable at equilibrium 3. In the second case, we should consider the tau values where tau not equal to 0. And assuming that omega I are the roots of the characteristic equation of the delay system, and substituting this into the characteristic equation, we can obtain the following. And by using the Euler formula, we can separate the real and imaginary parts. And help of these two equations, we can obtain the last following equation here. After that, we will suppose that u equals to the omega square here. And we will define our h function depending on u and p's, as you can see here. After some provings, for different lemmas, we will obtain our main theorem, but we didn't mention the proofs and lemmas here due to our time concerns of the presentation. So I will directly mention the main theorem here. We can see that tau 0 is our critical tau value of the equilibrium points. And we will suppose that our root Hurwitz criterions are held. So we will see our three different parts of the main theorem. In the first part, we can say that if these two conditions are held, the equilibrium point E3 is stable. In the second part, similarly, we can say that if these two different parts of conditions are satisfied, we can say that our equilibrium point E3 is stable for tau values between 0 and tau 0. Whereas it may behave unstable for tau values between tau 0 and tau 1. In the third part, we can see that if these conditions are held, our dynamical system undergoes a half bifurcation at the equilibrium point E3 when tau value is equal to the critical tau value tau 0. Of course, in order to support our theoretical results, we do some numerical simulations on MATLAB. And in order to do that, we select some parameters and we establish our selected system here, as you can see on the right. For this selected system, we can find two different positive equilibrium E3 points. E3A is a stable equilibrium point here, means while E3E is an unstable one. And also, as you can see, we calculated the critical tau value tau 0 for the stable equilibrium point E3A. Now we can observe some graphics. In the first figure, we can observe the behavior of the dynamical system for a lesser tau value than the critical tau value. You may see all of the three species comes to the equilibrium point after some time periods. In the second figure, we can observe the behavior of the dynamical system for a critical tau value. As you can see, the oscillation starts for this critical tau value. And in the chart figure, we can observe the system for a greater tau value than the critical tau value. We can see the periodic solutions. And we can see our system for the same tau value, but in a longer time period in the figure 4. Of course, we can see some two-dimensional phase portraits for changing tau values here. And also we can see three-dimensional phase portraits, again, for changing tau values. To be a discussion part of the numerical simulations, we can say that all three species comes to the equilibrium point after some time in the figure 1. And E3A is an asymptotically stable equilibrium point when tau is lesser than the critical tau value, which we observed in figure 1. Also, we observed in the figure 2, our dynamical system exhibits a half bifurcation at the equilibrium point E3A when tau equals to the critical tau value, tau 0. For the greater tau values than the critical tau value, tau 0, our system periodic solutions bifurcating around the equilibrium point E3A. And this bifurcation is named as supracritical bifurcation, as bifurcating period solutions surrounds an unstable equilibrium point. So to sum up, we can say that all results obtained from the numerical simulations match with the theoretical findings. And to be a conclusion in this work, we established a new pre-predator model, and we named modified following tenor type 2 model. And also we analyzed the stability conditions of this model, as well as the delayed version of the model. And we obtained the stability conditions and also the conditions of the half bifurcation here. We support our findings with the numerical simulations, and the simulations shows us that our findings match with our results. So thank you for listening to me today. Thank you for your attention.
Thank you very much for your extremely good talk, Professor Sakarya.
Thank you.
Is there any comment or question or remark regarding the presentation of the professor? Seems no question.
Okay, thank you very much. I will stop my sharing.
Thank you, Erat. Yes, Professor. Please, you can close your screen share and voice also. Thank you. And at the moment, we will go a break of 8 minutes. Now, I think. See you after 8 minutes then. Good morning and afternoon, everyone. I am Tahir Coşkun. At the present time, this time, speak for the talk of Professor Gilbert Strang talk. Unfortunately, we have some connection problems, some technical problems with his internet. I kindly invite Professor Volker Neumann to do his presentation, and I want to say thank you a lot, Professor, to accept our invitation. And I want to say a couple of words about him. Professor Neumann is coming from Technical University of Berlin, and he published a lot of peer-reviewed articles in high-level journals, and also he has published several books. I'm not going into detail. Currently, he is also the president of the Executive Committee of the European Mathematical Society. It is really a great pleasure for all of us, and particularly for me, a great honor to have Professor for a very informative and noticeable talk on Hamiltonian systems. And in the talk, Professor will introduce a universal model class for numerical simulation and control and their algebraic and geometric properties. The link and other technical facilities seem to be okay, dear Professor. You can share your screen and you can open your microphone, please. And dear Professor, do welcome to your presentation. You can start now, please.
Thank you very much. Can you see my screen?
Yes, Professor, but is it able to full screen? Yeah. Thank you. Yes, it seems okay.
Okay, thank you very much for the invitation. I'm really sorry that things got messed up this morning with my talk. I really had the dates and times messed up. So thanks also for the nice introduction, and I will talk about port Hamiltonian systems, a universal model class for numerical simulation and control and their algebraic and geometric properties. So let me start with some general remarks. So when you look at modern key technologies, they require modeling, simulation, optimization, and control of complex dynamical systems. And most real-world multi-physics systems combining components from different physical domains, different accuracies and scales. And modeling today becomes exceedingly automatized, linking subsystems of or numerical methods in a network fashions. A new buzzword that we always hear is digital twins, that are models that adapt to changes in real life. And modeling analysis, numerics, control, optimization, and data science techniques should go hand in hand. And most real-world industrial models also need model reduction to be able to run them for data assimilation, optimization, or control. Let me give you a real-world problem. So at the moment, we're talking about, at least in Germany, we're talking about changing the energy system completely to green energy, and wind and solar power, use them to generate the energy. But then we're also talking about changing the transport sector, changing the car from gasoline to electric. But also, since we are living in a cold country, we have to heat. And so these three energy sectors have to be coupled. And there are many challenges in this respect. So first of all, we have to guarantee the security of energy supply. The energy conversion must be efficient. Different energy sectors have to be coupled, and different components of the energy network have very different modeling accuracy. And they live on different time scale. Some come with increased randomness and decentralization, and we need dynamical approaches. And so in the long run, we would like to build a digital twin. Let me give you two examples what are components of such an energy network. And the first one is gas transport. So this is a big research project funded by the German Science Foundation on the planning, simulation, optimization, operation of gas networks. It's a joint project with several colleagues from different universities and industrial partners. So what do is you have a network of pipes, compressors, sources, valves, and also consumers. And on this network, you run a partial differential equation. These are typically 1D or 3D Euler equations. And you have such a network. And parts of these are compressor station. For example, here would be a compressor station 1 and compressor station 2, where the gas is compressed to make it flow faster and increase the pressure. Such a picture here is a picture of a compressor station. And so in such a compressor station, you don't really have a mathematical model available, but you have curves which you have to follow. So you have data-based models or even reduced order models. And the gas network, so here's this network in Germany, consists of big lines. These are the big lines. Each big line, each node here consists again of nodes, and this is again of nodes. And altogether, you end up in every household. And the mathematical model for the flow to describe them on each of these model components is we use the one-dimensional Euler equations. These are partial differential equations for the density, the internal energy, the temperature, the velocity, the pressure, and the height of the pipe. And you have mass conservation, momentum balance, and energy balance. So you have these three types of partial differential equations, and you have some constants in here, like the heat transfer coefficient, the friction coefficient, the diameter of the pipe, the wall temperature, the gravitational force, or the gas, real gas constant. So now you have a complicated network like this here, and on each pipe in this network, you have to solve this partial differential equation. And so this makes it a real challenge. So in order to be able to do this, we have built a model hierarchy, which is essentially on top are these Euler equations with temperature. And then we simplify the equations. For example, we set the temperature to be constant. These are the isothermal Euler equations. Or we look at a semilinear model by setting ddt rho v squared, which is small, we're setting this to 0, and so on. So you have really not only one model, but you have a whole sequence of models. And each of the models is discretized. It's a discretized PDE, and some of them are surrogate models. So that was my first example. My second example is a very similar project that is district heating. So the idea is to use the extra energy from waste incineration or extra gas or extra electricity that you have to heat up water that you send to the households to heat. And so you have a coupling between heat, electric, waste, and gas for the energy production. And then you have such a network. These are the households. You have a network where hot water is pumped into the network. It flows through the network, and the cold water flows back, and then is heated up again and in a circle. Typical temperatures are between 85 Celsius forward flow and 60 Celsius for the backward flow. So the equations look very similar, but this time they are incompressible because water is incompressible. So we have, again, mass conservation, momentum balance, and energy balance, together with incompressibility condition for water. And here some terms have been ignored. I have some references here, and I'm happy to send the file so that you can download it and look at the references. Other domains are, as I mentioned, power networks. We're also working with the company Siemens on electricity generation, turbine repair, additive manufacturing. We also look at reactive flow control. We also look at brain models, poroelastic models, or multibody dynamics. And if you're interested in reading more, there's a survey paper by myself and Benjamin Unger, which is on arXiv. So if this is our goal, then it would be great to have a model class in which we can do all this at the same time, a uniform modeling class. So we want representation that work across scales and physical domains. It should be open for, should be ready for real physics, for open and closed systems. It should have nice algebraic, geometric, and analytical properties. The model should be easy to analyze mathematically, existence, uniqueness, robustness, stability, and so on. We should have nice mathematics in the background, like canonical forms and things like that. And the model class should be good for space and time discretization and model reduction. And you should be able to use it for simulation, control, and optimization. And the question is there such a jack of all trades? Or in German, there is an animal, it's an egg-laying wool milk sow. So it's a perfect animal which can do everything. And the question is, does such a thing exist? And in the next part, I will show you that energy-based modeling with port Hamiltonian systems is a good start in this direction. So the idea is use energy or power as a common quantity of the different physical systems. So you connect different parts via energy transfer. To do this, you split the components into elements which store energy and elements which dissipate energy and control inputs and outputs. And you combine them with a geometric structure called the Dirac structure. And you allow every submodel to be such a model hierarchy as I showed you for the gas networks. And a system theoretic way to realize this are so-called dissipated port Hamiltonian systems. So what are they? So the classical description of a port Hamiltonian system is like this. So you have an ordinary differential equation, x dot, the time derivative is equal to J minus R. J is a skew-symmetric matrix which describes the energy flux among storage elements. And R is a positive semi-definite matrix which describe, or matrix function, which describes the energy dissipation or loss in the system. And this is multiplied with the gradient of an energy function. That's called a Hamiltonian. It describes the distribution of energy among the storage element. And then we have inputs, B minus PU, and outputs, Y, which is B plus PU, P times the gradient of the Hamiltonian, and you may have a feed-through term. So this is the ODE version. In the infinite dimensional case, these coefficient matrices are operators. They can be differential operators that map into appropriate function spaces. Why is this a good approach? So the first thing is that port Hamiltonian systems generalize Hamiltonian systems and also gradient flow systems. So that's a huge class. And the conservation of energy is now replaced by so-called dissipation energy. So the energy function h at time t1 minus the energy function at time t0 is bounded by the integral over y transpose u. So y is the output, u is the input, and this is the supplied power. So the system itself doesn't generate power, but the power that the system has is, or energy is bounded by the power that you have supplied to the system. The really great thing is that if you take two such port Hamiltonian systems and you connect them, in a power conserving way, then you get the port Hamiltonian system again. So the system class is closed under modularized network-based modeling. Stability and passivity analysis is easy. So you can analyze passivity because this is really a Lyapunov function for the dynamical system. The port Hamiltonian structure allows to preserve physical properties in Galerkin projection, in finite element methods, in PDE discretization, also in model reduction. And the properties of the physics are encoded in the algebraic structure of the coefficient and in the geometric structure associated with the flow of the system, and they are easily extendable. If we want to use such port Hamiltonian systems for networks like the like such a gas network, we also need to add algebraic constraints. And to add algebraic constraints, we have to look at so-called constrained port Hamiltonian systems. And recently, together with my student Ricardo Morandin, we have extended the definition we just had to also include algebraic constraints. And this is done in the following way. Algebraic equation would be given if this E matrix, which is in front of the derivative, if this E matrix is, say, a singular matrix. So if it's 0, then it would be purely algebraic. And so the terms are very similar. It just looks the same. This E function, which is called the effort function, has the relation if E is the identity, then it's the gradient of the Hamiltonian. So then it's exactly the extension of the system before. But the E matrix here E matrix function would be singular. And so this Hamiltonian now satisfies these two conditions. Gradient of the Hamiltonian is E transpose E, and the time derivative of the Hamiltonian is E transpose R. And now the properties that I've described before are encoded in the algebraic properties of the skew-symmetric part, which is given by this matrix J, B, B transpose, and the skew-symmetric part of the feed-through term, and the W matrix, which is the symmetric parts R, P, P transpose, and the symmetric part of this. And this is required to be semi-definite. And this definition extends to weak solution and infinite dimension, but I'm not going to discuss it too much. So again, you have such a dissipation inequality, like here, but now we even allow that the function depends directly on time. But again, we have the same dissipation inequality, and we also have a power balance equation that implies this dissipation inequality, that the total time derivative of the Hamiltonian is given by this effort and use vector together times the W matrix plus Y transpose U. And since W is positive semi-definite, we get this inequality.
So what do you suggest?
The really nice thing about this class in this general way allows you to you can do any local diffeomorphism. So any changes of variable, x is phi of t and x tilde, and multiplication with a non-pointwise invertible matrix from the left. And if you look at this system, this is again port Hamiltonian. If you have a local diffeomorphism, and if it's a global diffeomorphism, then the two systems are equivalent. So that means you can go to different coordinate systems. And you can locally look at charts if you have a nonlinear system. The structure is also invariant under making the system autonomous in time. So you just add the equation T dot equals 1 to the system. And the resulting system again is a port Hamiltonian structure. You can do structure preserving interconnections. So you take two such systems, and you build a linear combination between the inputs and the outputs of the two systems. And then the interconnected system is again a port Hamiltonian DAE, and the energy functions are just added together. And this brings me to the so-called Dirac structure. That's the geometric structure that is underlying the whole system. So let F, curly F, be a linear space and E be its dual space. Then we define a funny bilinear form on F Cartesian product with E in such a way F1E1 is F2E2, and that's the classical duality product between E1 and F2 and E2 times F1. And the Dirac structure is then a linear subspace of E cross E, F cross E, that is self dual in this inner product. So the F's and the E's are called flow and effort. And this can also be done in the nonlinear differential geometric point of view. Then you would have a Dirac structure over manifold X is described by the tangent bundle and the cotangent bundle, and taking the Widmer sum between the two. And if you have a nonlinear system, then a Dirac structure over such a vector bundle is just if the V and the X and Vx star is a linear Dirac structure. And in this way, you can always take any autonomous port Hamiltonian DAE, and you define a flow fiber, which consists of three parts: a storage part, S, a port part for the inputs and output, and a dissipation part, D. And you partition your flows and efforts as storage, port, and dissipative, and the efforts in the same way. And then you define a Dirac structure as F plus gamma, where gamma is this matrix that we have here, the skew-symmetric part. And then you add identity and minus identity, and you link the F and the E together. And this is a Dirac structure. And then Fs is just E times X dot. Es is just that. So that sometimes it's called E or that. The Fp is the output, Ep is the input, Ed is the dissipation matrix times Fd with a minus sign. And the being in the Dirac structure is equivalent to the fact that you have a power balance equation. And there is a geometric interpretation. We have a mix of Lagrangian and Dirac structures. So we have many more results. So we can do structure preserving time discretization using Gauss-Legendre collocation method that keeps the structure. We can use the non-uniqueness in the representation using diffeomorphisms to get a robust representation. We have local and global normal forms, and we have done perturbation analysis like the distance instability or non-passivity. And in the next pages, I want to get to PDE models. So how can you generate all this to PDEs? Or the first thing you can do is you just replace the coefficients by operators. Then we have an operated DAE modeling, or you can look at the generalization of the gradient flow concepts, or you can look at formal Dirac structures, or you can look at structured PDEs with inputs and outputs. There are some references, and they are all given in the overview paper. So let me give you an abstract port Hamiltonian PDE formulation. So how do you do that? Well, you have a space Z that is in our case that the density is greater or equal to delta almost everywhere. And the space is a space of a Sobolev space W13. And the J is a skew-adjoint operator. The R is a self-adjoint semi-elliptic operator. So R is semi-definite in that sense. The input function is mapped in here via an operator B that maps from LP to LQ. And the system theoretic output is denoted by Y of Z, and E of Z is the relative energy in the system. And in our case of the hot water flow, in order to make this port Hamiltonian, you need to add an equation for the entropy. An entropy equation, and if you look at this carefully, it has the structure of a port Hamiltonian system. The variables are the density, the momentum, and the energy. The energy function is split into H of Z. That's the Hamiltonian, or the so-called ballistic free energy. And the part that comes from the entropy, which is just TW, the wall temperature, times the entropy function. And so you have a quadratic function here, and you have the entropy function here. And then the E is just written like this. The variational derivative of E you have to take, it's given by these quantities, m squared divided by 2 rho squared, the rho derivative of the H function, and the gravitational times the height, momentum divided by rho, or the variation, the derivative with respect to the energy function. So that's the gradient of the variational derivative of the energy function. And then we get the J operator, which looks like this. It's skew symmetric into the components associated with pressure, the momentum, and the energy. And that you can associate with a bilinear form. So you can go to a weak formulation, multiplying the equations here with test functions and integrating over volumes. So we get the J matrix in such a way. And the R matrix consists of two parts corresponding to the temperature loss, and that's this one, and to the friction in the pipes. And it's symmetric, positive, semi-definite, elliptic. And you define input operators and output operators. And so in this way, you get a port Hamiltonian formulation, and you have a little bit more that links it to the gradient system. So these operators J and R satisfy non-interacting conditions. So J times the derivative of S with respect to entropy function with respect to Z is 0, and R lambda times the derivative of the energy function with respect to Z is equal to 0. And then you can do the same in the hierarchy as we've done before and leave out terms and simplify, and you get a similar structure. So what else can we do with this? I mentioned already that we can do discretization, and we need discretization which preserves the structure. So you should use preservation of the Dirac structure and the constraints. And so there should be something like a discrete time port Hamiltonian system. And you just write down the Dirac structure and discretize this with collocation methods. So you just do a classical collocation method and write it down in a clever way, and then you have the same thing as we have for the continuous time system. We get that time derivative of h of ti satisfies this condition, it's like the gradient of the Hamiltonian times the x dot, and that is given by the storage inner product of ES, FS in the flow, and that is the resistive part plus the input and the output. So we get exactly the same condition for the continuous system, and then we discretize it by replacing the time derivatives by the corresponding collocation method, and we get the same condition except for the discretization error. And this is even exact if the Hamiltonian is quadratic. And let me give you a small power network example. So this is a very simple toy model of a DC power network. And so the energy is stored in the inductor and in the two capacitors, and that gives a quadratic Hamiltonian. And if you discretize this with the implicit midpoint rule, which is a Gauss-Legendre method, then you see nicely, this is the Hamiltonian, the dashed blue line, it goes to 0, and the functions after a while also go to 0 because this is a stable system. Another important point that I would like to mention with colleague joint work also with a colleague from Ankara, it's a discretization with this Gauss-Legendre method. You get a linear system, and the linear system has a special structure. It has a symmetric part, which is positive, semi-definite, or definite. And then you can show that the iterative methods that we usually have for the linear system are much better. They have a nice three-term recurrence relation, and you can prove very nice properties. And there is a method developed by Witlund and a variation by Rappaport. So you can see super fast convergence of the iterative method. If you make the step size smaller, it gets even more fast, and this has to do with the fact that the skew-symmetric part has the step size in front of it, so it's more or less like a symmetric problem. So now let me, at the end, tell you about what we've done with this for the gas networks. So we have used this to optimize the gas transport. So to find the compromise between error tolerance, computational speed, and to use them in optimization and to build a digital twin. So we took a 4-level hierarchy. I showed you this, this level here. This is the isothermal Euler equations with the real gas equations plus Kirchhoff's laws at the nodes. Then the first simplification is that we set this term here to 0 because it's in a flat area. Second model is we also take this term on ddx rho b squared, this term here, to be 0. And the third model is the second model and the stationary state. So we set ddt equal to 0. And this is a model class, and then we build an adaptive discretization method. So the first goal was minimization of simulation time. So we defined error estimates for the space discretization, time discretization, and choosing the model. We found a cost function, and then we optimized the cost function. And we could show that for this model that I showed you, the computation time could be reduced by 80%. And we could also optimize the compressor cost. So D is a discretization error, M is a modeling error, and eta is a total error. So we switched between different discretization levels and different modeling levels and optimized here the compressor cost. This is a real-world model with 40 40 edges, and this with 135 edges. And finally, this is from the district heating application. So we set an upper bound for the solid curve here. That is the upper bound for the amount of waste that we burned, and then we optimized the pressure, the power consumption at the households. So we really optimized the energy. So using the same method, and we could solve problems that with classical optimization methods we could not solve. So let me come to a conclusion. We have this wish list. And the Port Hamiltonian DAE or Port Hamiltonian PDE systems are ideal. Almost all wishes are fulfilled. But there are many things to do. Real-time control and optimization, other physical domains to incorporate stochastics in the models, stability analysis, appropriate functional analysis, error estimates, preconditioning for the solvers, database models, uncertainty for quantification. And at the moment, we are building software for digital twins to deal with these systems. So with this, I would like to close my talk and thank my sponsors for their support. And I hope I have given you a glimpse of a new paradigm of modeling that is really ideal for real-world problems. Thanks a lot.
Really. Thank you very much for your extremely good, original and charming, and also eye-opening presentation of your professor. Is there any comment or remark regarding the presentation of the Professor Mehman? There is a question by Professor Svangöktu Aydemir, but he's writing his question in German, and actually I'm not talking.
Is it in the chat?
Yes, Professor. Is it in the chat? And maybe I can.
So I can translate. So here's Göktuğ. I have two questions. Is the Hamiltonian structure better than the others to solve energy problems? And the second question is the Hamiltonian structure is also important for aerospace. Indeed, for flow problems like in aerospace engineering, it is really nice because you stay within the physical system that you want to deal with. And the first question, because you stay so close to the physics of your problem, the structure is very much nicer to fulfill all the demands that we had in the wishing. If you are interested, there is this survey paper here, which is on archive and will appear in Acta Numerica. And this survey paper is about 120 pages, gives you a very nice overview why and where this is all used, but it's really something which needs to write another book. And there is a very nice first book on this topic here, this book by Wanderschaft and Jelzimmer, which you can download from the internet, and the same thing on the PDE setting by Jakob and Zwart. And there's a software package by Peter Breitfeld from Twente University. And so there's quite a lot of stuff that has been done already. And from this, you can get a really good, good overview. But in the meantime, a lot of further stuff has been done.
Also, another question here, dear Professor. Professor Gökhan Göksu asked that, did you face any problems by calculating the gradient in evolution of Hamiltonian?
No, the good thing is this gradient that you have here or in our more, so you model directly with the gradient. So the good thing is the modeling directly, the gradient of the Hamiltonian is really given by this matrix, this matrix function times a vector. So you don't have to compute the gradient. It is already in the modeling directly encoded. So that means you have done it before you even look at the systems. And then in the discretization, oh yeah, in the discretization, what you do is, I didn't talk about this, but so what you do is you do Galerkin projections. So maybe easier to explain here. So you put your X, your state, you put it into a finite dimensional subspace generated from finite elements or some other way. And you project and you multiply with the transpose of that from the left. And then the resulting system is again the port Hamiltonian system. So finite element discretization or Galerkin projection in general will preserve the structure. So you can use whatever technique you use anyway in standard discretization technique.
Thank you, Professor. It is a great pleasure to see you here, and thank you, Erat, for your nice and eye-opening presentation. In the program, now we will go to a break of 10 minutes. After that, Professor Ramazan Yashar will moderate the next session. Thank you, Erat.
Thank you very much.
Professor. Thank you.
Dear participants, welcome session 4 of our webinar. I'm Ramazan Yaşar, the moderator of this session. Now I kindly invite Professor Gül Tuğ from Trabzon, Turkey, to do the presentation. Open your microphone and video, please.
Okay, thank you. Thank you, Professor.
Share your screen.
Okay.
Please.
Is it visible?
And please, full screen. Can you do full screen?
Yes.
Control L.
Okay, I'm
Maybe
trying. Yes. Okay, thank you.
Okay, then the link and other facilities for the online presentation seems to be okay. It's a really great pleasure for all of us to have here Professor Tuğ for the noticeable talk on accretive surface growth by using Bezier curve fitting. Professor Tuğ, do welcome to your presentation, please.
Thank you very much. The morphogenesis of the biological beings is a quite complicated issue. According to many multidisciplinary studies, including the accretive growth of some crustacean surfaces has been made by different scientists. Capturing the outlines of 2D objects is also a substantial topic in computer-aided geometric design, and curve fitting with Bezier curves is a traditional method in this process. The elastic behavior of rods and beams, which attracts continuous attention since the time of Galileo, Bernoulli, and Oerden. Elastic curves, as a curves being in nature, has complex parameterizations. In the study, we combine all the theories mentioned above just for describing the kinematics of the growth process of real-life objects. The accretive growth of a surface in the Euclidean space is introduced in one. It is considered a generating curve R0 in plane at a time 0, and the velocity vector field Q represents the local direction and rate of the growth at each point. This velocity field gives the evolution of the generating curve and defines a surface. And let R be a smooth curve and D1, D2, D3 be an orthonormal frame attached to that curve, and we will use the Fresnel frame, and we will choose D3 as the tangent vector. And here lambda is a stretch factor. We have U and W matrices, which are the Darboux matrices describing the rotation of the local basis at a given time t, and the angular velocity of the local basis at a fixed point s, respectively. Once the generating curve and the attached frame are known, the surface can be written as this differential equation. We assume Q bar is the velocity expressed in the local frame under the assumption of the differentiability on the surface and using the orthonormality of the general basis. We have these two equations, and we can rewrite these equations in the means of components as these: a set of 6 nonlinear first-order partial differential equations for 7 dependent variables. Then the accretive surface is obtained by integrating this equation. Since we use the Fresnel frame, the Darboux matrix is in this form. Lambda is the stretch factor. The accretive surface is determined by choosing a frame, providing a structure for the growth velocity. Here we note that the velocity must have a component in the binormal direction to construct the surface. Then solving the system. In this section, we give a brief information about the planar elastic curves. A planar elastic curve is described by gamma together with specified endpoints and tangents and length, which minimizes the bending energy given by this integral. Also, the curvature of an elastica at all points proportional to the distance to a fixed line, which is called directrix. If theta is the tangent angle function of a unit speed elastic curve, then derivative of theta equals kappa, the curvature, and the curve satisfies the following Euler-Lagrange equation. For some Lagrange multipliers, lambda 1 and lambda 2, we set lambda 1 and lambda 2 as this lambda cosinus phi, lambda sinus phi. And this gives a simpler version of the Euler-Lagrange equation. If lambda equals 0, the differential equation becomes this. So the curve is part of either a circle or a straight line. If gamma is an elastica, then the scaled and rotated curve gamma bar, defined by this, is also an elastica. This is important because we make rotations and scalings while constructing the accretive surfaces. Explicit parameterizations of the elastic curves are given as follows in A, B, and C. Here, E and F denote the incomplete elliptic integrals of the second and first kinds, depending on the argument U and modulus K. And AM denotes the Jacobi amplitude function. Here we have the illustrations of the elastic curves in A, B, and C from top to the bottom. In all cases, the parameter lambda is 4. We take the elastica B as the initial curve for an example. Then we choose a growth velocity, Q. This growth velocity gives a constant growth in the rectifying plane of the initial curve at every point. Then we solve the system of PDE and take the integral. So we have this accretive surface. However, when we use an elastic curve as the initial curve to evolve and create a surface, the system of PDE given in the equation 1 is quite difficult to solve. Hence, we make an approximation to the elastic curves by using the cubic Bezier curves for obtaining polynomial expressions. This method would be very helpful in the calculations when someone needs to use the curves defined in more complex forms in the nature. The general equation of a cubic Bezier curve is determined by the Bernstein polynomials as this. Here, Kr are the 4 control points. An example is this. K0, K1, K2, and K3. The parameterization of the Bezier curve, and this is the illustration. If we change the 2 control points in the middle as K1 and K2, these 2 control points, while the start and end points remain the same, we have this curve. Now we assume that K0 and K3 are 2 consecutive points that we aim to fit, while K1 and K2 are the remaining 2 control points that we need to predict. Take gamma I as the Bezier curve that fits pi to pi plus 1, and it has this form. Now we need to determine the coefficients A1 and AB here, A1 and AB. Moreover, for the final curve to be smooth, the transition between gamma I and gamma I plus 1 must be smooth around the point pi plus 1. That means the curvatures of two pieces matches. Then we have following conditions. Since we have n curves, we need to find two n variables to determine ai and bi. However, we only have two n minus 1 equations. Therefore, we give the following boundary conditions. And we calculate the first and second derivatives of gamma I and substitute in the last two equations. We have two n equations as follows. When we eliminate all the bi by using the first and second derivatives of gamma I, then the equations become this. Matrix representation of the row system of equations is like this. And we can find the coefficients bi from the. In the light of the above method, we find the best approximation of the elastic curves with the help of the cubic Bezier curves. We give the computer algorithm related to Bezier curve fitting and the elastica and constructing accretive group surfaces as, this is the algorithm. Here we give an example. Let me choose the elastic curve given in C. I can show it. This curve is C. If we take 8 pieces, it means 16 pair of K1, K2 points. We calculate the coefficients AI and BI as follows. However, we need more pieces to obtain best results. The following figure shows the resulting curve for 8, 16, and 32 pieces, respectively. From top to the bottom, 8 pieces, 16 pieces, and 32 pieces. We define a constant growth in the direction of the binomial vector at every point. So Q is 0, 1, 0. We calculate the frame apparatus at every point on each pieces of the Bezier curves and calculate the accretive surface as a cylinder like this. Another example is this. Let we choose the elastic curve given in A. The following figure shows the resulting curve for the approximated curve for 16 and 32 pieces respectively. Blue one is the approximated curve. Choosing a constant growth in the direction of the binomial vector at every point on each pieces, then we have the accretive surface as a cylinder again.
You have 2 minutes left.
Okay. The unwanted rotations of the frame at the inflection points. Here at the inflection points, binomial vector changes its direction. So it can be removed by choosing the attached frame as a rotation minimizing frame. It can be determined the error between the methods of the original form and the Bezier curve fitting. The growth velocity can be developed to more complex forms such that it includes rotations and scalings. We chose growth velocity as constant in our examples, but it can be developed. Hence, the growth of more complex structures may be explained. These are the references. Thank you for attention.
Okay, we thank the professor for her nice talk. If there is any question or comment, please use the question and answer button. Also, we check here. Okay, it seems there is no question or comment. So we thank again to Professor Tu. So stop your screen sharing, please.
Okay.
We have about 2-3 minutes for the next presentation. Dear participants, now I would like to invite Professor Özgür Keskin from Ankara, Turkey, to do the presentation. Open your microphone and video, please. Professor Keskin.
Hello.
Hello. Share your
Hello.
screen, please.
My name is Özgür Keskin.
Okay, stop. First of all, share your screen, please. Open your presentation.
Yes.
Be patient. Okay. So please, full screen, though. Yes, okay. So the link and other facilities seems to be okay. It's a great pleasure for all of us to have here Professor Keskin for the valuable talk on closed space-like ruled surfaces, thanks to rotation minimizing frames. Professor Keskin, do welcome to your presentation, please.
Thank you very much. My name is Özgür Keskin. I finished my PhD on June 18, 2020. Right now, I'm also working on the article again. In this presentation, integral invariants that are the pitch and the angel pitch of any k plus 1 dimensional closed space-like ruled surface are computed considering any rotation minimizing frame in 4-dimensional Minkowski space. This presentation is consisted of three fundamental sections. Firstly, introduction. The rotation minimizing frames that are connected with any space curve are available for producing sweep surface by actioning a profile curve throughout a path. Also, the rotation minimizing frame concept has emerged at the same time that the Bishop frame concept has introduced. So the first publication on this frame is thought to be 4. Since then, the calculation of this frame and its consequence on sweeping surface have been discussed in several notable articles. In differential geometry, the ruled surface is very worthy in the examination of kinematics or spatial mechanism. Some of the studies on ruled surface are as follows. The definition of the vector they express as a dual Steiner vector is given in 1 variance closed spatial moments. In this study, initially, integral invariants that are the pitch and the angel pitch of any K1 2-dimensional closed space-like ruled surface are computed considering any rotation minimizing frame in 4-dimensional Minkowski space. In the first case, any K1 2-dimensional closed space-like ruled surface is created according to the RMF that is obtained by taking the time-like vector files of the A3 vector files of the Frenet vector files of this space-like curve and the orthogonal trajectory of this surface, the angel pitch, and the pitch are calculated. In the second case, K plus 1, the dimensional closed space like ruled surface is created as regards the RMF that is obtained by taking the timelike vector files of the A1 vector files of the Frenet vector files of this space-like curve, and the orthogonal trajectory of this surface, the angle pitch and the pitch are figured out. Finally, all the obtained states are generalized to the n-dimensional Minkowski space, and all cases are examined as two states. Next, the calculations are shown in an example. Our aim in this study is to calculate the angle pitch and the pitch of the closed ruled surface in high-dimensional Minkowski space with the help of RMF. In the light of such information, it has been manifested the integral invariance can be computed more smoothly by means of the RMF. Preliminaries, the Minkowski for space is the real vector space supplied with the standard flat metric given by, due to the fact that H is an undefinite metric, if satisfies a vector is called as a space-like or time-like or null light-like. Also, the norm length of a vector is defined by and the norm and two vectors said to be orthonormal when G UK UV is equal to 0. We will give two cases of the Frenet frame for the four-dimensional Minkowski space. Other situations can be expressed similarly. Suppose that the Frenet frame also A3 is the unique time-like unit vector files. This Frenet frame formulas. Suppose that Frenet frame is the Frenet frame throughout any unit space-like curve. A1 is the unique time-like unit vector files. This Frenet formulas. Definition 1.1. Let R is equal to RT be any normal vector files on any curve. Is RT is called a slightly parallel or rotation minimizing frame. Suppose that is any curve T N NIT, I is equal to 1 blah blah blah n minus 1. Provided that the initial basis A1 T0, A1 A2 T0, AK T0 is given, then basis the Frenet frame satisfying AMT ANT inner product delta MN and is satisfied. Let phi t let this equation be k plus 1 dimensional ruled surface in Rn if the requirement pct plus p is equal to PCT is provided to real numbers, P is greater than 0, then the surface is said to be any closed ruled surface. Is this orthogonal trajectory at PCT the Freyvenus between gamma t and gamma t artı p is said to be pitch of x. Suppose that PC is any closed ruled surface of dimension k plus 1 in Rn, and the vectors of a1, a2, ak are unit ruler vectors of producers at the point PCT. Also, suppose that ak1t displays the unit tangent vectors of orthogonal trajectory at PCT. ak1, k plus 2, k plus 2, k plus 1 t and k plus 1 t plus p is said to be the angle of the pitch of x and is shown by theta t. Here ak plus 1 t plus p, which is the tangent vector of the orthogonal trajectory at PCT plus p. P is period of PC. The integral invariance of x. The integral invariance as grades and RMF in Minkowski space. In this chapter, the integral invariance of any closed space-like ruled hypersurface and computed with the help of an RMF in Minkowski space. We first give the formula of the RMF in order to calculate the integral invariance of any k plus 1 dimensional closed space-like ruled surface. In addition, we stated the RMF for two conditions for space-like curves in a Minkowski, four-dimensional Minkowski space. The RMF for other conditions can be expressed similarly. The integral invariance of the closed space-like ruled surface obtained for other conditions of the RMF can also be calculated. This equation RMF.
2 minutes left. We have 2 minutes left. Professor Keskin, do you hear me? Professor Keskin, do you hear me? Okay, I think we have no connection with her. So next section, next presentation will be in 5 minutes. We will have a break. Okay, I think Professor Keskin couldn't be able to reconnect to our webinar. So I would like to thank to her, Professor Keskin, for the talk. Now, okay, I would like to kindly invite Professor Teslim Meryem Baran from Kayseri, Turkey, to do the presentation.
Yes, I am here.
Open your microphone and video, please.
I open.
Yeah. Share your screen, then full screen, please.
Okay.
The link and other facilities for the online presentation seems to be okay. It is a really great pleasure for all of us to have here Professor Baran for the noticeable talk on closeness, sobriety, connectedness, and compactedness in the category of constant limit spaces. Professor Baran, do welcome to your presentation, please.
I will talk about closedness, sobriety, connectedness, and compactness in the category of constant limit spaces. In this paper, we characterize closed and strongly closed subset of constant limit space. And we characterize each of T0, T1, T2, and compact constant limit space. Some results for various forms of subconstant limit space and investigate the relationships among these forms. We characterize various forms of connected constant limit spaces and examine some invariance properties of them. We'll compare our results with some known results in some topological categories. And we present its extension theorem and Yusuf's lemma for constant limit spaces. And I will give a little history. In 1937, Cartan introduced the filter, and 1948, Chakat used them, developed the theory of convergent space, and 1966, Beans and Killer defined the limit spaces. And 1981, Stoy used the T0 separation axioms in Lambda calculus programming language. And in 2009, Jandit used the T0 separation axiom in algebra topology. And in 1991, Baran defined pre-Hausdorff space along with T0 and T1 are being used to define separation axioms T2, T3, T4. Also, pre-take objects have an application in the theory of geometry realizations, their associated intervals, and corresponding homotopy structures, and sigma algebra. In 1987, Digrangen and Julie introduced the closure operators. They have been used all branch of mathematics. The usual notion of closeness is being used to define topology concepts such as T2, T3, T4, and compactness, perfectness, and connectedness in topology categories over sets. The subspaces introduced in 1971 and studied by several authors, and in 2022, in this year, Baran and Ebu Halvar gave various forms of sub-objects in the topology category and investigate relationships among these various forms. Why top is not necessary because top is not Cartesian close. The product of quotient function need to be quotient function. Quotient functions are not hereditary. Uniform convergence coefficients uniform as complexes don't exist. The by constant limit space, the category only of constant limit spaces is Cartesian closed and hereditary topology category such that products of quotients are quotients. The definition is definition of topology category and constant limit spaces. Let's be non-empty set. F be the set of filters on B. Key is a function satisfied following conditions. First condition is for each x in B, stack x in Kx. Second condition, if alpha in Lx and beta contain alpha, then beta in Kx. And if alpha beta in Kx, then intersection in Kx. And we call Bk is a limit space. If K constant function, we call Bk is a constant limit space. The theorem has initial lift, final lift, discrete structure for constant limit spaces. In 1991, Baran gave these maps and those maps, and he used those maps defined to closed and strongly closed, and strongly closed. If the initial lift of the used source infinity and delta A infinity is discrete, then one point set A is said to be closed. If x divides M is T1 at star, then M is said to be strongly closed. And also he gave those maps. A is principal maps, S is discrete maps, and delta is folding maps. And he used to these maps definition to T0, T0 bar, T0 prime. If the initial lift of the U source A and delta is discrete, then X is called T0 bar. If the initial lift identity and delta is discrete, X is called T0 prime. If X doesn't contain an indiscrete subspace with 2 points, then X is called a T0 object. It is many. If the initial lift, the U source S and delta is discrete, then X is called T1. If the initial lift of the U source A and C agree, then X is called Hausdorff bar. If the initial lift U source final lift of the U thing injection maps agree, then X is called Hausdorff prime. X is T2 bar if and only if X is T0 bar and Hausdorff bar. We proved let Bk be constant in space. Bk is T0 bar if and only if T0 prime, if and only if T1. Bk is T0 if and only if B empty and B the one empty point set. And pre-Hausdorff bar if and only if pre-Hausdorff prime, pre-Takey bar if and only if pre-Takey bar. For the category type, all of the T0 bar, T0 prime, and T0 are equivalent, and they reduce to usual T0 separation axioms. Let 0 prime A be the full category, full subcategory of A consisting of all T0 prime and objects of E. We get this full subcategories are pairwise isomorphic categories. And closure operator, let Vk be constant limit space and F subset B. CLF is called closure of F, the same as CL is called strong closure. C, the other definition, C be a closure operator of E, 1, E0, C, it means T0, E1, C, it means T1, E2C, it means T2. Each constant limit space Vk is conlim 0, 1, 2 STL and conlim 0, 1, 2 STL are isomorphic of conlimit. And we investigate a relationship among those categories. They are equivalent subsets and they're equivalent. And some other researchers study another categories, con-FCO, constant filter converse space, filter converse space, Born-logical spaces, pre-order space, convergent approach space, limit space, and PQSUMET, a category of extended stochastic metric spaces. Subconstant limit spaces, UB topological functor, and X is said to be irreducible if M and R closed subobjects of X, and X, M union N, then M is X or N is X. X is called quasi-subr if every non-empty irreducible closed subset of X is the closure of a point. X is called T0 bar subr if X is T0 bar and quasi-subr. T0 prime subr if X is T0 prime quasi-subr, and T0 subr if X is T0 and quasi-subr. And we proved the following are equivalent. A constant limit space Vk is a quasi-subr, T0 bar subr, T0 prime subr, irreducible. And the following are equivalent T0 subr, B empty or B is a one-point set. And the other categories.
2 minutes left.
Okay. Connect the constant limit space, use topological functor if the only subsets of X, both strongly open and strongly closed, are X and empty, then X said to be connected. X both open and closed, X said to be strongly connected. If any morphism for X to any discrete object is constant, then X is said to be deconnected. And we proved the following are equal. A constant limit space Vk is connected, deconnected, and STL connected. In the conlim we have connectedness, deconnectedness, STL connectedness are equivalent. Implies strong connectedness if and only if CL connectedness. Compact constant limit space UB topologic functor if the image of each closed subobject of E is a closed subobject of B, then F is said to be strongly closed. If projection maps close for each object B in A, then A is a compact. And we proved constant limit space is compact if and only if it is strongly compact. And its extension theorem for constant limit space. If BK is a T0 bar constant limit space and AL in non-empty closed subspace of BK, then every morphism F has an extension morphism where R is the set of real numbers and S is any constant limit structure on R. Finally, Eurozon's lemma for constant limit spaces. Suppose BK is a T0 bar, constant limit space, and M and R a non-empty disjoint subset of B. Then there exists the morphism F, where the 0, 1 is the unit interval and L is any constant limit structure on 0, 1, such that Fx is 0 if X in M and Fx in 1 if X in N. Thank you for listening to me.
Okay, we thank you, Professor Baran, for the valuable talk. If there is any question or comment, please use the question and answer button. Let me check. Are there any questions? Okay, it seems there is no question or comment. So we thank again to Professor Baran. Stop your screen sharing, please.
Yes, I stopped.
Okay, for the next presentation, we have about 5 minutes. Dear participants, now I would like to invite Professor Ayşenur Altıntaş from Karabük, Turkey, to do the presentation.
Hello, I'm Ayşenur.
Hello. Open your video, please.
Your webcam, right?
Yeah, yeah.
Okay, I'm
Please.
opening.
Share your screen. Green button. Please full screen open your presentation. That's okay. The link and other facilities for the online presentation seems to be okay. It's a great pleasure for all of us to have here Professor Altıntaş for the valuable talk on a new hypercube-like graph. Professor Altıntaş, do welcome to your presentation, please.
Hello, thank you. I'm Ayşenur Altıntaş from Karabük University, and Burhan Selçuk is my advisor. I will present you a new hypercube-like graph. This is our work. As contents, first I will first introduction, then preliminaries about the graph I will present, topological feature of this graph, and labeling algorithm on this graph, comparison result, and at the end, the conclusion. The graph is used as mathematical model in many branches of science. The graphs are a collaborative research field of mathematics and computer science. Actually, I'm in computer science department. Hypercube graphs are used in computer architecture, radar systems, construction of networks, or sorting genetic algorithms for land use. Actually, this has many different use. Many hypercube-like graphs have been described in the literature so far. In this study, a new hypercube-like graph topology is introduced, motivated by Karji and Selçuk's study. For this, two different definitions will be given. The first definition is derived from the union of a certain number of squares with a common side in two-dimensional space, and the second definition is derived from combining two squares or two connected square graphs obtained by a recursive process. Recursive process is important here. We can construct this graph with using recursive process is our main advantage. This new hypercube-like graph is called connected square network graphs, CSNG. The close Hamiltonian paths of the new hypercube-like graphs are found with the help of the gray code in 9. And then these graphs are proved to be Hamiltonian graph. A labeling algorithm finds the Hamiltonian path for this resulting graph. We are using gray code for the labeling. The important graphical connectivity indexes of a new hypercube-like graphs are calculated as 10, and finally conclusions are given and the projection for the future work is presented. For the rest of the study, G is our graph, and V is a vertex set, and E is an edge set. XY is an edge in E, where XY is the element of this graph, and the degree of the vertex X is denoted by DEGX degree X, and DXY is the shortest path from XY in this graph. For the concatenation of two strings, we will use this symbol. The Hamming distance is calculated with using bitwise XOR operation. This bitwise XOR operation actually give the number of different bits between these two nodes. We will see this in the labeling. S2 is denoted as square in 2D space, and 2D coordinate system is given below in figure 1. Two-dimensional coordinate space is X and Y. Two different definitions is given to obtain these graphs in this section. For the first definition is construction of the CSNG graph. For the case 1, construction in one direction. We have two directions as you see here, X direction and Y direction. For this construction, we can use both X direction or Y direction. For this one, for this case 1, I'll show you the construction along the Y direction. Suppose 2 to the power, sum of 2 to the power I starting from 0 to m. This denotes the number of the squares in the graph CSNG 0m. And these squares are common with two nodes. These two nodes or edges are connected along the y-axis. This graph will be called CSNG 0m. If the direction is x direction, then our graph will be CSNG m0. For example, the mesh structure given in figure figure 2a and b. For this one, CSNG 00, actually this is square, two-dimensional hypercube also. And CSNG 01 is like this. We are constructing the network, our graph along y direction. For this one is CSNG 02. For second case, the construction in two direction. This is, for example, CSNG 12. We construct this CSNG. For example, for this CSNG 12 is obtained by combining three CSNG 02s, which have top and bottom horizontal surfaces to be in common, like this. For the first line, the bottom line is same, connected with the second line top edge, and bottom of the second squares are common with the third squares top lines. Here, actually, the number of the lines here is equal to 2 to the power, sum of the 2 to the power I. I is starting from 0 to k, and with common lower and upper surfaces are connected along the x-axis this time. This graph will be called CSNG Km. For the second definition, two CSNG Km-1s can be merged to construct an image of size doubling the size of CSNG Km. There are two situations here. If doubling dimension is x, then the nodes NS in CSNG K-1m and CSNG K 0 concatenate with CSNG K-m and 1 concatenate with CSNG K-1m are also included in this graph. Let me show you. For example, in the x-axis, for base step, this is square. When we are constructing CSNG 01, we are using two CSNG 00, 1 and first and second CSNG 00. For CSNG 00, we are adding 0, bit 0 to the labeling, starting off the labeling, 0, 0, 0, 0, and labeling is 0, 0, 0, 1, 1, 0, 1, 1. For the second one, we are concatenating bit 1 to labeling of the CSNG00. Actually, this is the reflection of the first one. That means 00 here, the 00 is here, the other side. For this one, 01 is here. Like this is a mirror, we are reflecting and putting 0 at the beginning for the first one. And for the second one, we are putting 1 bit, concatenating 1 to the labeling of the second square. And we are connected these two nodes. As you can see, the difference here is 1 bit, only 1 bit difference here. It's same for the second case. This time we are doubling the dimension in y coordinate. This time y coordinate will be acting like a mirror, and we are reflecting the square or our network along y-axis, and we are putting labeling, concatenating 0 for the first one and 1 for the second graph at the beginning of the labelings, and connecting these two graphs with using these nodes, and these nodes, the difference between these nodes will be 1 bit. Here, as you can see, this is also another example. When we are constructing CSNG02, we are using reflecting plane as X plane. We reflect this according to X axis, and we are concatenate bit 0 of the first graph, and for the second graph.
2 minutes left. We have 2 minutes. Yeah.
Really?
Really?
For the, I'm sorry, construction, as you can see, this is also construction for the CSNG 1 and 2. For the topological feature, actually we can see Hamilton features while labeling, and for the theorem, we are calculating the number of the gray codes. As you can see, for the basic step, hypothesis, and final steps. Sorry, I talked too much actually, so I can't finish. We are calculating according to theorem. We are using mathematical induction, nodes and edge node numbers, total number of edges, and like this. We prove this with using mathematical induction. For the labeling algorithm, as I mentioned before, we are adding 0 and 1 and using inverse graph. We are finding labeling for each graph. Here, for the algorithm, we use 2 for loop, 1 loop inside another loop, and the running time of the algorithm is km. For the comparison result, we are finding node degrees and total number of degrees and the relation of the edges according to degree nodes. And we calculate some connectivity index according to general sum connectivity index with using degrees of these nodes. And we found the functions like this, result like this, and also we calculate Rundic index. In conclusion, in this paper, connected square network graphs are introduced, and 2 different definitions are given to obtain connected square graphs. The topological features of the graphs have been investigated, and the graphs can be thought as hypercube variants, and the labeling algorithm is given that reinforces the idea. Thank you for listening. If you have any question, you can ask.
Okay, we thank to Professor Altuntaş for the absolutely nice talk. If there is any question or comment, please use the question and answer button. Let me check. Here are there any questions? So I have a question. You said last pages, you use some algorithm there.
Yes, this is the algorithm for labeling.
Which programming you are using here?
Actually, this is pseudocode, but you can use any programming language. You can use C++ or C#, also Python. You can implement with using any
programming language.
Yes.
Okay, thank you. It seems there is no other question or comment. So we thank again to Professor Altuntaş. Stop your screen sharing, please.
Thank you for the listening. Let me.
Okay. We have about 3 minutes for the next presentation. Okay, now I kindly invite Professor Ayla Erdulkara from Tekirdağ, Turkey, to do the presentation.
Yes.
Open your video, please.
Okay.
And please, full screen sharing. Control plus L, maybe you can do.
Okay.
Good. The link and other facilities for the presentation seems to be okay. It's a really great pleasure for all of us to have here Professor Kara for the noticeable talk on investigations on singular minimal hypersurfaces in Lorentz space. Professor Kara, do welcome to your presentation, please.
Thank you. Before starting, I would like to thank those who contributed to the organizations of this webinar for giving us the opportunity to speak in such a beautiful organizations. Before giving the mathematical definition of singular minimal surface, let's talk about the architectural shapes of such surface. This surface appear as structures called domes. Historically, the shape of a dome has been of great interest. The construction of the domes involves a complex interplay of artistic and structural issues that require the architect to determine various variables such as the choice of materials and the desired stylistic effect. The main engineering problem to be solved is to construct a structurally sound, aesthetically appealing roof that rises over a large empty space. To achieve these, architects need the support of science. For this reason, it is of great importance to examine the domes geometrically. Thus, the first condition to be considered is that the dome is standing along its boundary by its own weights. Accordingly, inference about domes can by integrating it with a limited large homogeneous piece, a cloth whose boundary is represented by a predetermined fixed curve. The part supported by this curve turns into a static equilibrium under the force of gravity. The fabric's surface is closely related to that of the dome because a surface suspended solely by its own weight, subject to tensile forces on tangential to its interior. When the surface is inverted, it produces the optimal shape of a dome. Reversed converts the piling force into a compression force. The inverted surface satisfies the same equilibrium equation as the original surface, so the main problem can be shaped as follows. What is the shape of a flexible hanging surface of uniform mass on which only gravity acts? Consider the one-dimensional analog of the above problem, that is when the problem is reduced to the problem of determining the optimal shape of hanging cable. The answer is the catenary with the simple expression yx for a positive constant a. The catenary has the property that its center of gravity is lower than that of any curve of equal length and with the same fixed endpoints. Catenaries have been important field of study for mathematicians and they have an important place in determining of optimal shape of arcs. For more detailed information about catenary, see these references. Some of the studies investigating the shape of surface hanging under their own weight are
this. Therefore, with arrow definition, the following definition can be expressed. A surface determining only by its own weight is called a singular minimal surface. Now, let's define it mathematically. Let x, y, z denote the canonical coordinates of the three-dimensional Euclidean space and z vertical direction. Consider gamma a closed curve and a big zero, a fixed positive number. We construct the differential equation that parameters a surface spanning gamma with area A suspended from gamma by its own weight. Assume that M is made of a flexible, incompressible material of equal density Phi per unit area. Let M be given by the graph of a sigma differentiable function defined on sigma. Under the influence of weight, surfaces M reaches an equilibrium point when the weight of the center of gravity is a local extremum. Suppose the gravitational potential at a point x, y, z is the distance z to the xy plane. The height of the center of gravity is equation 1. We can suppose that A and B take the value 1, where sigma x, sigma y are partial derivations of sigma with respect to x and y respectively. Euler-Lagrange equation of equation 1 is equation 2.
2 minutes left. 2 minutes left.
Oh.
Please.
Since we are no. Since we are concerned with smooth surfaces, we only consider non-zero functions sigma in equation 2. I give the results. Basic definition. Let's R1 M plus 1 be endowed with the canonical Lorentzian metric. Let Phi be a smooth immersion of an oriented time-like hypersurfaces. Xi unit normal vector field and H mean curvature. Let Y non-equal 0, a space-like vector non-parallel to Xi. Then Mn is called singular minimal hypersurface with respect to Y if satisfies this equation. We have problem finding cylindrical singular minimal hypersurface in Lorentz spaces. We skip. As a result, the only singular minimal cylinders in R1 M plus 1 with respect to a horizontal space-like vector Y are either the hyperplanes parallel to Y or cylinders whose generatrix is alpha Lorentzian catenary and the Rollings orthogonal to Y. Problem 2. finding singular minimal translation hypersurface in Lorentz space. And as a result, we find singular minimal translation hypersurface with respect to a horizontal space-like vector y, then it is either a hyperplane parallel to y or a cylinder whose the generatrix is alpha-Lorentzian catenary and the Rayleigh stretch lines orthogonal to y. And finally, consider time-like surfaces being invariant a uniparametric group of translations. In this form, we have the only singular minimal cylinders are in R1, 3 with respect to a horizontal space-like vector y are either the plane parallel to y or cylinders whose the generatrix is alpha-Lorentzian catenary and the Rayleighs orthogonal to y. Other problem, finding singular minimal affine translation surface in Lorentz spaces. An affine translation surface R1, 3 has one of the following graphs, where f and g are smooth functions, g non-equal 0. And as a result, singular minimal graph with respect to horizontal space-like vector y of the form f this, then it is either a parallel plane to y or a cylinder whose the generatrix is alpha-Lorentzian catenary and the Rayleigh straight lines orthogonal to y. And these results satisfies in this form time-like surfaces. And this forms singular maximal graphs with respect to horizontal vector y1, 0, 0. Then f equal constant and this equal. Many thanks for your attention.
Okay, we thank you, Professor Kara, for the talk. If there is any question or comment, please use the question and answer button. I will check. Are there any questions here? No. It seems there is no question or comment. So we thank again to Professor Kara.
Thank you.
Stop your screen sharing, please. Okay, we have about 5 minutes for the next presentation. Okay, on the behalf of organizing committee, I would like to thank all participants for their patience and attending session 4. Next session will be start in 5 minutes, about 5 minutes, and be moderated by the Professor Talha Arkan. Thank you.
Dear participants, welcome to this section. I am Talha Arıkan and I will moderate this section. For the first talk, I can kindly invite Professor Patel from India for presentation. She's gonna talk about structure of FQR linear theta delta theta cyclic codes. Please share your screen, Professor Patel.
Hello. Is it visible?
Yes, it is good. Please make it full screen. You can use Ctrl+L. Yes, everything is fine. You are welcome to present your study.
Okay. So, hello everyone. Myself Shikha Patel from Department of Mathematics, IIT Patna, India. My title of presentation is Structure of FQR Linear Theta Delta Theta Cyclic Codes. So these are outlines of my presentation. First of all, I will discuss some basic definitions like linear codes, Hamming distance, dual code of a code, and cyclic codes. After that, our main work, FQR linear theta delta theta cyclic codes, its construction, theta delta theta cyclic codes are in R, then FQR linear theta delta theta cyclic codes, and then finally grammar for the construction of optimal codes. For linear codes, let F2 be the finite field and F2n denotes the set of all ordered tuples represented like in this way A1, A2, An, where each AI is coming from F2. The elements of F2n are called the vectors or words. A linear code over F2 is the subspace of F to the power n for some positive integer n, and a subset C of F to the power n is linear if and only following these two conditions will hold. That is, its linear sum is in C and its scalar multiplication is again in C. For example, suppose C is a code consisting of these elements, then we can see that this is a linear code over the finite field F2. Now the Hamming distance between any two code words X and Y of C is the number of positions in which these two vectors will differ, and it is denoted by pxy. Further, the minimum distance of a code C is the minimum of the minimum Hamming distances between any two distinct code words. For example, let's see with a set consisting of these vectors, then we can see that the minimum distance of the code C is 2. Now, if C is any k-dimensional subspace of F to the power n, then it is an NK code, and if we also specify the minimum distance, then it is an NKD code. Dual code of a code, for this we consider the inner product of two vectors V and V in F to the power n. This is a scalar defined as U1, V1 plus U2, V2 and so on. U1, V1. If its inner product is 0, then these two vectors will be called orthogonal. For a linear NK code C, its dual is denoted by C perp, and it is defined as the set of those vectors of F to the power n which are orthogonal to every code word of C. For the cyclic code, this is a linear code, and also any cyclic shift of a code word is as in a code word. That is, if A0, A1, An minus 1 in code word is in C, then its circular shift An minus 1, A0, A1 and so on, An minus 2 is also in C. For the construct, to discuss the algebraic properties of a cyclic code, we must identify a vector A0, A1 in F to the power n with the polynomial AX, which is defined as A0 plus A1x plus and so on, An minus 1x to the power n minus 1 in this quotient ring, F2x modulo x to the power n minus 1. That is, we can always view a code as a subset of F to the power n as well as a subset of Rn. So, for the construction of cyclic codes, we consider the set generated by fx, that is, this is the set consisting of the all multiple of fx where Rx in Rn. For example, suppose C is a code generated by 1 plus x square in R3, where R3 is F2x modulo x cube minus 1. So, we can generate a code by just multiplying 1 plus x square by each 8 elements of this ring R3. So, here we get only 4 distinct code words 0, 1 plus x square, and x plus x square. This is now from the algebraic and combinatorial structure, we can easily get the code C. In the terminology of ring theory, we can say that these cyclic codes are ideal in Rn, and these ideals are principal ideal that is generated by a single element. Now, cyclic codes are constructed over the competitive structure. Now, people are continuously searching for the structure or the technique where we can improve the Hamming distance, that is optimize Hamming distance. For this, we are considering a non-competitive setup. For this, we consider a set Rs theta where theta is an automorphism. This set form a ring under the usual addition of polynomials, and multiplication is defined as axi star bxj is equal to a theta to the power I b x to the power I plus j. This is a non-competitive ring unless theta is identity. A linear code C of length n over R is said to be skew-cyclic code under this automorphism theta if and only for any code where C in C its skew-cyclicity is again in C, that is defined as theta Cn minus 1, theta C0, theta Cn minus 1, theta Cn minus 2 is again in C. This is the progression of the coding theory. So firstly, linear codes were studied over the binary field. Then in 2007, Boucher et al. Investigated skew-cyclic code, that is the cyclic codes over the non-competitive structure, and these are investigated further in 2009, and in 2010 Boucher et al. Studied Z2Z4 linear code, that is the codes over the mixed alphabet. In 2014, Abulab again investigated Z2Z4 cyclic codes and derived its dual also. In 2000, et al. Analyzed the additive cyclic codes. Additive codes over this structure Z to the power S, Z to the power R, Z to the power S in general, and further they analyzed over the mixed alphabet with three alphabets Z2, Z4, and Z8. Further, in 2020, apart from these works, Belcam et al. Studied codes over the mixed alphabet in the non-competitive setup. Now, these works are in the non-competitive setup, but here we will also consider the skew polynomial ring with both theta and derivation. So, Gauss and Laurie studied sigma delta codes and introduced the notion of F sigma delta codes. In 2014, Boucher et al. Studied linear codes by using the polynomial rings with the help of both automorphism and the derivation. In 2018, Sharma et al. Investigated these skew-cyclic codes with the derivation over this particular ring, and in 2021, Amma et al. Studied sigma delta skew quasi-cyclic codes over the same ring. Recently, in 2021, Patel and Prakash studied theta delta theta cyclic codes over this ring via the decomposition method. Now here we will study the theta delta theta cyclic codes over the mixed alphabet FQR. For this, we consider a ring FQ U modulo U square minus 1, and let's see the linear code of length n over R, and these C1, C2 are the linear codes of length n over FQ, and mu1, mu2 is defined like this way. These mu1, mu2 are the idempotent orthogonal decomposition of this ring. That is, R can be decomposed as mu1 FQ direction mu2 FQ. That is, any element of R can be represented like this way. R is equal to mu1 u1 plus mu2 u2, and C is represented as mu1 c1 direction mu2 c2. So now we will define the theta derivation. So this is, if these two conditions will hold, then this map delta theta is a theta derivation of R. We consider here the set F2 as theta delta theta. Then this ring is a non-competitive ring under the usual addition of polynomial, and multiplication is defined like x is equal to sigma ax plus delta a, here a belongs to FQ. Further, we extend this to this in general over the ring R, where theta is the Frobenius automorphism of R defined by theta of a plus ub is equal to theta a plus u theta b, and delta theta is a theta derivation of R. We define a map delta theta in this way. Delta theta a plus ub is equal to 1 plus 2 theta of a plus ub minus a plus ub, and consider the set FQR AS, where A is coming from FQ and S belongs to R. This is, we can see that this is a ring but not in general R modulus structure under the usual addition. So for this, we consider a map xi from R to FQ, xi R is equal to A, and introduce the R scalar multiplication on this ring FQR. That is, star is defined from R to FQR defined by R star AS is xi R A RS. Then it is verified that this ring R is an R module under this defined multiplication. So we can also extend this multiplication to FQ rho cross R tau. A non-empty subset C of FQ rho cross R tau is said to be an FQR linear code of length rho plus tau if C is an R sum module of this ring. Now we define the inner product between T and T dash, which is defined as U summation I is equal to 0 to rho minus 1 ai dash plus summation j is equal to 0 to tau minus 1 sj dash. So CPerf is defined as t dash is any element in this ring such that t dash is equal to 0 for all. Sorry, here t dash belongs to C. For all t belongs to C. Now we consider this ring R rho tau defined as f modulo ideal generated by f to the power rho minus 1 and Rx theta delta theta f to the power tau minus 1. Now we consider two polynomials Ax in this ring and Sx in this ring. Now we identify this code word in this ring f2 rho R tau with the polynomial of this form. Cx is equal to Ax, Sx belongs to R rho tau. Then the multiplication star in R rho tau is defined as follows: Rx star Ax Sx is equal to xi Rx Ax Rx Sx. Now this ring Rx theta delta theta ideal generated by Fx is the left, Rx theta delta theta module under this multiplication Rx Ax plus ideal generated by Fx is equal to Rx Ax plus ideal generated by Fx. A code C of length tau over the ring R is said to be theta delta theta linear code if it is left Rx theta delta theta sum module of this quotient ring. And a code C of length tau over R is said to be theta delta theta cyclic code if C is a theta delta theta linear code, as well as if for any code word C belongs to C, its T theta delta theta cyclic shift is again in C. Now let's see be a linear code of length tau over R, where C1 and C2 be linear codes of length tau over F2, then C is a theta delta theta cyclic code of length tau over R if and only C1 and C2 are theta delta theta cyclic codes of length tau over F2. Further, if C is a theta delta theta cyclic code of length tau over the ring R, then C is generated by mu1 f1x, mu2 f2x, where f1 and f2x are the generating polynomial of Ci corresponding to the finite field F2, and its cardinality is q to the power 2 tau minus summation I is equal to 1 to 2 degree of phi x. And let's see here theta delta theta cyclic code of length tau over R, then C has a generating polynomial fx, which is a right divisor of x to the power tau minus 1 in this ring Rx theta delta theta. And now we will extend this work to in mixed alphabet, that is F2 R linear theta delta theta cyclic codes. A code B is said to be F2 R linear theta delta theta cyclic code of length rho plus tau if B is an R2 module of this ring, as well as for any code word A in B, that its T theta delta theta cyclic shift is again in B. Now for we consider an F2 R linear code B of length rho plus tau. We define two sets B1 and B2 in this case, where Ci's are defined as in previous slides for I is equal to 1, 2. Also an F2 linear code B of length rho plus tau can be represented. That is, we can always decompose this code B over R into over F2. That is B1 plus mu2 B2. This is also an idempotent orthogonal decomposition. A code B of length rho plus tau over F2 R is the theta delta theta cyclic code if and only gives the left Rx theta delta theta sum module of this ring R rho tau.
2 minutes left, Professor.
Yeah. Okay. Let B be an F2 linear code of length rho plus tau, where B1 and B2 be linear codes of length rho plus tau over F2. Then this code B is an F2 linear theta delta theta cyclic code of length rho plus tau if and only B1 and B2 are the corresponding theta delta theta cyclic code of length rho plus tau over the finite field F2. Let B be an F2 linear theta delta theta cyclic code of length rho plus tau. B is generated as this left Rx theta delta theta sum module of rho plus tau, and also this is generated by this polynomial fx, which is a right divisor of x to the power tau minus 1, and gs is a divisor of x rho minus 1. Now we define the gray map for, that is any arbitrary element of ring R is represented as R1, R2 in F2, and we also any element of F2R is represented as A slash this R1, R2, and let GL2F2 be the set of all 2 cross 2 invertible matrices, and we define a gray map phi from R to F2 as follows: A plus UB goes to A comma B into L, where LL transpose is equal to gamma I2, and I2 is the identity matrix matrix of order 2. We can also extend to now we define the Gray map for the mixed alphabet, that is phi from FQR to FQ3 as follows. AR is equal to A, R1 and R12. We can also extend this map to component wise over this ring F2 row R tau. We can easily extend it to component wise. So this Gray map phi is an F2 linear map and distance preserving from F2 row R tau to F2 row plus tau. That is this also preserve the distance distance to Hamming distance. If C is an R row plus tau k DL F2R linear code, then phi C is the row plus tau KDS linear code over F2. This was under progress. These are the references. Thank you.
Thank you, Professor Patel, for this nice presentation. Is there any question or comments? So we have a question from Professor Turan. So she asked, what is the Q in this ring?
Q is some prime power. Here P is odd prime. Actually, because mu1 and mu2 is defined as 1 plus u by 2 and 1 minus u by 2. So Q is any prime power. That is Fq we are considering. Fq is a finite field. So Q must be some prime power and P is an odd prime here. Because its decomposition is mu1 and mu2 and it is defined as 1 plus u by 2 and 1 minus u by 2. So it is always odd prime.
So thank you, Professor. Is there any other question? So we have another question. What about the generator polynomial of FPR?
So here we can always generate a code B in FQR like this way. Here FF means this is the generating polynomial for this code B, that is FQR linear code. Fx is mu1 f1x plus mu2 f2x, where fx is the right divisor of x to the power tau minus 1 and gx is the divisor of x to the power rho. Means this is generated by this form mx fx. Means these two polynomials. This is not singly generated actually. This is generated by gx comma 0 and mx comma fx, where fx is coming from our original code, that is from R, and this gx is coming from this fq. Means this is combination of these two, fq and R. So first time we consider when we consider fx, then we have to took the right divisor of x to the power tau minus 1, and when we consider gx, then this is simply the divisors of x to the power rho minus 1. That is, this is generated by the linear combination of these two sets.
So thanks again, Professor Patel, for your contribution. We have a limited time. Please make private conversation between Professor Turan.
This work is under progress, so I am exploring this. So I have to make some examples right now. This is under progress.
Okay, thank you again. Please stop sharing your screen.
Thank you. Thank you.
So I kindly invite the next speaker for Professor Sabri from Algeria. She is gonna talk about multiplicity of solutions for non-homogeneous elliptic equations with critical exponent. Please share your screen, Professor Sabri.
Hello?
Hello, please share your screen.
Yeah.
So please make it full screen. You can use Ctrl+L. So everything is fine. You are welcome to present your study.
Hello everyone, and thank you for your being here. The subject of my presentation is multiplicity of solution for elliptic equation with the critical exponent. Here's the outline of my presentation. First of all, I will be looking at the problem statement. Then I will discuss the existence of the first solution. And finally, I will finish by looking at the existence of the second solution. In this work, we are concerned with the existence and multiplicity of solutions to the following non-homogeneous quasi-linear elliptic problem. With the critical Kaffarli-Nuremberg exponent P star, such that P is between 1 and n, A and B are numbers, lambda is positive or equal to 0. G belongs to the dual of circular space W, is a continuous function and Rn, such that G of 0 is strictly positive and H is a bounded positive function on R. Here, W of Rn denotes space obtained as the computation of the space C0 infinity with the following standard term. The problem P is related to the following well-known Kaffarli-Nuremberg inequality for some positive constant CIB. If we take B equal A plus 1 in the preceding relation, we obtain the following Hardy inequality. In the hour space W, we use the following norm for all mu positive or equal to 0 and less than ui bar. A Hardy inequality, it is equivalent to the usual norm of the hour space W. Since our approach is variational, we define the functional A on our space W by the equation equation 4. From the relation 1 and the fact that G belongs to the dual of circular space W, we deduce that I is well defined in our space W and belongs to C1. Now we define a weak solution of our problem. The function U is said to be weak solution of problem P. If U it satisfies the equation 5 for all V belongs to space our space W. Elliptic problems involving the Hardy inequality or Hardy-Sokolov inequality has been studied by some others here in bounded domain or in the whole space Rn. Kang proved that for epsilon positive, strictly positive, and a radial function U, the equation 6. Satisfy for lambda equal to 0, with H is equivalent to 1 moreover V epsilon achieve S mu in equation 7. بشقيف عند مطلع studies the problem P for P equal to. We consider the following assumption H. Our main result is the following theorem. Assume that H satisfies H and G belongs W, dual W, is a continuous function on Rn, such that G of 0 strictly positive. Then there exists lambda étoile, lambda star strictly positive, such that the problem P admits a solution in W. In our work, we prove the existence of less to this critical point of A, one by the equivalence variational principle with negative energy, other by Montaigne-Plus theorem with positive energy. As the problem under consideration is critical, then the Kaffarli-Nuremberg, if they are not compact, let's UN in our space W, we are a sequence such that in this equation, then either UN converge to U1 in our space, or C strictly superior set this quantity. To prove this lemma, we use the condition H and the Brisislav lemma. Now easy calculation show that there exists rho zero positive, small enough and this quantity, this equation, such that energy A strictly positive for lambda between 0 and lambda 1. Since G not identical 0 and continues on Rn, we can choose phi belongs C0 such that this integral strictly positive. Hence, E of TV, T is negative for two T strictly positive small. We also assume that T is now small enough that such that the norm of T phi strictly less to rho zero, thus we have C1 strictly negative. Using equivalence variational principle for the complete metric space B rho zero bar with the respect of the norm of W, we can prove that there exists a policeman C1 sequence UN in the bool such that UN converge with lever U1 for some U1 with the norm of U1 strictly inferior to rho zero. Now we claim that UN converge for U1. If not by lemma 1, we have this quantity or this inequality. Then our contradiction. Then we obtain also critical point U1 of A for all lambda between 0 and lambda 1, satisfying C1 strictly negative. On the other hand, we have this quantity, C1 equal this quantity. This U1 is a non-trivial solution of our problem with negative energy. Now we use the one-time-pass theorem to prove the existence of a non-trivial solution with positive energy. Let lambda 2 strictly positive such that this quantity is positive. Then for epsilon positive, there exists Z epsilon belongs in our space, and lambda 3 between 0 and lambda 2 such that sup of A of T Z epsilon inferior to C star. The proof of lemma 2, for proof this lemma, we use the function V epsilon when S mu is attained and the continuous of G and the condition H. since the limit of the A of t z epsilon equal to minus infinity, we can choose t large enough such that the energy of t z epsilon is negative. We have E in the bar of whole strictly positive for all lambda between 0 and lambda 1. Then by Montan-Pass theorem, there exists a policeman C2 sequence UN such that E of UN converge to C. And E prime UN converge to 0, where C2 is characterized by this quantity. With gamma equal this quantity. Then UN has a subsequence still denoted by UN, such that UN converge weakly to U2 in our space W by lemma 1 and lemma 2 if UN not convergent to U2, we get this inequality. Then UN converge to U2 in our space W. Thus, we obtain a critical point U of A for all W for all lambda between 0 and lambda star. With lambda star equal this quantity satisfying I de U2 strictly positive. It is the reference. Thank you.
Thank you for this good presentation, Professor Sabri.
Thank you.
Is there any question or comments? Let's wait for a while. So it seems there is no question. Thank you again for your contribution, Professor Sabri.
Thank you, sir.
Please stop sharing your screen.
Yeah, thank you.
So we have a nearly 7 minutes break before the next talk. I would like to invite the next speaker from Indonesia, Professor Febrianti. She's gonna talk about solving Black-Scholes equations for barrier option pricing using adaptive differential evaluation neural network algorithm. Professor Febrianti, please open your video and share your screen.
Okay, thank you, Mr. For the chance.
So please make it full screen. Okay, thank you. Everything is fine. You are welcome to present your study.
Okay. Good evening, everyone. Thank you very much for this chance. Today, I will present about the paper with the entitled Solving Black-Scholes Equations Numerically for Barrier Option Pricing Using Adaptive Differential Evolution Neural Network Algorithm. This paper is under supervised by Professor Kunchoro Aji Sidarto and Mrs. Novriana Smarty, PhD. I'm a member of Financial Mathematics Research Group from Institut Teknologi Bandung, Indonesia. Here's the outline of my presentation today. The first is about introduction, and the second one is about the brief overview about the theory in our experiments, and the third one is about the problem and the results of our experiments, and the last one is conclusions. We continue for the first part in this presentation. And for the introduction, we have known that Black-Scholes equations, or also known as Black-Scholes-Meltern equation, is a partial differential equations in calculating financial market options. This Black-Scholes equations was first introduced by Fisher Blacks and Myron Scholes in 1973, together with Robert Merton, have revolutionized the equation in financial markets, especially in option pricing. And in equation 1, this is the general equation for the Black-Scholes equations that are usually used in option pricing, and the boundary conditions like in equation 2. And for calculate the payoff for vanilla options, we use the payoff like in equation 3 and 4. And equation 3 is for payoff for European call option, and in equation 4 is usually used for calculate the put options. And we have known that many numerical calculations have been used to solve Black-Scholes equations, especially using finite difference method. But now we will present about an approximate solution to the Black-Scholes equation using the mess-free method, namely the optimization method. Before that, many researchers has do the research about approximate the solution for the Black-Scholes equation. Like Chen et al. Has introduced the approximate solution for Black-Scholes using genetic algorithm, and then Kahn and Smith Miller has introduced about approximating the Black-Scholes equation using neural network concept. Now in this research, we also use the meta-heuristic algorithm to model the equation for the that we have modeled a Black-Scholes equation into an optimization problems. To change the Black-Scholes equation into an optimization problem, we use a residual method. Then this residual method is solved using meta-heuristic algorithm that is called adaptive differential evolution neural network. And for the brief overview about the theory, I will explain about the trial solution that we use for approximate the solution of the Black-Scholes based on neural network concept, and then about the meta-heuristic algorithm that we use in this paper or in this research. In this research, we use combinations of differential evolution algorithm with neural network algorithm. For the first, about the trial solution that we have used to approximate the Maxwell equation based on the neural network concept. For the first, we formulate the trial solution based on the neural network concept, like in equation 5, based on Lagares et al. And x1, x2 is defined for partial differential equation for two variables. And here G is corresponds to the boundary conditions of the differential equations. And for the f, x, and xx of P, it's contain the activation functions like the trigonometric functions, sigmoid functions, and linear function from linear combination of independent variable from partial differential equations. And for the trial solution of the problem of the Maxwell equation, we formulate like in equation 6, and here is Px is for the payoff for European co-options, and Fz is for the activation function of neural network that we have used. Next, we continue to explain about the materialistic algorithm that we use in this research. In this research, we use adaptive differential evolution neural network algorithm. Here, we use this algorithm to find the coefficients in equation 6, like to find alpha, mu, omega, and beta. And for coefficient that we have don't know that we want to find from this equation. And here is the algorithm that we use to find the solution for the Maxwell, to approximate the Maxwell equation. For the algorithm 1, we use adaptive differential neural network. And here is the step of the algorithm, where DA is one of the evolutionary algorithm that is inspired based on a genetic algorithm. And differential evolution is found by Stern and Price in 1995. And this is we use the updating population and weighted of DE using neural network algorithm. And here is the brand new that we use in this paper. Like for the first, this is the standard DA that classic, and we do modification in this mutation part, where in mutation part for find the weighted of the mutation, we use the neural network algorithm. And after mutation, we do crossover part, and then the last one is used. We do selection in the air to find the best solution. And for the next materialistic algorithm we use is neural network algorithm. And here's the algorithm. This is the 3 part that we use in this algorithm. This is initialization, population, and weighted. And then we calculate the fitness function value, and then we update the weighted and the population. After we get the weighted and population, we check the population in the boundary condition. After that, we find the best individual of the population. And this is neural algorithm is the one of the brand new materialistic algorithm that was first introduced by Iss Model in 2018. Here, updating the weighted and done when the is also followed by updating the population. And here is the idea of updating new pattern solution from neural network algorithm based on the paper 7 or Algebra papers. And we see from this, we define that the total value of the weighted is must be 1 or equals 1, and its rate is from 1 until the number of populations. And this is if we hybrid it with DA. And for this section, we will explain about the problem and the result of our experiment. For the first, we use simulations for solving to approximate the solution of Black-Scholes. Especially in this case, we use European co-option. We use the parameter, input parameter the same with the paper 4. We use the strike price is equals 100, and this is the risk-free interest rate is equal at 12%. And for 1 year maturity date of the option contract, with the volatility is 10%, and the stock price is from the 70 until 130. And for the first, we calculate the European co-option without barrier, and then we calculate the European co-option with barrier down with the barrier value is equals 80. After that, we use various measurement like mean absolute error, mean square error, and then mean square relative error in order to do the performance analysis. And here's the results of our experiments. And here we use the population size of 100, and maximum of number of iteration is in this computation is 1000. And we use it, all the computation are running in MATLAB program. With here's the specification of the laptop that we use. And there is the error of the European co-option using adaptive DE, the adaptive differential evolution neural network is stated in table 1. Here is the 3 types of errors that we have used, that we have calculated in our experiments. And here is the result of mean absolute error for European option without barrier. In the second table is the second part of this cell is about with option without barrier down and out option, and option without barrier down and in. And here's the result that we get. We see that means square relative error for European co-option without barrier is has the mean is like this, and for option without barrier like this line. And for the next, we have draw the surface of Black-Scholes. Here the graph of the result with the 5 neurons that we have used, and here is the Black-Scholes surface for European co-options. And here's the left side is the exact solution, the surface for exact solution of Black-Scholes equation, and the right one is the numerical solution of surface of Black-Scholes equation. This is the surface based on the adaptive DE neural network. And in figure 2, we can see that the graph of the exact solution fits well to the numerical solution. Here is the convergence of our algorithm, and this is the surface of the Black-Scholes with barrier options. Here, we use barrier down and option for this surface. With the barrier down is equals to 80. And we can see that the surface of exact from the adaptive DE neural network is fits well to the surface of the exact solution. So we can conclude that we can use a neural network concept to build a trial solution of the Black-Scholes equation, and we can use adaptive differential evolution neural network as an alternative way for solving optimization problem, especially for approximating the Black-Scholes solution and Black-Scholes that is equipped with the barrier option pricing. And here's the reference that we use in this paper. That's all of my presentation at this time. Thank you very much for your kind attention.
Dear Professor Febrianti, thank you for this interesting talk. Is there any question or comments? Let's wait for a while. I think there is no question. Thank you again, Professor Febrianti, for your contribution.
You're welcome, Mr.
Before the next talk, we have a little break for 5 minutes. As a last speaker of this session, I kindly invite Professor Düzgün from Turkey. He is gonna talk about a comparison of without elimination method and a new method for solving nonlinear systems of equations of second order. Please share your screen, Professor Düzgün.
Excuse me, I cannot share. Can you see can you see my screen? No.
No, is there any problem? So please try it again.
May I take a few seconds, please? I cannot share.
Yes, we have a limited time. Please try it again.
Here it is.
So I think
is it okay?
Yes, please make it full screen.
Okay.
So you are welcome to present your study.
Okay, thank you very much for this organization and giving me the chance to present our presentation. And good evening for everyone. Good evening to everyone. Our presentation is about second order set of equations, and we proposed a new method for this, and I will talk about this. First, I will explain one article about this problem. It's about Stewart Gulf platform, but it can also used in any set of equations. Then I will talk about the Bezo method and our proposed method, and I will give some numerical example from both Bezo method and our proposed method and the comparison. I would like to start with Stewart platforms. As here